Maybe let's start. Okay, I think we're live right now. This is going to be live stream. So, well, hello everyone. Welcome to CK Accelerate. I'm super happy and pretty excited to be here. My name is Leandro, and I'll be your host for the day, or at least for most of it. Well, I think that the whole idea for today is to celebrate CK engineering by gathering the best companies in the industry working with CK and hardware acceleration, and have some great talks, panels, and of course some time for networking. This has been a rough week for everyone, so thank you all for being here. And I want to start by thanking Ingonyama. They are the organizers of the event. Since day number one, they've been working a lot for this event to be the best and to gather the best people. Unfortunately, due to this crazy world that we lived in, they couldn't make it to here, so I'm here today representing them. But there is a big but in this. They said that this will be the first of many events that they will do. So please let's give a big round of applause to Ingonyama that for sure are watching the live stream. Ingonyama here. So, well, before going to the sponsors, I want to also thanks to Chloe that you might have seen wandering around there. She's been working a lot, and when I say a lot, it's really a lot for this to happen with the organizers abroad. So thank you, Chloe. She's there. If anyone needs anything, there's Chloe. And well, last but not least, we have the sponsors. This won't be happening without these companies working in the industry. So we have two partners. We have AMD that for sure everyone knows what they do. Sometimes for sure you have heard of. And we have Lambda Class as partner, which I work for. And then we have a lot of sponsors. I will mention them. We have Electron, NIL, Takeo, RISC-0, AWS, Ola, QED, Marlin, Lagrange, Starward, Geometry, Helio, Lumos, Sama, IOSG Ventures, Matter Labs, and Polygon Maiden. So please, thanks to the sponsor. Big applause. Thank you all for being here. To finish, I want to have a little recap on the agenda. This will be a day completely full of talks. So this is a QR for the agenda. If you have the badge, there you have the QR code as well. You can watch all the agenda there. Please, speakers, if you're here, some of them are, don't be mad at me if I make some signs for you to stop. The agenda is completely tied up. If people have Q&A and we don't have time for Q&A on the stage, for sure you will find the speakers or the companies in the networking area. So please, let's try to do the best to respect the schedule because, well, we all need to talk. So, and for the speakers, we had a timer over there that is saying me, I need to go fast. So, thank you all again. I hope you enjoyed this day. Thank you for being here. And well, let's get this party started by I'll be presenting the first speaker. We are having Mami Ratsimbasafi, I guess it's right. From Takeo, that will be talking about standardizing CK EVM acceleration API. So, thank you all.
Hi everyone, I'm Mami Ratsimbasafi. I joined Takeo 6 months ago as a ZK engineering lead. Previously, I was working on the consensus layer of Ethereum for 5 years, in particular accelerating BLS cryptography on the BLS 12381 curve. And when I joined, one of my objectives was accelerating Halo 2. So Halo 2 is used by Takeo, but also by many other companies like Axiom, Scroll, Ezekiel, LurkLab for their Nova backend, and others. And one of the biggest remaining issue is making it fast. which involves GPU FPGA acceleration. We have many companies working on this. Ingonyama, for example, Superscalar, Supranational as well, which did the BLS acceleration for consensus layer. And I think for further innovation, we need to standardize, to decouple the backend and the prover. So let's talk about the agenda. We'll just give you a brief overview of the state of the PSE, so Privacy Scaling Exploration, a team at the Ethereum Foundation. Then a teaser of the end goal, how to go there, and what's left after this one. And then some Telegram, Discord ideas for how to collaborate if you want to join the effort. So, state of the code base. As I said, we have many users, coprocessors like Axiom and Ezekiel, compiler and high-level frameworks like Lurk and Powder, and rollups like Scroll and Tycho. On the hardware side, we have Hello 2 KZG with a couple of let's say, proof of concept for hardware acceleration, some that were using code for Matter Labs, the Bellman accelerated code, others that were created in October from Superscalar or Delphinus Lab on the Zcash side. Yeah, one thing when I say Hello 2, it's Hello 2 KZG, the one used by PSC, but Zcash has the original library that uses IPA for commitment. And we also have Arcworks that so far has been the target of GPUs and FPGA acceleration. How to make them all work together in a nice land filled with unicorns, that's the goal of the talk. On the software side, I want to highlight a bit some of the efforts I did. So on the Hello 2 KZG 187 issue, I've outlined 7 steps to go from current Hello 2 speed to state-of-the-art. We have recently had ZCalc and a talk at ZK Summit 10 about benchmarking snarks. That said that GNARC is the fastest MSN provider benchmarked, and it provided above 10 times more speed than Hello 2 KZG. And besides that, I have also my own personal library that I wrote from scratch in the past 4 years, called Constantine, that reaches the same speed as GNARC, or even faster, like up to 40% faster, but it's only on a small number of points that are applicable for EIP 4844, for example. This is a slide that I shamelessly stole from the talk at ZK Summit 10 that highlights GNARC and Arcworks and other implementation. Just say that GNARC is below, and since time, that means it's the fastest. Now, why do I still talk about software in a GPU and FPGA and hardware acceleration conference? Because I think software still has potential. GPU renting cost is quite high, and we're in competition with AI startups that want to gobble up all the GPU available. We have also GPU embargoes, so some of the cheap providers are in China, like Tencent, Alibaba Cloud, and they can't give access to the latest NVIDIA GPUs. The other thing is that we can still have access of many threaded CPUs, like AMD EPYC CPUs. You can have 384 threads if you use 2 sockets of the latest EPYC. And on Xeon Platinum with 8 sockets, you can get up to 960 threads. Is there someone using this, that much compute on ZK to see how inexpensive it is compared to GPU? I don't think anyone is using yet. And how would I use this today with my own library or with GNARC or Arcworks over? Well, so far, the Hello 2 KZG and Arcworks library are using parallelism at only one level. but you have many more level of partitioning points. So MSM level partitioning, where you have 1 million points and you compute on 500,000 points on one side, 500,000 on the other side. Why don't we do this? Well, because if you split, you don't benefit from the multiscalar multiplication, which makes the complexity grows by n divided by log n. So we try not to do this too much. Then there is window-level parallelism that everyone uses it because it's the simplest one. And there is bucket-level parallelism, which provides the more parallelism possible because you have millions of buckets if you have, for example, 4 million points. And the issue is that you need sorting because otherwise you have collision and data races. So, in terms of software feature developments, besides what I talked about, there are also specialized MSMs that are specialized for lookups, or for example, for Keccak hashing functions that worked at the bit level. And we have an example of Halo 2.202 done by Axiom that accelerated Keccak implemented at bit level by 40%. Plus, we also have prover level parallelism, where, for example, for EIP 4844, for batch KZG commitment, you have free scalar, multiscalar multiplication that you can compute in parallel, and those will be parallel as well at free level, and then you have 4 levels of parallelism that you can use for acceleration. Now, the end goal. I guess everyone knows this XKCD. There are 14 competing standards. We need to develop one universal standard to cover everyone's use cases, and then there are 15, except there are 0 at the moment, so hopefully we can kick the ball and get this started. Concretely, we want to dissociate the proof system from the computing backends because provers are always evolving. We had KZG commitments-based provers, IPA-based prover. Now we have GKR prover with some checks. And we use MSMs, FFT, primitives that hardware provider can target without being worried about all the prover changes. Now, also hardware accelerator, they want to minimize the work done and have multiple prover for a single, with a single code base and just very small adapters, maybe 50 lines of code, just to make sure that it works for everyone. This reduces maintenance costs, reduces the bug surface, and they focus on their specialty. And proving library can focus on the high-level part, lookups, optimization, etc. Plus, they can do differential fuzzing and benchmarking because, well, in the past couple of months, we see a lot of benchmarks, but it's very hard to compare. Still, everyone says it's apple to oranges, and we haven't had Twitter fights. And in the end applications can pick the backend, hardware acceleration backend that they want. Maybe they want AWS, maybe they want to work on GPUs, maybe on FPGAs. It's in the control of the end applications instead of the proving library like Halo 2 or Arcworks. How to get there? I made a proposal 2 months ago called, called since this talk, Acceleration Abstraction Layer. It proposes an encoding of field elements, of elliptic curve G1 elements, optionally an async API to issue multiple MSMs or FFT. And how it does this is all FFT and MSM are prefixed with a context parameter called engine. And that's where all the nitty-gritty stuff and the implementation details go, like number of cores, so you can read your environment parameters, or the GPUs to issue the multiscalar multiplication or FFT2. Thankfully, there is not much difference between Halo 2, Arcworks. I mean, everyone is using little endian for limb endianness. because all GPUs, AMD, NVIDIA, Apple are using Little Indian. Also ARM, x86, RISC-V are using Little Indian. So it just makes sense. And because we're talking about proving, usually, well, Halo 2 is using peri-friendly curve, so everyone is using Montgomery representation. Now, for stacks, we can, of course, use a canonical representation for this. The ABI was inspired by accelerators for image processing and machine learning. So I used to be a data scientist and a deep learning developers. I've used CUDA, cuDNN, 1DNN from Intel, OpenCV HAL, a hardware abstraction layer, which is very much in line with what we want to do, and also the Windows kernel APIs. The main difference is that those sometimes ask you to first query to get the size of memory to allocate, and then they tell you allocate the memory. I think this is going a bit too far, so for now I've not done that, but I'm open to suggestions. And as I said, engine context, and maybe at one point we'll add an optional operation descriptor if you want to cache, for example, your trusted setup, and you don't need to recompute it at the beginning of the MSM. I've looked into the changes that are needed in Halo 2. Best FFT, the FFT compute appears twice. The only issue is that there are also coset FFT, and I have yet to figure out what API and ABI to get for those. And best multi-exp. I really don't like the multi-exp name for multiscalar multiplication. It goes to additive versus multiplicative notations, but it appears only 9 times. Thing is, those propagate to everywhere, so we need to change everything. Now, what's next? For now, I focus on the sync API because everyone is doing sync call to multiscalar multiplication, but in the future, async API, so you just call MSM async, a bit like CUDA, memalloc async, and then you just wait on this, and you can compose as you wish. The caching abstraction I mentioned, and then some of the hardware acceleration team, like Ingonyama, said that, well, just MSM might not be enough. We might need KZG commitment level acceleration, or even Planck level acceleration, so that everything is done in GPU. We can explore that later, but let's get a working group started first, and go forward from this. Now, collaboration. You can read my issues 216 on the PIC codebase first. There is also Superscalar that did their first proposal. And you can talk to me on the side. We can discuss if we create a Telegram group or a Discord channel. And I invite all software libraries, hardware providers, and end users to talk to me afterwards. Thank you very much. I can take questions if you want. I have 1 minute 30. Okay, thank you.
Okay, thank you, Mami. Now I will leave you with Emil Beistel, right, from AWS. Yes. Thank you.
Thank you. Is this the clicker? Yes. Oh, the countdown has started. Good morning, everyone. Thank you for waking up early and coming to these talks. Recently, I've had the opportunity to work with a few ZK rollups and ZK bridges who have been building on AWS. And a lot of these projects require fairly large instances, so maybe dozens of CPUs, lots of RAM, all that stuff. And a common question which comes up is, how do I reduce the cost of this? And so what I want to share today is one way that we designed for reducing the cost of running your ZKPs on AWS. My name is Emil Beistel. I'm a blockchain architect at AWS, so let's get started. And that's me. Okay, so today we're going to start with an overview of EC2, which is our Elastic Cloud Compute. If you've ever spun up an instance on AWS, you've used EC2. I'm going to talk about the different ways that you can that we price out EC2. And then we're going to get into some more of the details around spare capacity of EC2, which is what we call spot. And that's really the underlying thing which we're going to use here for cost optimizing our ZKPs. And then we're going to do a bit more technical deep dive into specifically what you need to do to run ZKPs, because there are some nuances with running on Spot versus running on that. And then we're going to end with a bonus, untried, untested, theoretical thing around serverless ZKPs, and this is something which came out from a discussion I had with one of those projects. So let's talk about EC2. As everyone here knows, depending on the type of application that you're running, if you're running a website, if you're running machine learning or DNA sequencing, you need very different types of compute requirements, right? And that's why we have many different categories of compute. There's compute, CPU intensive, memory intensive, stuff that has instant storage versus network storage, so a lot of different kinds, and we're adding to this quite a bit, and so there's over 600 different instances. And if you're wondering why does this matter with Spot, the reason why this matters is one of the key ways of being successful with Spot is being very flexible in the instances which you run, right? So having flexibility in which instances you can run your ZKP on is going to improve your opportunities for running on Spot. Okay, so let's talk about the purchase options. So on the left, you've got on-demand instances. So if you've ever spun up an instance from the AWS console, you click Start, more than likely, you've gone with on-demand. And with this one, you get billed by the second. So if you run it for 2 minutes, you get billed for 120 seconds. You shut it down, you stop billing. And this is good for sort of spiky workloads, if you need something to run for a bit of time and then shut it down. But if you're going to run something that's long-running, if you're going to run a website and you know it's going to be running for a long time, you're better off doing a savings plan, because you can commit to 1 year or 3 years, and so you get a reduced cost there. And the last one is the one which we're going to spend the rest of the talk on, is Spot instances. And with Spot, you're basically taking advantage of spare computing capacity on EC2 to get up to 90% discount. And that's where the cost savings comes in here. But there are some constraints here. And so Spot is really optimal for stateless and flexible and fault-tolerant workloads. And I'll get into the fault-tolerant piece here in a second. Okay, so let's see how this works. So as an example here, we've got several different instance types, and we're going to look at one of the instance types here, the C6i 12x large. It doesn't really matter what the instance type is. This is just for one. And when we talk about elastic, what do we actually mean by that? So as AWS, we want to always be able to offer instances on demand. So when a user says, hey, I want to spin up a C6i 12x large instance, we want to be able to provide that. So in order to be able to provide that, we always have spare capacity ready to go to provision. Now, what we see in this picture is a stack of C6i 12x large instances, and this is just a figurative representation, but the red boxes here are the ones which are currently being used. The white ones are spare capacity, and we call this the Spot pool. So you come in and say, hey, I actually want to spin up a Spot instance of this, and so now you have a Spot instance of the 12x large here, and this one comes at a very steep discount compared to what is if you're running there. So that's how Spot works. And underneath it, you're using the exact same hardware, the same infrastructure, as if you were going through on-demand. Everything is the same. It's just the pricing and how we price it, which is different. We talked about the pricing. You get up to 90% discount on this. Interruptions. We haven't talked about this. So this is something that is different about Spot. So because we want to be able to serve customers that request this on demand, we need to be able to reclaim the Spot instances when capacity dries up, the spare capacity. And I'll get into interruptions more in a second. And then diversification, we talked about this a bit, but being able to be flexible in the workload which you have. I don't know what is that stuff on there. Okay, so interruptions. So let's say you're running Spot, and then EC2 says, we actually need to reclaim that because there is a surge in the demand for the on-demand instance. So there's two ways of reclaiming. The first is proactive, and this is the recommended one. And proactive is basically a warning that you receive on your instance that says, demand is rising for this instance, and there's an elevated risk that your instance might be reclaimed. So this gives you an opportunity to do anything you need to do to prepare for that and then wind that instance down. Or there's a reactive, which basically gives you a 2-minute warning that says your instance is about to shut down in 2 minutes, and then you need to take any actions there. So ideally, what you can do in that 2-minute warning or in that proactive warning is save any state which you've already generated in your proof so that the next time the spot spins up, you haven't lost all that compute which you've done there. So your proof generation needs to be able to pick up from that state. Otherwise, you're just going to have to restart from everything else. A bit about diversification. This comes in a few different areas. So the first is instance type and instance size. So rather than saying I want a C6i 12XL, you can maybe say I need at least 48 CPU and at least 1 terabyte of memory. And then whenever an instance is available that matches those requirements, you will get matched. So being flexible in which one works will give you a lot better opportunities. If you don't have any restrictions or requirements on geography and where that runs, that's going to increase your opportunity as well. So regions and availability zones, and then being flexible on time. So if you don't need it this instance and you can wait, minute or hour or something like that, that helps. Okay, so now we know about Spot, how all that works. Let's see how you build ZKPs on Spot. Okay, so on the left, at the bottom here, you've got an Amazon machine image. So when you spin up an instance, whether it's on demand, Spot, anything, it loads an Amazon machine image, will load up your base system. And that pretty much is your operating system. We keep it very, very lightweight because we don't want to bloat it, and we don't want to add additional libraries, which you may or may not need, which introduces additional security threats and things like that. So we keep it very minimal. But any application you're running, whether it's a web app, whether it's a ZKP, you're going to need utilities on top of that, right? You need your Git compiler or your Git command line. You need some compilers. Maybe you need to build a compiler. Maybe you need to install a package manager. So all this stuff adds time, right? And on top of that, if you're building a snark and you've got a huge circuit, you're going to have a several gigabyte proving key, which you're going to have to download to your instance. Now, if you're running an on-demand instance that's always available, this is fine. It's a one-time hit that you're going to take. Maybe you can wait 10, 20 minutes, however long it takes, and you're OK with that. But if you're doing this on Spot, and your instance is going to wind up, run, and then wind down, and then wind up, and you're going to take that hit every single time. And so what you can do is set it up one time, take a snapshot, and create your own AMI. Now, the next time your instance spins up, again, whether it's on demand, whether it's Spot, you're going to start from this point. So right away, all you need to do is download any data that you need for generating the proof, and then you can get going there. So this in itself is going to save you a lot of time in the proof generation there. So some considerations with Spot. As we talked about, must be interruption tolerant. So being able to respond to that warning that your instance is about to be reclaimed, and ideally persisting state somewhere else. So then when the Spot instance recovers, or when you come back online again, it can pick up from where that is. The second one, this came from one of the ZK rollups where they were saying, depending on mainnet pricing, they may hold off pushing state onto mainnet for hours, because the cost of pushing that state onto mainnet is so expensive, and it's going to go down with 4844. So hopefully that makes this less of an issue. But they're already coordinating with mainnet pricing, so having to coordinate with Spot pricing may introduce an additional complexity, or it's something which needs to be designed around. So for example, if you're generating your proofs and then you just have them ready to go whenever mainnet pricing is available. The other thing is not all instances are available as Spot. So again, this comes back to flexibility, being able to be flexible on which instances you're running, and not every instance is available in every region as well. And the last one is something came out from one of the ZK bridges, which I was talking to. They want to continually or periodically on a consistent basis send state from mainnet to another blockchain. And so this is something that they don't want to depend on spot, because if spot pricing is too high for a while, then they're going to have a long period where they're not pushing state. So for them, having a baseline capacity makes a lot of sense, right? So taking a reserved instance where you're getting a lowered price for committing to like a year or 3 years makes a lot of sense. But on top of that, applications can request proofs on demand, right? So if there's a trade or if there's something else where an application on the destination chain requires some state from mainnet, they can come in and request that. And so for that one, spot makes a lot of sense, because then you're serving sort of spiky demand with spot instances without impacting your baseline capacity. And you might even be able to service those requests with your baseline capacity if you're not generating one of those proofs during that period anyway. So that's another consideration there. So that's it for Spot. I want to talk about serverless ZKPs for a second. And this is something that hasn't been tested or tried, but it's from talking to one of those ZK projects, they mentioned that they were starting to look at this. If you're not familiar with serverless, you can think of it as code that runs on an event, and then it just winds down. So there's no servers, there's no instances. Well, there are, but we manage all the servers and instances. So for you, all you do is you deal with the code, and then we run your code for you, and it shuts down. So it's great. Lambdas are used all over the place. They connect many services together. They're used in data transformation and API handling and all that stuff. But there's a lot of restrictions here. And so this may not work for everyone, but it's worth sharing here. So the first thing is you can't create a custom AMI, right? So all that we talked about of creating your own image with the utilities and the binaries and all that stuff, you can't create that as an AMI. And also, this requires running a runtime. So instead of starting with an OS, you're actually doing a runtime. So by default, we have all the popular runtimes. We have Node.js, Python, Java, several others. But you can also provide your own runtime as well. There's this thing called Lambda layers that are basically, you can think of them as static artifacts that your Lambda can access. And those are a 1/4 gig each, and you can have up to 5 of those. And so those utilities and other things which we talked about, you can actually put those in the Lambda layer. So you have about a gig of artifacts which your Lambda can access at the time which it spins up. And then locally, you have 10 gigabytes of file storage. So if your proving key falls within that range, then you might be able to actually do this here. And for using additional storage, you can use Elastic File System, which is a network file system, and that can be your persistence for your proving key, or you can download it from S3. So if you're actually able to run your proof using a proving key that's on a network file system, this could actually work really well, because you no longer have to take that hit of downloading the 10 gigabyte proving key or whatever to your local file system. Last thing here, some Spot tool sets, things to help you get started. The first one is blueprints. 5 more minutes? Okay, I thought it was a bit short. Yeah, Spot blueprints that provide a great way to get started with your Spot. And then the last one I want to point out is the fault injection simulator. And so what this helps you do is simulate getting that interrupt alert. So if you want to test your Spot instance with getting that interruption and being able to test that, that will help you with that. And that's it. Thank you.
Well, there you are. How you doing? Good. Long time. Okay. Please welcome Timothy. Timothy.
Okay. Can I put my computer? I have a few
You
notes.
cannot put your computer. Do you need to put your computer?
I have a few notes.
to show like them?
No,
that's the issue.
just
you have everything
having
here.
it there to be able to read my my notes.
Okay, let's take some room over here. Let's try to make some
Yeah,
space.
it's a big one.
I will bring a chair, maybe.
So I press this. Okay. Okay.
Fine or not?
Yeah, it will be fine. So I press this button and this to go back.
Yeah, and this is like a LED for the screen.
Okay.
Okay, you're good to go. Thank you.
Good to go, yeah. So, nice to meet you. I'm Timothy. I work. Oh, I can stay there. Okay, I will stay there. So, hello. I'm. Yeah. So, hello. I'm Timothy. I work at Starkware as a part of the exploration team. I'm currently leading a project named Madara, which is an alternative implementation of the StarkNet sequencer. It's an open source project. You can come and contribute, and we will pay you to do so on a PR basis. But today I'm here to talk about Cairo, the language, which has been developed by Starkware in order to easily develop Stark constraints so you can prove any language. So this is Cairo. It's a Turing complete language. So you will be able to write any code you want and then have a proof of this execution. But before, we are going to talk about Stark a little bit. So Stark are mathematical constraints that allow you to prove some execution of computation. So the big idea is if you give me a program and an input, I will be able to give you an output and a proof of this execution, so you can verify that the output is correct given the input using the proof. So that's what the Starkware team came up with, and they created in this paper, they presented it. And in the early age of the company, they were writing those Stark constraints by hand for some clients, like DYDX, which is like a trading platform that was able to build its application with Stark and have like insane performance and no cost for user to emit trade because they can scale very much. So the good thing when you write those by hand is that you learn a lot. The bad thing is not scalable at all, and you have for every new type of operation you want to develop in your application, have to write the constraints yourself. It's really error-prone. It doesn't scale. So they came up with a way to automatize this, which is the Cairo architecture. It has been published in this paper 3 years ago, and it describes a CPU architecture because basically it defines a bunch of registers and memory zone and a set of instructions you can use to write to those memory zone and update the registers. And the big idea is that rather than writing the constraint for your specific program, they wrote the constraint for the virtual machine and the way it's going to update its own state. So by doing so, we can execute any program in this virtual machine and prove its execution by proving each one of the execution steps. So we are not really proving your program, we are proving the execution of your program on this specific virtual machine. Good thing with the design of the Cairo virtual machine and the language itself is it allows for non-deterministic computation. The idea is that when you write Stark, you don't really write instruction, you write constraints, and then there will still be instructions, they will be executed by the prover, but the idea is that the prover can execute actually whatever code he wants, as long as it respects the set of constraints you define. So we are going to approach this with an example. Let's say you want to find the square root of this number, which is 31. You can go two ways. You can go the classic execution way, where you will create a function that will compute the square root of a number. It's a fairly complicated thing in terms of execution. You have to find it progressively. Or you can go the non-deterministic way, which is the second example. The idea is that if you were able to magically guess that the value you are looking for is 31, you can then write a constraint that will take this value, multiply it by itself, and assert that it was equal to the original value you were looking the square root of. And this, in terms of proof, just gets the job done, and you don't have to prove every execution of your square root computation algorithm. So you can spare a lot of computation doing this, and it's done in Cairo with what we call hints, which is what is happening in, let's use the laser here. So this part of the code between the weird brackets, it's something you give to the prover to execute, and it can be any piece of computation. It can be Python code, Rust code, C code. It can do HTTP request. It can do whatever we want. The important thing is that at the end, it updates this value into the Cairo code. It sets X to this value. And then, as a developer, you have to write the correct constraint to make sure that this value is the one you were looking for and is valid in the context of your execution. So the first way you can do this is with a syntax like this. So this is a kind of, it looks like assembly, and it is assembly for the Cairo virtual machine. You can see some AP, some FP. Those are different, those are the two registers that exist in the Cairo virtual machine, and you can update them manually, you can call, you can do some jumps when you define label. So the syntax is really assembly-like. The good thing with it is that there is no overhead, and you know exactly what you are doing. The bad thing with this is that there is no abstraction at all, and you have to know precisely what you want to do. So it gets the job done when you have a deep understanding of the Cairo virtual machine, but it's not for everybody to use because there is probably a good learning curve. The good solution is, the good news is that we have a solution. The Cairo virtual machine take as an input this kind of file, which are like JSON-like file. It's Cairo assembly, and any language, in theory, well, if you have the right compiler, can be compiled to this, or at least you can write different language that can compile to this. You declare function, constant, a bunch of things, and then the Cairo VM takes this as an input and is able to execute the contract. So we were able to come up with a higher level syntax, which looked like this and was known as Cairo. Now it's known as Cairo 0 because we come up with the next thing on this talk, which is Cairo 1. And the thing is, people at Starkware, they are mostly mathematicians and cryptographers, so they really liked Python, and they kept the Python syntax, so you can recognize it. It gets the job done when it's about looking like a regular language. It looks like Python, but when you write with it, there is still a lot of caveats that you have to deal with. Basically, when you are doing if-else, you will get problem because the compiler doesn't know by how much you have moved the register, the AP pointer, in each of the different arms. So you have to add additional code in order to say to the compilers that it's not aligned. So there is a lot of things that has been abstracted, but not enough, and you still have to understand and to care about what's underneath. So it was quite a good intermediate level of abstraction, but we wanted to go further to give people a really easy to use experience when writing Cairo code, but especially smart contract on Starknet. So that's the current syntax. It's now inspired by Rust, and that will be like what we are going to talk on this talk. I will go rapidly over like the syntax of the language. To do so, I will be using a lot of examples from the Cairo book. I think if you are interested, you should give it a look. It has been written by developers in the community. It's open source. You can contribute to it if you want. It's a nice resource. So one thing with the Cairo VM is that the memory is immutable. Well, it's required in order to be able to prove the execution. Once a value in memory is set, you cannot update it. But with Cairo 1, we give you like the abstraction that allow you to write code that feel mutable, even if it's actually not mutable. And a lot of things that have been developed and went into the architecture of Cairo 1 is about abstracting a lot over the virtual machine to give you a developer experience that feel like what you may be used to, but actually there is a lot of abstraction on top of this. Same thing, on the Cairo virtual machine, there is only one single type, which is the felt, the field element, but it's not really handy, so we come up with different types. You have the scalars, you have your bools, you are able to build a structure, custom types, and you even have enums. You can use those enums in the control flow to do some matches. You still have the if-else, but no, there is no this weird thing about the revocated references I told you about, which existed in the previous version of the language. And we now have loops, which is also a great improvement, because in Cairo 0 there was no loop, only recursion, which make it a bit specific to write. We also have generic for struct, for function, for trait also, because there is trait in the language. And there is a few default collection. The first one is an array, so it looks like a vector, but it's actually not one. Because of the non-mutable memory, we have to put some limitations, so you can only do two things with it. It's append at the end or pop from the front, but you cannot change values in the middle or do anything else. You can read it. So if you want data structure with mutable memories that feel mutable, you have to go with dictionaries. So it's not a dictionary at all if you look at what it does behind the scene, but it has the API of a dictionary. When you write code with it, you are able to define a key and give it a value and then later update this value. So it's feel good to use. We also implemented ownership because we are a big fan of Rust now. So each value is only owned by a variable. When this variable goes out of scope, the value is dropped. And you can pass values by reference to functions, so you don't have to return the ownership out of the function each time. And there is this really specific thing, which is like Cairo only, which is snapshot. It allows you to create a view, a snapshot of a value of a connection at a specific point during the execution of your program. So you will create this snapshot, then you can continue to change your value or like add element to your array, but the snapshot will not change at all, and you are able to pass it to functions that require non-mutable access to this kind of type. And it's really useful. It solves a lot of limitation of the language. And then you have Starknet, which is kind of a superset for Cairo. It had a ton of features that are related to writing smart contracts. So you have new libs, new macro, all these kind of things. But it will be, I think, the next step in your discovering of the language. And that's it for my talk. I still have some time, so I will add a few more ideas. So as we've seen, because you can compile different type of language to the Cairo VM, you can have different language with different trade-off. We saw that in the history of Cairo so far, we traded the fine-grained access that you have to the virtual machine against a lot of abstraction. It's important to mention that in Cairo 1, you also lost the ability to do hints, so you cannot do non-deterministic execution anymore. You can do it with a set of whitelisted syscall that contain non-deterministic execution, but you cannot add your own anymore. So this is really nice for Starknet, because we don't want users to be able to upload like any execution they wish onto the blockchain, onto our servers. But for computations that you want to do off-chain with your own prover, it may not be the best trade. You maybe want to be able to write some non-deterministic execution, and so far you will have to keep using Cairo 0 to do so. But I think in the future we may see like other language pop off that propose a different mix of those trade-offs between abstraction and fine-grained control over the virtual machine. And yeah, so that's my guess for the future. Is there any question? We still have 8 minutes.
Hi. I have a question regarding the Cairo 0 and the Cairo 1. And then as a Cairo 0, as a low language, we know that there is a now Cairo 1, right? And the more expressive language addition with the Sierra. And then what is the kind of like defining factors that separates those two languages? Like, let's say if the Cairo VM extends its use cases beyond Starknet, maybe in Cosmos, maybe in Polkadot, and how does it mean for the application builders on those ecosystems that can see in those two?
Question is, what's the defining factor between Cairo 0 and Cairo 1?
Yep.
Yeah. So the huge thing with Cairo 1 that justifies its development is that you cannot write code that is not provable. With Cairo 0, if you write code and there is an assertion that fails, it will panic and you won't be able to generate any proof for this execution, which is a problem in the context of Starknet, because we want to be able to charge users that send transactions that we fail. And if we cannot prove a failed transaction, we cannot charge them for this. So in Cairo 1, we introduce an intermediate representation during the compilation, which is Sierra, and that main purpose is to make sure that everything that compiled to Sierra will result into a provable execution of the Cairo virtual machine. So that's the main difference, and then it's trade-off in terms of abstraction. So you will sacrifice a bit of performance, you will have some overhead, in comparison to Cairo 0 and to Cairo assembly specifically.
All right, thank you.
So suppose that I want to prove computations in Rust. So I will have to write a compiler, right, from Rust to Cairo. 1, and 2, would I have a guarantee that it will give proofs for any computations in Rust?
What's the second question? A guarantee that?
So once I have a compiler from Rust to Cairo, then the second question is, does that guarantee that I can generate proofs for any Rust computations?
Well, I'm not sure you can. We tried a little bit this way internally to be able to directly write code in another language and prove this computation. And we gave up on this. Rather, we went with the creation of language that are much more limited and that allow you to write code that makes sense from the point of view of the Cairo virtual machine. because when you write Rust, there is a ton of things that make sense only in the architecture, in the context of the x86 architecture or classical computer like this. Here we have like a specific hardware. Even if it's a virtual machine, it could be like its own processor at some point, and it only have 2 registers, different memory zones. Like it's really different in its nature, in the constraints. The memory is non-mutable. So I guess we could imagine some kind of library framework that you can write in Rust and that will abstract that part, but it's basically making a language library in Rust. So,
But
far,
since it is Turing complete, right, I should be able to convert any program in any language to Cairo.
well, I'm
In theory,
not sure.
in theory.
Maybe, but I have no idea.
Thank you. Possible to work with variable-sized loops, for example. I don't know the exact number of structs I want to process. In one case, I need to create 10 structs, in other 20 structs, etc. With loops with variable length, yeah, it's a problem, for example, for CIRCOM.
Sorry, I don't get the question. It's
Is it possible to write a program who runs a loop over a pack of structures, but the size of this loop depends on the previous computation?
Oh, so the way you pass like input to the program is through hint, non-deterministic computation. So you will create like a variable, and then with some non-deterministic computation, you will read your desired input from the local file system or the command line, and you will put it into the Cairo execution environment. So yeah, you can pass arguments that are any size you want.
Okay, thank you.
You're welcome. Are we good? No more question?
Okay, let's say hi to Garbit Gold from Electron.
Hello. Yeah. Hi, everyone. So this is Garvit. I'm the founder and CEO at Electron Labs. And today I'm going to present some of the stuff that we've been working on. And so we've all heard about ZK light clients and ZK bridges. Today we're going to present the same concept in a different light from a very different perspective and focus a lot more on the use cases side of things as opposed to the technology, what has been discussed in the recent couple of weeks and months. So Electron is building what we like to call as ZK compression of consensus protocols. So what that means is that we are essentially building a computation compression engine that allows you to generate these validity proofs of consensus protocols. What that means is that, so if you talk about consensus protocols such as Ethereum or Solana, they usually require you to rent out a large machine on AWS and actually paying for a decent amount of rent to actually run these machines. And these machines are quite incredibly hard to actually run on mobile phones and definitely not on smart contracts. What we do is actually we go ahead and generate a ZK proof for these consensus protocols, which makes it easy to verify at the verifiers end. So you don't really have to run these consensus nodes at your end, and you can actually verify them quite cheaply. To give you a bit more context on what that actually means, so imagine you actually wanted to run the Ethereum consensus node as a Solana smart contract. We'll get into why you would want to do that, but let's assume you want to do that. The challenge is that even though Solana is really scalable, it's supposed to be the most scalable chain out there. Even in that case, the Ethereum consensus node is so heavy that you can't run it as a Solana smart contract. Forget about running any consensus node of any blockchain or on the smart contract layer of any blockchain. It's just not possible today. So in order to solve this problem, we actually, as I discussed, we actually run these ZK provers, which create proofs of validity proofs of the consensus execution of the Ethereum consensus node, and that allows you to So what you have to do is that all the computation requirements are essentially offloaded off-chain, and you can simply run a simple ZK light client node on Solana, which can validate, which can essentially validate all the proofs coming from the prover, and you can basically verify transactions quite cheaply. If you go a bit into why you would want to do that, so I think one of the first obvious use cases is that ultra-secure cross-chain transactions. Any transaction that is originating on Ethereum can actually be verified with very high level of security on the Solana side, and basically you don't have to rely on any third-party security models. So that's kind of a high-level overview of what we've been building. As I said, this talk is mostly going to be focused on use cases of this technology, not the technology itself. We'll probably spend some time on the technical side towards the later half. So one by one in the rest of the presentation, I'm going to be looking at different use cases, and I'm going to be presenting each one of them that are enabled by this technology. So let's get started. So the first use case I would like to present today is the one that, that's the closest to my heart, is that if you are an alt L1, if you're running an L1, you can actually start renting security from the Ethereum blockchain using our technology. So what does this even mean? It means that if you're an alt L1, you can start essentially receiving proof of stake security from Ethereum restakers and pay them token rewards in return. This model essentially allows you to continue to operate your alt L1 as it was operating before, just like you've been operating for the past couple of years. And this actually presents a viable and a gradual path towards your alt L1 becoming an Ethereum Validium without giving up too much control, without making a drastic change to the infrastructure, and without giving up your sovereignty. Going a bit deeper into how this actually works under the hood. So we'll spend some time on this slide. So let's say as an alt L1 you wanted to rent security. So first of all, the first step is actually ETH stakers locking up some money on the staking contract. This could be, let's say this is ETH holders who are locking up some money. And by locking up this money, they're essentially intimating to everyone else that they are interested in providing security to this alt L1. And they are essentially putting up their collateral for slashing conditions for any consensus, any malicious action in the consensus execution by the alt N1 validators. At the same time, we also run the ZK consensus node of the alt L1 on the Ethereum smart contract. So what this allows us to do is that on Ethereum, we can completely track what is the action being taken up by these alt L1 validators. So for example, are they creating valid blocks? If they are creating valid blocks, you can record the same information on the ZK consensus node and actually pay out rewards to the staking contract. If they're conducting any malicious activity, that itself can be tracked on the Ethereum blockchain in a completely trustless fashion, allowing you to again slash the stakers who have provided money to the staking contract. Of course, in the middle, we have the ZK prover of ETH consensus running, powered by the Electron infrastructure that will allow you to create these validity proofs of consensus of or the alt L1. So that's kind of the first half of how you track the consensus on Ethereum. On the flip side, we also would like to maintain the Ethereum consensus on all the alt L1. This allows us to actually track how much money has been locked up by the staking ETH stakers on the Ethereum side, which actually informs the alt L1 consensus that it can update the voting power of the alt L1 validators, and this kind of becomes important for distributing rewards as well. So you can actually track the full history of additional validation delegations that have been received on the staking contract for the alt L1 validators. So going a bit deeper into the architecture itself, so when it comes to the staking contract, so we can actually invite a wide variety of token holders to actually lock up their money. So we can have plain vanilla ETH holders. You can also have staking derivatives, liquid staking derivatives. We can actually lock up any kind of ERC20 token. We can lock up stable coins, USDC. Even L2 coins can be locked up to actually provide security to any alt L1. So if you're an L2, you can actually run another chain which is then secured by the governance token of your rollup. You can do that. And of course, you don't need to set up your complete infrastructure from scratch. We can simply reuse the work that has been done by EigenLayer here, and so that we actually don't have to go and build our own supply of security, to power this engine. So we can simply plug into that. If you abstract away the tech, what's essentially happening here at a very high level is that these alt N1 validators have essentially received delegations in the form of ETH in a cross-chain setting, and they're paying out rewards in the native form. So imagine you stake your contract, you stake your ETH on Ethereum, and then you're basically earning Solana token rewards on top of that against providing validation services. This is like very similar to how proof of stake works in the first place, but this is like in a cross-chain setting. Of course, you can issue a liquid staking token against the Ethereum that has been staked on your chain. And this liquid staking token can be issued on your alt L1 and can start chasing liquidity positions across DeFi protocols. Just want to mention here that this does not require running any additional infrastructure. Neither the stakers and nor the validators have to run any additional infrastructure for you to actually enable this to happen. So this increases your validator profitability since you're receiving more delegations without any increase in the infrastructure itself. Since Ethereum is a slightly more premium asset, you can actually get away with paying a lower amount of token emissions. Like Ethereum as a premium asset expects a lower yield as compared to, let's say if you were running your own chain, where you're actually staking your native token to provide security, to your chain. And this token can basically fluctuate over time. As a result, the validators will essentially demand a much higher yield because of the fact that your token is, quite volatile. So you can actually get ETH, which is a more stable asset, to provide security to your chain. As a result, you pay lower APY on your security. So basically, you can get, for the same dollar value of security, you have to pay lower token emissions to secure your chain, which effectively reduces the overall operating cost of your network. And yeah, basically just improves your overall tokenomics. Yeah. And yeah, there's additional benefit, of course, like Ethereum alignment is one of the biggest advantages here. As we've seen that increasingly more and more chains have been looking to attract Ethereum users and liquidity to their chain, and in return for the scalability services that they provide. And you can actually market your product, shell your product in the Ethereum ecosystem quite seamlessly, and actually even attract liquidity just by securing your chain. Yeah. And something I just want to reiterate here, this is a question we often get from people who are actually looking to rent security, that the first question we get is that if you're an ETH staker, are you required to run an additional node? Absolutely no. If you're an ETH staker and you want to rent security using this model, all you have to do is essentially make a transaction using your MetaMask, lock up the money just like you do it with any other staking protocol, any other DeFi protocol, and that's it. Like you don't have to run any additional infrastructure. You simply interact with the UI and send a transaction using MetaMask. That's it. You don't have to run any additional nodes. And just to talk a bit about adoption, like this can actually be done on Cosmos SDK today, right? We are actually working with a couple of Cosmos SDK-based chains on this right now. So Cosmos SDK is this modular architecture which allows you to add these additional modules, which will allow you to rent security quite seamlessly. With a little bit of that, this can actually be extended to other chains as well, like Solana or any other chain for that matter that may be interested in renting security. And but yeah, like Cosmos SDK is kind of the place to start here. It's probably the lowest hanging fruit, and once people see it working for these kind of L1s, it probably becomes interesting for the other chains as well. Yeah, so like, imagine, like, again, talking about adoption, like imagine, Canto and Celo, both chains recently announced that they are actually looking to transition from an L1 architecture to a roll-up-based architecture. Now, imagine like what must have happened at the leadership, level within these chains. Like this is actually a pretty drastic measure. You're giving up your entire infrastructure that you've been running for quite a while. You're giving up your sovereignty. You're giving up your whole community, the way it has been organized around your sort of infrastructure. Like you're giving up your validators as well. Your validators are going to be pissed off. And you're having to suddenly transition to an infrastructure which is not as well tested out as setting up your own L1. And so the idea being that the transition to an Ethereum rollup or Validium is actually quite complicated. It's actually a big decision right now because you have to give up this infrastructure and set up a new one. The model we are proposing here actually provides a transition, a very gradual and a slow transition to Ethereum, to becoming an Ethereum rollup or Validium, taking a gradual process and not giving up your sovereignty or control, in the entire process. So I believe people, more and more chains will increasingly start following this model as they transition to an Ethereum rollup architecture from an L1. Yeah, so that's the use case I just wanted to present. This is the first one. There are more use cases to come here. But yeah, just to summarize, we are essentially enabling alt L1s to essentially rent security from Ethereum. So moving on to more use cases. Yeah, so, another use case I would like to present is again powered by this whole concept of ZK compression of consensus protocol. So we recently saw NIA make this announcement that they are actually looking to provide validation services, data validation and data availability services to the Ethereum rollups. And we expect that more and more chains will soon follow suit. That it just makes sense because these chains have a lot of block space that is free. They have a lot of cheap block space. And all you need to do essentially is basically run a ZK consensus node on Ethereum. So whenever basically a rollup that is operating is posting data, rather than posting data to a DAC, data availability committee, or directly on Ethereum and incurring high gas costs, you can actually publish this data to your alt L1. And from there on, we actually generate this ZK light client proof of the same, which can then be submitted back to the Ethereum contract for checking that the data has indeed been published. At the same time, this chain could actually be renting security from Ethereum as well. So you're basically getting a chain that is renting security from Ethereum and then is also posting light client commitments to Ethereum against any data that has been posted for that. This is like a very high security model while keeping the gas costs very low, right, in terms of data availability services. Right, and another use case I would like to talk about here is, so like, for example, if we talk about L2 to L2 bridging, we're probably going a bit fast here, like there are lots of use cases to present, but yeah, I'll continue to move forward on the same pace. So yeah, and so like, right now, like if you talk about L2 to L2 bridging, in L2 to L2 bridging, we're mostly using centralized services right now, which are again, come with their own set of problems. And one of the ways that L2s are trying to get around that problem is actually reading the Ethereum state directly inside the L2. This is actually a great technique, but it has some problems that it actually makes your overall infrastructure a bit more bloated. And it also, like, imagine like if these rollups wanted to sort of start interacting with other L1s as well going forward, maybe settle on them or maybe have a bridge with them. The problem is the moment, whenever this rollup wants to interact with another network, it would have to run the state, would have to have a pre-compile for the state of that chain inside the, inside the, the core infrastructure of your L2, which essentially makes it inflexible and it overall increases your cost as well. The model that we are proposing here will essentially allow you to run the Ethereum. So basically, this will shift the, the fact that you need to read the Ethereum state. It will shift that from a requirement of the core infrastructure to the smart contract layer. So you can actually read the Ethereum ZK consensus inside the L2 network. And from there on, you can essentially read the state of any other rollup, since rollups commit to Ethereum anyways. So what this allows us to actually build is, if you wanted to do a completely trustless transaction, you can actually go from L2 to L2 directly using this model. While if you don't use this model and you wanted to do a trustless transaction, you have to first of all withdraw your assets back to Ethereum, and then from there on, you make a transaction to the second L2, which of course means you have to do a mainnet transaction, which increases your cost significantly. So this is a trustless way and a cheap way to conduct these transactions. What this unlocks essentially is that you have lots of L2s that are coming online, and the cost of switching these L2s is going to be pretty high. And what this allows us to do is that it reduces the cost of switching rollups and enables app-specific rollups to exist, because the cost of switching rollups would be, like, you don't have to do a mainnet transaction anymore. So you can simply switch to a rollup at L2 cost, making it really, really cheap to essentially switch rollups, yeah. And talking a bit more, yeah. Can you tell me how much time is left? Okay, thank you. Yeah. So presenting another use case. So again, like, this is something that people have experimented in the past, and it has never worked, right? So for example, we've often seen that people have demanded that wallets should essentially run a light node inside, like, inside a mobile phone or a browser. But that has actually never happened. And the reason for that is because light nodes, Ethereum light node, or any other light node for that matter, even though they're called light nodes, they're actually not so light. And if you were to actually run it on your mobile phone, it would be constantly downloading blocks every couple of seconds, which makes it incredibly, even though it's supposed to be right, it's still you're downloading a lot of data, you're still processing a lot of information to actually run this infrastructure, which has made running light nodes on the client side quite impractical. Nobody does that, right? Ethereum phone, sorry, Ethereum OS, these guys are working on this. They actually run the light node on the operating system layer as well. I mean, yeah, like they can essentially use our technology to run a ZK consensus node inside the phone, which means you only have to download, a couple of bytes, a couple of 100 bytes of data whenever you actually need to sync to the blockchain. Like, you don't have to do it continuously. You can switch off your phone for a couple of weeks, come back online, download a couple of 100 bytes of data, and that's it. You sync to the Ethereum blockchain, and you can start sending transactions, receiving transactions, and start interacting with the chain as you see fit. Yeah. So it's basically, again, maintaining the same security model while at the same time reducing the data requirements, network requirements, and computational requirements quite significantly using this model. Yep. And yeah, at this point, I think I would like to, that's kind of the use cases I wanted to present. And just going back a bit, I just want to summarize the use cases that we've discussed. The first one is obviously renting security for all L1s from Ethereum, starting with Cosmos. Enabling your chain, which is on alt L1, to essentially provide data availability services to Ethereum rollups. Ultra-secure cross L2 communications, enabling micro rollups to exist, and basically reducing the cost of these rollups quite significantly, the cost of switching rollups quite significantly. And of course, the last one we discussed, which is verifiable RBCs and client-side light clients. So that's the use cases I wanted to present. I think at this point, we can move to a bit of technical architecture and what is the stage of Electron, how much of this has actually been shipped so far. These are all future use cases. So let's actually try to understand where we are at today. So like first of all, we are already live across 3 different networks, Cosmos, Near, and Ethereum. So of course, with Ethereum, we're using the Altair sync committee right now. Since ZK proving the full Ethereum consensus is quite hard. Although that's something that we have started to explore around a bit, and I think we do have a roadmap in mind that I'll present on that going forward. And so yeah, like we have the Ethereum ZK light client powered by Altair already running as a Near and Cosmos smart contract, written in Rust, again powered by the Electron's ZK infrastructure. Secondly, we have already built this out for the Cosmos and the Near ZK light clients as well. This is deployed on Ethereum today. So again, so this is already live, by the way, live deployed on mainnet, actually powering transactions. So we actually operate a bridge between Ethereum and Near right now. And this bridge has no multi-sig operators behind the scenes. Like no one actually securing these transactions. It's just the light client that is doing it. All transactions going from Ethereum to Near to and fro between these 2 chains are actually secured by the ZK light client of each of them running on the other side. And yeah, right now we only kind of do the, so if you talk about consensus, it's mostly essentially validator signatures. So we have done ZK compression for validator signatures, and for the rest of the consensus process, like voting power and tracking all of that, that part is also coming soon this year. And we plan to like, achieve a 60x reduction in gas fees. We already achieved 30x reduction, but with a couple of upgrades, this will come down to 60x reduction in gas fees, as opposed to if you're running the full consensus on chain. And yeah, I think just one last thing I wanted to present here. So as I was talking about, the Ethereum Altair light client is kind of, it doesn't really borrow any Ethereum security right now, because like can't slash validators on chain. If the Ethereum or sync committee members basically conduct any, malicious activity, you can't really slash them. So that's something we're essentially trying to fix by ZK proving the full beacon consensus. Basically, you post a single ZK proof on Ethereum or any other, smart contract environment. You add a single Merkle commitment of that, and these 2 information basically attest to the validity of the entire Ethereum blockchain. So you could like post a single commitment for the entire, for entire single block, or you could actually do this for the entire Ethereum blockchain from Genesis. So this is again something we're working on. Probably, quite a while it will take to build this, but yeah, definitely this is something we're going to see very soon, that will unlock all these use cases that we discussed just before. And yeah, I mean, we essentially use a combination of Starkey, Plonky 2, and Groth 16 to run this entire infrastructure. And yeah, I think I won't go too deep into the technical parts right now, but yeah, I think that's, yeah. So yeah, any questions, like, would love to. Yeah.
Are you familiar with Mina, and can you compare how they do it, how you do it? Thank you.
Yeah, definitely. So like Mina is basically, a lot of these ideas are actually borrowing from Mina protocol itself, because Mina has already actually achieved this. They are kind of ZK compressing their entire consensus. I think one of the biggest differences here is that Mina was actually able to build their consensus and hashing schemes and all the cryptographic primitives that they were using optimized for ZK proving, right? The biggest difference here is that the consensus processes here were given to us, and then we had to fit the ZK engine to work with that. So a lot of cryptographic schemes we are using are actually very, very ZK unfriendly, like they're kind of hard to work with, essentially. Yep. Yep. Any other questions?
Okay, thank you. Next will be Joanna Zeng from Alio, but let's take a short break, maybe 10 minutes break, so you can go to bar and have a coffee, but please come back because talks will continue, okay? Just a little break.
I see.
She just put this here because we are having an updated version here, and we don't want to confuse the speaker. Sorry. No problem. If the speaker's not coming, can you do the presentation? No idea.
The next one is ready.
Oh, so you're actually ready for more now? That's good. Maybe we can just do like this. And then you know how to do it. Okay. It's more beautiful. Let's see. Kullandığı zaman bu da akıcı. Bu ilerleyecek. He connected the clicker, so you can just use this one as well with the new slide.
Both.
Yeah, exactly.
This controls both now.
Abi basında sadece yenisi harekete çıktı mı eskisi? Burası da orası da gidiyor. Yani bunu kullandığı zaman burada akıcı. Ya da çıkıp buraya kapatıp açması lazım. Ha, şimdi sadece orası akıyor. Ha tamam anladım. Anladın mı? Ya what will move. But we can just readjust it once we're done with geldiği zaman bir sonraki konuşma. Buradan kullanılacağı zaman gelsin şuna bas. Okay, only A.
A is the computer.
The computer, yeah.
And B is that side.
Oh, another system.
Okay. A computer.
Exactly.
Okay. So
Ben şimdi kapalı bırakıyorum. Açık bıraksak sıkıntı olur mu abi?
okay. When A is off, then that is in charge.
No. It's just we can change it manually there. So all you have to do is click on A. That's it.
And then it's gonna work.
Yeah, exactly. Ne yaptın? Aşağıya gönder, silahına gönder. If bu open, see, it will be automatically synchronized.
Okay. So the
Ya
thing
sadece
is,
gelip şunu tıklasın. Yeah, all you have to do is just click A. That's it.
Yeah.
Basically.
the speaker, Aleo, this one, who we have on those notes, he's late. So just in case he does not show up, then we are prepared for this next one.
You mean the
just
switching slides? The PowerPoint?
no. Aleo, he has his slide there.
Yep.
He's late. That's why we have a break. If something happens, he does not come. We are ready to use these.
Like these, you mean like a new slide or
No,
like what's
no,
these?
next person.
Ben anladım. Şöyle diyor galiba.
If he does not come.
Bir önceki konuşmacı burada bırakırsa siz oradan gelen konuşmacının ismini alın diyor. True?
Imagine you are Aleo.
Okay, yeah,
I am Zama. You are late right now.
sure.
You broke your leg. You say, I'm not coming. I am Zama. I come. I present.
Okay, then but what is the difference? Like, what do we have to change? I don't
Oh.
understand that exactly.
He will probably come.
Okay.
And we are using that and then this.
But what's I don't understand what's like. Are we using that? This is
Okay. Aleo has slides there.
That's what I meant. Like
Yes.
the new slide and the first slide and
Yes.
the second slide, right? So if Aleo does not show up,
Yeah. Then
we will switch to the first one, first slide.
Okay, AMD here to save the day. So this is a spoiler, don't watch. Here, well, Hamid, thank you for this. I know it's hard. Well, thank you and welcome. Please. Yeah. A big applause for Hamid, who is saving the day. Forward, backward, light in the pointer. There's a pointer. Forward, backward. Thank you.
Hi, everybody. So I should probably stay here. My name is Hamid. I'm the Director of Product at Embedded and Computing and Embedded Group at AMD. My focus is mostly on Web3 products, fintech products, and kind of broader data center products. And for today, I want to talk about hardware acceleration broadly for ZK-proof generation. And that's a topic that has a lot of facets into it. I'm going to try to keep it high level broadly and kind of demystify some of the misconceptions, hopefully, about hardware acceleration. So broadly speaking, when we talk about hardware acceleration, typically that refers to versus a CPU. So you have a program running on a CPU, and either you want to run it faster or you want to run it more efficiently, and then you are going to start to use some dedicated hardware to achieve that goal. So there are different types of hardware you can use, right? You can use off-the-shelf hardware, or you can design your own hardware, basically, right? Off-the-shelf hardware typically, are GPUs, FPGAs, and those are type of devices that you can program. Now, in case of GPU, you program in software. In case of FPGA, you program in hardware. But in either cases, this is something you go to a company, Intel, AMD, NVIDIA, you buy a GPU, you buy an FPGA, and you program them to run your operations faster or more efficiently. And then if you don't want to do that, if you really want to make it cheaper, even more efficient, then you design your own hardware. And then in that case, you are going to design your own device, whether it's an ASIC, which is application specific, or you do an eASIC. An eASIC, more or less, is very similar to ASIC. If you think about how semiconductors are designed, you have different layers. You have the base layers, which is the core logic, and then you have the interconnects. Those are the metal layers. And in case of eASICs, basically, you have the core, and then you're going to design your interconnect. And then you're going to have a tape out. Still, you are designing your own hardware. It's a little bit cheaper, but you're not going to have as much flexibility as where you're designing a full ASIC. So these are your choices, basically, more or less, when it comes to hardware acceleration, the type of hardware that we are talking about. Now, each of these pieces of hardware have advantages, disadvantages. You have to decide what piece makes the most sense. And even before that, you have to decide if hardware acceleration is needed for your problem. Because for a lot of problems, you might not even need hardware acceleration. But if you determine that running a program faster, more efficiently, that's becoming your bottleneck, then you're going to consider hardware acceleration. Now, if you look at the different type of product, and for simplicity, I'm not going to talk about eASIC. If you think about GPUs versus FPGAs versus ASIC, and you hear a lot of that, if you go on LinkedIn or on Twitter, and people talk about these pieces of hardware, and I want to kind of explain what the differences are between these different pieces of hardware, right? So in terms of development cost, I would say GPUs and FPGAs are one category, with GPUs being the cheapest, because you basically buy you can buy a GPU of any store, and you can program it. You just have to learn CUDA. It's fairly easier than other type of hardware acceleration, right? And then you have FPGAs. So again, programmable, but you have to know hardware languages. So you have to know VHDL, Verilog. You are programming the device at the gate level. So it requires a little bit more knowledge. It costs a little bit more because the teams that know hardware developer, those are kind of more difficult to put together. And the number of people that know hardware programming is more limited, right? And then you have ASICs, which basically order of magnitude more expensive, right? And also non-programmable. Now, in terms of performance, and there are a lot of caveats here I want to point out to kind of demystify some of the misconceptions here. So both ASICs and FPGAs, you are designing at the gate level. So for a specific problem, you can get it very close to the optimal performance. GPUs are more fixed architecture, so performance is still good, but might not be as good, unless the problem you're optimizing for is especially suited for the GPU architecture. In the case of ZK proof generation, for example, the MSM primitives are particularly good, suited for the GPU architecture. So if you are solving a problem that is particularly good for a GPU architecture, it could outperform FPGAs, right? But broadly speaking, when you are designing in FPGAs, because you are designing at the gate level, you can get very close to performance of an ASIC. Now, if you just look at this description, you might say, okay, ASICs, 10 times more expensive. FPGAs, you can get very close to the performance of an ASIC. So everybody should use FPGAs all the time, right? But that's not the case. The main drawback of the FPGA is the silicon area you are going to use to implement a logic, right? It's the device cost, right? Not the development cost. So you have to differentiate between those two different costs, right? So basically, if I want to implement a circuit on an ASIC and it costs me $1 worth of silicon, implementing the same thing on an FPGA is going to probably cost you $10, the cost of the device itself, right? So yes, I can pick up an FPGA off the shelf. I can do my development. Development cost compared to an ASIC is significantly lower. But then if you want to mass produce in quantities, ASICs is going to be order of magnitude cheaper, right? So those are kind of different level of compromise that you have to think about when you think about hardware acceleration. Typically, what we see is a lot of people start on CPUs. It's just, it's basic. Everybody can run programs on CPUs, high level. And then you migrate to a GPU. You need to learn CUDA in case of NVIDIA. In case of AMD, we have ROCm. And then from there, you can migrate to an FPGA. And then there is a big chasm to cross if you want to move to an ASIC. So when it comes to hardware acceleration for these cryptographic primitives, hardware acceleration is not a new subject. People have been using hardware acceleration for the past 20, 30 years. Think about the early days of the internet and using the public key cryptography, the AES. And early on, it was very actually compute intense until those blocks got hardened and got integrated within every CPU block today, right? So you don't even think about it. And then early days of Bitcoin, mining, a lot of that, solving the hashing algorithm using hardware acceleration, and obviously now it's all has gone ASIC, right? And now you have FHM and ZKP, and people are trying to use hardware acceleration to create more efficient proof generation systems. Now, if you look at hardware acceleration for ZKP in general, there are different things to keep in mind. The first thing is, what is your goal for hardware acceleration, right? So not all hardware accelerations are the same, right? So you might say, I need hardware acceleration because I need to generate more proofs per second. Is that your goal? Or your goal might be generating the proof faster. So you might not be as concerned with how many proofs you are generating per second per se, but you say, I want to be able to generate a proof as quickly as possible, right? So latency might be. And depending on, if you're using it for, a bridging application, for example, or if it's a roll-up application, you might have different constraints. Or you might not care about either. Frankly, you might say, I don't care how fast I generate it. I don't care how many proofs per second I generate as much. I just want to make it as cheap as possible. So dollar per proof, that's what you care about, right? Or you might care about power efficiency. And these two, sometimes people think dollar per proof and watt per proof is the same thing. Not necessarily. Because you might be in a situation that you might not care about the money as much, but you are capacity constrained. So if you have a facility somewhere, you have access to fixed amount of electricity, it's not the issue that you can go buy more electricity. It's hydro, for example. You cannot generate more water, right? So you say, okay, how many proof I can generate with that amount of electricity? So then watt per proof becomes important, right? Now, again, in case of KZP, ZKP, there are two main primitives, right, that we are talking about accelerating with, whether FPGAs or GPUs or ASIC. One is MSM, which is multi-scalar multiplications, which is basically a dot product on an elliptical curve. And as I said, the MSM problems are uniquely actually good on GPUs. We had some competition through Z-Prize that ran last year, and some of the results coming out of the GPU team were very impressive, as a matter of fact. And then you have the NTT, which is a fast Fourier transform on a finite field. And the NTTs typically are a little bit more unstructured, and we see that a lot of impressive results on FPGAs, as a matter of fact. And then depending on, and this is a very nice table put together by Amber, depending on what kind of polynomial commitment scheme you are using, depending on what system you have, the ratio of MSM to NTT changes, right? So if you have a system that's kind of a more Fry-based, like a Plunky 2, for example, right? You see that the share of the NTT is higher, right? And then if you have a system that is more snark-based, like a KZG, Marlin, for example, you see that most of it is dominated by MSM. And then depending on what that choice of primitive ratio is, then you can decide what type of hardware acceleration is best suited for your problem, right? Now, one other piece of consideration you really have to keep in mind is, so you have to really think about your overall problem holistically. Right? Assume that you have a proof system, and this is just for demo purposes. The ratios might be different. I'm just putting something just to make a point here, really. So assume you have a proof system that is 40% MSM, 40% NTT, just for simplicity's sake, and there are 20% overhead. How you move data between different engines from the host, right? And you say you want to accelerate this using hardware acceleration. Say somebody in your team shows up and says, you know what, I found a way to accelerate NTT 1,000,000 times, right? And again, it's just to bring a point, to prove a point here. And then if you do that, but you don't accelerate the rest of the problem, okay, so the NTT piece goes away, but still you have 60% that, is you're gonna accelerate your system not even 2 times, right? 1.6 times. So you say you create a system and then you eliminate the compute load for both NTT and MSM in this case. Still, you're only accelerating by 5 times, right? So the primitives, you're accelerating 1,000,000 times, but overall, you're only accelerating the problem by 5 times. Even if the ratio of the other piece was 10%, right? If you eliminate NTT and MSM, at most, you're going to accelerate 10 times. Irrespective of how much you're accelerating NTT and MSM. So what to do, right? The way to think about hardware acceleration, you have to think about your overall proof system. You have to think about how memory access is structured, how you're moving the data, how you can accelerate the complete proof generation system. And it could be that you might need to create a system that has a mixture of FPGAs and GPUs, and also pay close attention to all those pieces. Maybe you need a custom memory hierarchy. Maybe you need a certain cross point. Maybe the way you talk to a host. You have to see where the bottlenecks are and eliminate that. So when you are thinking about creating that system, don't just focus on a primitive and just making that primitive 1,000,000 times better, because that might not necessarily help you. So couple of other things to think about when you think about hardware acceleration. What does it mean when it comes to actual implementation, right? So the first piece is you want to do parallel processing, right? You want to divide your problem in small pieces, run them at the same time. That's what GPUs does. Everybody is familiar with it. The second piece is pipelining. So if you look at your silicon, when you run a problem on it, a lot of time you see that only a small portion of the silicon is active, right? So you have to have a pipeline where we kind of call it there is no dark silicon. So as close to 100% of the silicon is utilized. So that's very, very important, right? And then kind of building onto that is memory access. So you don't want your problem to wait for memory, for data from the memory. So how you write your memory, your data to memory, how you read it from memory, how you can use cache memory, how you can use, in case of FPGAs, we have internal SRAM memory, BRAM memory, B block, how you are kind of dividing the problem in different pieces so that the memory is used really efficiently is very, very important. And also how you implement the problem itself, right? If you have different type of data field, how your hardware is suited for that specific data field is going to be very important, how efficiently you implement your problem. And then the last one is overclocking, how fast you can run the silicon, right? So I want to just double click on FPGA for a second, because FPGA is one of those pieces of hardware that people are kind of hear about it, but they don't know what it is as much. So basically, at the very kind of high-level basic element of an FPGA, you have millions of logic cells. So what are these logic cells? These are tiny truth tables, basically. And then on top of that, you have an interconnect that connects these logic cells, and those are programmable. So you can design how these logic cells are connected to each other. And then on top of that, you have different blocks, different type of resources you have access to. You have DSP blocks. You have, these are tiny math engines, basically. You have AI engines, which are bigger math engines in kind of simple terms. And some FPGAs, you have access to high bandwidth memory. And then different type of FPGAs have different combination of resources. So when you're thinking about hardware acceleration, even just in the frame of FPGAs, you have to think about what FPGAs suits your problem. So you have to really think about some of these decisions, because it really has major impact on how much you're accelerating. You read in kind of a lot of articles that different people use different products with totally different results, and these are not trivial matters. It could have orders of magnitude impact on how much you can accelerate your problem. So just a little bit of kind of more specific on FPGAs and what we have made available to the community. There are 2 FPGA cards that we have made available through zPrice to people who want to use FPGAs for hardware acceleration. One is called U55C. U55C gives you access to 1.3 million lots. So you have almost over 1 million tiny truth tables, right, that you can program. And then you have access to 9,000 small DSP engines, so those are math engines. And then you get 16 gigabyte of high bandwidth memory, right? So that's what you get on a U55C. And then on a U250, you get 1.7 million lots of logic cells, 12,000 DSP engines, and 64 gigabyte of DDR. So these different combination of resources, each of these cards might be suited for a different type of problem, right? I don't have a lot of time, so I'm going to go through this a little bit more quickly. So if any of you, got interested in, getting into the world of hardware acceleration, a very good place to start is looking at the content that was created last year by zPrice. So zPrice, the competition running annually, was ran last year, and AMD was a technology sponsor. And really, the goal of zPrice is to advance cryptography for zero knowledge. The interesting thing about zPrice is all the entries, all the result of the competition is open sourced and available online, so you can scan that QR code, and you can go to GitHub and see what people have done to accelerate some of these primitives, both on GPUs and FPGAs. The event is running again this year in 2023. AMD is again as a technology sponsor, and we are looking to see what other advances we'll see this year, but definitely this is a good place to start. And go through some of the entries and get started. Obviously, if you are interested, you can participate in Z-Prize as well and get access to our FPGAs and GPUs and play with some of these. And these are some of the references if you're interested to see kind of more details on some of the material I presented. And I'm just going to leave it here in case people are taking pictures.
About the speed up based on how much you improve MSMs. Is there an assumption you're making at the number of MSMs and entities and the sequence in which that is there when you make that calculation? I'm really confused what your assumption was.
So the chart that I showed, the 20%, 40%, 40%, no, just to bring a point. So it might be 50%, 40%, 90%, 10%.
You said if you have a 10 to the power 6 improvement in entities, you get 1.6 times improvement in overall. That's a very strong assumptions being made underlying, and it's confusing for most of the people in here. So
yeah. So basically, the point I was trying to make is if the entity piece even goes away, you still have 20% and 40%, right? So even if you accelerate it infinite, right? So it's still the overall problem, you're not accelerating it much. So that's the point I'm really trying to make is when you think about hardware acceleration, don't just think about a single primitive, think about the complete application. Because the bottleneck might be somewhere else and you might be wasting your resources somewhere else, right?
Thank you. Okay, thank you a lot. Now we have Sama. Not sure where we are. Here, Morten Dahl, right? Welcome, please welcome. Sama, can we have the... Okay, thanks, welcome.
Hey everyone, and thank you for inviting us here to speak. Let me just see, I'm supposed to have a clicker. Oh, I'll just use the laptop. Okay, so this presentation is about FHE, fully homomorphic encryption, which you may wonder what does that have to do with CK, and I'll touch on that towards the end, but you'll see there is quite some similarities and synergies between the two. All right. Thank you. Okay, so first off, Sama is a company focusing on homomorphic encryption. We're building a homomorphic encryption library, TF-EGRS, which is available open source, Rust-based. On top of this library, we're building two solutions. One is blockchain, the other one is AI. When I say we're building blockchain, I should mention that we're not actually building our own blockchain. We're rather providing the components, as I'll dig into the details of in a bit, for people that want to build a blockchain on encrypted data. Yeah, so I won't go too much into this, but we have a relatively large research department focusing on this both on the theoretical side of FHE, but also on the implementation side. We're building or implementing towards CPUs, GPUs, have a small FPGA and ASICs teams as well. I don't think we need to say much here, but the motivation behind this is that data on the blockchain is inherently public, and that creates some issues. But if we can encrypt this data, then we can get around some of these things. Theft could be one thing that people can see your data, can figure out your account balance and so on. You might not be comfortable with people seeing all this data and what they can use it for. And we also have, like MEV, some concrete issues where people take advantage of the data because it's publicly available. So what fully homomorphic encryption can do intuitively is that you can encrypt data, and then you can have someone else compute on this data while it remains encrypted. So without being able to decrypt the data, you can still manipulate the ciphertext in such a way that it makes a meaningful computation. which then can be sent back to someone who has the decryption key who can then decrypt the results. So you can kind of outsource the computation, but in a secure way where you're guaranteeing the confidentiality of the data. So for instance, we might have an encryption of X and encryption of Y, and then without decrypting this, without knowing the decryption key, you can still turn this into a third ciphertext, which is now an encryption of X plus Y. Likewise, you can do a homomorphic comparison between two ciphertexts. So this is not just looking at the bytes of the ciphertext, that would be meaningless, but you can do a homomorphic computation on the two ciphertexts and then compute a third ciphertext, which is now whether or not X is smaller than Y. And more generally, you can apply a function to encryptions and then get the result of that function as a new encryption. Okay, so what we can do in terms of, in the context of blockchain is we can encrypt transactions, we can encrypt the state on the blockchain, we can keep the data available on-chain, so it doesn't have to be off-chain. And we can also mix this together with existing applications. So you really decide, and we'll see an example in a bit, you really decide which part of the contract you want to have encrypted and which part you want to have in plain text. So there's no, if you want to run ordinary applications on our FHEVM, you can do that. But then you can start bringing in or changing some of the data types to work on encrypted data instead. We're not doing anything to protect the computation, so everyone can see the logic that's being computed. It's only the data that's being computed on that we're protecting. We also have the implementation where it's up to the smart contract itself to decide what access control you want. So in other words, each smart contract decides which ciphertext can be decrypted and which can't, which makes you free to do whatever you want in your application. And we also make it very easy to mix data across different users and across different smart contracts. I'll get into the details, the technical details of this in a bit here. Okay, so some of the use cases we're looking at is tokenization, blind auctions, where instead of, so a blind auction today might be you first submit a commitment to your bid, and then there's a second phase where all the bids have been done, where you open all the bids, and then you compute who won the auction. In our case, using fully homomorphic encryption, you can send encryptions of your bits, and then you can also compute without decrypting anything who's the winner of the auction. So the only leakage with these blind auctions is really who won the auction. If you want to, you can also keep that private in some sense. Games, we can generate randomness on-chain, so it's easy to deal directly with the encrypted data. Of course, you can't do massive games with these things. We also have performance challenges, as we'll see in a bit. But you can start to make simple games. Voting is another one. Encrypted identities, I'll touch a bit on this later. And of course, private transfer. So you can make an ERC20 token where you keep the balances encrypted, for instance. I'll have a quick demo of that or slide on that later. Okay, so diving into the more technical aspects of this. What we do is we are basically saying there is a single global public key, FHE key, under which all the data on the blockchain is encrypted. So here on the left, we have the blockchain. The green dots represent validators. They each have a copy of the public key, meaning they can do these homomorphic computations and so on. And then next to it, we have a KMS, a key management solution, where the secret key lies. So, and the orange dots here, which are the threshold nodes running the KMS, they don't have access to the actual secret key. They just have secret shares of the secret key. Okay, so there is a threshold assumption here that you need a certain amount of corruptions in the KMS before you can leak the secret key or take advantage of the secret key. But using these shares of the secret key, the players or the parties in the KMS can still do decryptions and threshold re-encryptions, as we'll see. Okay, but that's kind of our setup. Another point is we're not touching anything on the blockchain side of things, so you still get your proof of stake consensus and all that stuff. The only thing that our protocols are dealing with is in the KMS and how we keep the secret key secure. So a naive way of generating this secret key would be to have it generated on one single party and then secret sharing it. That would, of course, be insecure. So what we have instead is we have threshold key generation. So the orange dot here, meaning that the parties inside the KMS, they start out with nothing, and then they run a protocol between them to generate shares of the secret key as well as the public key, which can then be distributed to the validators and to users. When the user wants to input a ciphertext now to the blockchain, he can simply take this public key, take his input X, encrypt it, and send it to the blockchain. We're also saying here that it's not just a ciphertext he sends what we call a certified ciphertext, which is because the ciphertext comes along with a zero-knowledge proof of knowledge that the user knew this X. I'll get into the details of this in a bit, but it has a security requirement. But that's, yeah, so that's simply providing inputs to the blockchain. He just encrypts under the public key, generates a proof that he did the encryption correctly, and then sends this into the validators. When we want to do operations on this is a purely local operation or computation from the validator's perspective. So here they take an encryption of X, an encryption of Y. They apply these homomorphic operations, which can be done locally. So each validator is doing this, and each validator will then arrive at a new encryption of C in this case, so the comparison or the addition, multiplication, whatever you want, of X and Y. The scheme we have and the implementation we have is deterministic, so that's why we get consensus on the byte level of these ciphertext. And all of this stuff can be done locally. When we then want to do a decryption, so at some point you might want to know who won the auction, so you want to decrypt the winner of the auction. We send this ciphertext to the KMS. The KMS runs a threshold decryption protocol, meaning they all communicate. We have optimized protocols for our encryption scheme, or MPC protocols for our encryption scheme, that can then do the decryption, arriving at X in this case. Sometimes, of course, you don't want the X, or the plaintext value, to be publicly known to the world. So what we do instead is we also have what we call re-encryption, threshold re-encryption, where the KMS starts out with an encryption of X, and then a new public key, so in this case a purple public key, and we'll see in a bit where this comes from. And then what we do is we take the encryption of X and we turn it into a new ciphertext, which is now an encryption under this purple public key. And again, the naive approach of doing this would be to have the KMS decrypt the ciphertext and then re-encrypt it, but that will of course be insecure, so we actually don't do that. We go directly from the encryption of X into a new encryption under this, of X under this new public key. Where this is useful is, of course, when the user wants to see his own balance, for instance. So in that case, he can generate a key pair locally, meaning he has the secret key to this key pair. He can send the public key to the blockchain, and then we do the re-encryption under this new purple public key into the encryption of X, send this to the user, and then since he knows the corresponding decryption key for this purple key, he can decrypt and obtain X. Okay, so I want to dig into how the FHEVM works a bit more from the technical perspective. We do primarily one modification. We add a pre-compiled smart contract to the FHEVM that allows us, for the most part, to call into our homomorphic library, TF-HERS. And then I also want to cover what we call honestly obtained. So since we want smart contracts to be able to decide the access control logic, so the smart contract developer really decides what can be decrypted and not be decrypted. That also means that a malicious user could submit a malicious smart contract that would just decrypt everything. So you could go on the blockchain, you would grab a ciphertext, you send it to your malicious smart contract, which will then decrypt it, and that way you can reveal all the data on the blockchain. So to avoid this, we put a limitation that smart contracts can only ask ciphertext to be decrypted that they have honestly obtained. And then forcing this notion of honestly obtained could be done using zero knowledge proofs, where you kind of prove along the way that this was actually done correctly and that you had the rights to kind of arrive at this ciphertext. But as I'll talk a bit about later, this is actually really expensive to do verifiable computation for FHE. So instead, we have more a software-based approach or logical-based approach, where we enforce that smart contracts, they only ask honestly obtained ciphertext to be decrypted. And I'll dig into how we do that in a bit. I see a counter here. Is that a timeout for the talk, by the way? Yeah, okay. All right, so I'll go a bit quick on this. So basically what we do is we have a smart contract A here on the side. They don't operate directly on ciphertext. They rather operate on handles to ciphertext. A handle is just the hash of the ciphertext, so this makes them smaller, makes them easier for the smart contract to store and pass around and so on. Then whenever the smart contract wants to do anything with this ciphertext, it sends it to our precompiled smart contract, which has an area of memory. So this is just a normal area of memory that is allocated and unreachable by the smart contract, where we keep track of these handles and how they link to the ciphertext, and also we have an access control list. So in this case, we say that this handle, HX, was honestly obtained by a smart contract A if A is in the list LX. And that's kind of our property. So when the user provides this certified ciphertext in the beginning, the sender here, the user on the left-hand side, sends the ciphertext along with the proof to the smart contract. The smart contract can't do anything with this ciphertext at this point besides passing it to the precompiled smart contract, which will verify that the proof is correct, that it was something that was sent to the smart contract. So we're linking this ciphertext to the smart contract, and also that it came from the sender. We verify the proof, assert that it's valid, and then we simply update the protected memory saying, okay, this handle is now pointing to this ciphertext, and A has honestly obtained this ciphertext, giving it back to A for further processing. So we now, smart contract A at the bottom has this handle to the ciphertext that it can use for processing. If we then want to do a decryption, or the smart contract wants to do a decryption, we basically look up the handle in memory. We assert that A has the permission, was in the list. If so, then we send the ciphertext to the KMS. We wait for a response. We get back the plaintext value. We now store the correlation between the handle and the plaintext because validators can call the KMS, and the KMS will wait until a certain fraction of the validators have said, okay, this is what we want to decrypt. But full nodes trying to catch up, for instance, they won't be able to do this, so we store this correlation between the handle and the plaintext for them to see in the future. And then we send X back to the smart contract. Here is just how we call operations, same story. We see that we're using our library. We fetch the ciphertext in the protected memory, then we give them to the library, and then we mark the ciphertext afterwards as being honestly obtained. We also track if one smart contract is sending a ciphertext to another smart contract, then we update these permissions along the way, saying honestly obtained is also, or in this case, smart contract B also honestly obtained a ciphertext if it was given to it by A that had it honestly obtained. And likewise, if it returned something to A, then A also honestly obtained this ciphertext. So this way of tracking what was honestly obtained is where we can block decryption, right? The components we have the FH EVM, so this is our EVM for running these contracts, the threshold protocols for the KMS. We have a Solidity library that doesn't touch anything on the developer side, so you can use your normal developer tools to express smart contracts, and then you need the FH EVM to run them afterwards. One of the things we do is we introduce this EUINT32 data type, or other data types as well, that represents these handles to ciphertext, and we then add operations to them. You can do add, subtraction, comparisons, and so on. So I'm going a bit fast here. This is where we convert them. So you get the raw ciphertext bytes, then you convert them into a handle. So this is where we do the proof checking. We can do decryption, as I said. One thing is that whenever you do a decryption, even if you're just decrypting a Boolean value, so here you can do a homomorphic comparison between the amount and the balance you have, which gives you an encrypted Boolean. If you then want to use this in a require, you have to decrypt it first, otherwise it's meaningless. Of course, this leaks something. It's not clear what it is. That depends on the application. If you don't want to do this, we also have the CMUX operation, which is a purely local operation that doesn't decrypt anything. There are some caveats to that, but in the interest of time, I'll skip. And we can do the re-encryption as talked about. Okay, so finally getting to the point. FHE, O, and CK, the way we see it is that these two things, they really come together. So both of them are kind of like a privacy solution for it. One benefit of FHE is that it gives you this composability, especially when data is coming from different users. That's kind of hard to do in CK. And also with FHE, we can keep everything on-chain. Oh, okay, the counter went up again. Okay, so to dig into this a bit, if we would... Oh, okay. So if you want to do a computation, so say you store commitments on-chain using CK, when you want to do a computation on this, you need to do that computation on the plaintext data. So in this case, we have, the validators would have 2 commitments on-chain, and then the user would have the corresponding plaintext data. When he wants to do a computation on this, he can do the computation at the bottom, he computes set, which is a function of X and Y, make a new commitment to this and a proof that he did the computation correctly, push this to the chain. This works nicely if there's just a single player doing this. The problem is, what if you have 2 users and they now want to mix this data? Then the question is, who actually does this computation? Because the computation needs to happen on plaintext data. With FHE, and since everything was encrypted under the same key, this was trivial to do, right? But this is one of the big differences between FHE and CK. Another thing is that CK is typically used, for instance, in an identity solution to prove that certain statements are true. The way we see it is that you can do the same in FHE, but instead of proving and then checking the statement, you basically compute the statement homomorphically, and then you can check that it was true afterwards. So if you want to attest that someone has a certain age and so on, you can just compute whether or not this age is above a certain limit, and then make a requirement on that. So you can also build some of the same applications with FHE. Okay, I'll stop here. All right. Thank you. I think Okay, sure. All right, thanks everyone.
Okay, let's have some Q&A over there, please, or outside. Thank you, Sama. Now we have AJ here, there. Yeah, AJ from Radius. Thanks.
Hi, this is AJ, a founder of Radius. Radius is building a shared sequencing layer. Sequencing layers is kind of a new infrastructure in modular blockchain space to help developers develop their own ZK validated rollup and also operate them efficiently. So there are some challenging parts in building a sequencing layer. So Radius' approach is that to apply a cryptography like encryption or ZKP as much as possible. So the challenging part in developing ZK validated rollups is kind of to run sequencer nodes by themselves. Sequencer is kind of like a validator for Ethereum. So the thing that sequencer does is that receive transactions from user and aggregate them to build a block, and then execute them, and then post a result and state to layer 1. There are two ways to decentralize sequences. We need to decentralize sequences somehow, so there are two ways. One is that to have multiple nodes operating the same execution thing. It's a monolithic approach, but we'd rather take a modular approach that we just specialize the features like builders to build a block, proposer to execute the block, and the prover also generating ZK proof for this state transition in rollups. So, but there are some challenging parts, which is the pre-confirmation. Rollup is all about the scalability solution. So pre-confirmation is really important, like to make user experience better. But to apply this modular approach in sequencing for rollups, there should be some unwanted additional latency for pre-confirmation. That pre-confirmation is to say that your transactions will be included in next block or something. So with this modular approach, the time when you get pre-confirmation from the system is that probably after proposer or build a block, after proposer or confirm a block. So it's kind of additional latency happening in this approach. So in Radius approach, that's where encrypted mempool and order commitment comes in. With the encrypted mempool, especially end user encrypt their transactions, so builders cannot see the contents of the transactions. So builders should respond to user with some kind of order commitment saying that your transactions will be included in a specific order of next block. Since builders cannot see the contents of the transactions, it cannot manipulate the order. So that's why builder can respond with this order commitment thing to users, which means that it's fast pre-confirmation. Not waiting for proposer to build a block. At builder side, you can respond to this pre-confirmation thing. Since we applied an encrypted mempool thing, another advantage that we can get is censorship and MEV resistant thing. Actually, Radius project came from this MEV resistant AMM stuff, and then we found out that there are some really challenging part in rollup space, especially sequencing part. So we could apply this encrypted mempool approach to this to make better this sequencing part. So as I said before, builder cannot see the contents, so we cannot do any malicious bad MEV extraction happening in builder side, like front running or sandwich attack. So builder will go deep into this. So in this modular approach, builder and prover is kind of a commodity. So we can consider both a builder and proposer as a sequencer. So I will explain with this concept. So let's go deep into this. So encryption part, we applied a delay, a time lock puzzle encryption thing, which means that the solution to time lock puzzle will be the decryption key, which means when an end user encrypts their transactions with this with time lock puzzle encryption, a sequencer needs to find this decryption key by solving time lock puzzle. That's where delay comes in. So during this delay, sequencer needs to respond to the user with this order commitment thing. So that's where MEV, MEV resistance comes in as well. So, and then end user can get guarantee from sequencer about the order with this order commitment. This order commitment is signed by sequencers, so end user can make sure that his transaction will be included in the next block. So what if sequencer, like a malicious sequencer, can lie about this order commitment thing? We can protect this edge case as well, because a sequencer needs to publish the results of the next block to layer 1. So smart contract in layer 1 is going to store a transaction hash list. So when end user find out this order commitment from the sequencer is broken, he can claim to layer 1. So smart contract in layer 1 verify the claim with the order commitment. So it works trustlessly. So when order commitment is broken, sequencer is going to be slashed. So that's how this order commitment, we can force sequencer to keep this order commitment as well. So with this encrypted mempool and order validation thing can protect you from malicious sequencers. So you can, your money will be safe. But another problem happening is going to happen on sequencer side, not end user side. So that's why ZK comes in. So let's say that there is some malicious end user sending invalid encrypted transactions to sequencer. Sequencer cannot distinguish that this encrypted transaction is valid or not because it's encrypted. So, so sequencer is going to waste their own computing resources to solve this time lock puzzle, and also it's going to waste on block space because it's invalid transactions like rubbish or something. So this wasting thing would lead network instability in network. So it's a really big problem. So we could solve this problem with the ZK. Obviously, and when end user creates encrypted transactions, they also need to generate ZK proof to prove that this whole encryption process is done correctly. So with this ZK proof, a sequencer can be guaranteed that this encrypted transactions is valid. So sequencer needs to verify this ZK proof, and then this verification is true. Now it's time to solve the time lock puzzle to find the decryption key. So in this way, end user needs to generate this ZK proof, but time lock puzzle encryption thing is really computation heavy, which means that time lock puzzle is based on RSA group squaring thing. So it's a sequential this computation. So that's many times of sequential computation is needed to generate like 1 or 2 seconds on general MacBook. So if you want to turn into this process into ZK circuit only, it's really not going to work. So the core achievement of Radius is that we made it practical. So we call it a practical verifiable delay encryption, which that we not only use ZK SNARK or ZK Stark stuff, we also combine ZK SNARK with Sigma protocol. So we can make sure that this generation ZK proof stuff on client side only takes 0.1 time. And regardless delay, which is needed for sequencer side. So it's about less than 1 second on your browser. So another one is that we need that right now we only prove that this ZK prove that this encryption process is done correctly. It's not guaranteed this transaction's integrity. So right now we are researching on this, to prove this encrypted transactions is integrity. So including signature and nonce and to prove that this sender has enough money to pay a gas fee. So we'd like to encrypt the whole transactions. Also, another approach that we are researching is that like a stateless approach. So to make this ZKP generation is like lightweight. So or we could use some kind of ZK acceleration on this because this time to generate ZK proof on client side is really important for a better user experience. So another problem, another challenging part in sequencing layer is that interoperability. People usually criticize this roll-up-centric approach because it's going to be fragmentation happening between these roll-ups. So we need to make sure that communication between this roll-up is kind of easy. So there are many projects, but I think the sequencing layer is well positioned to solve this problem because sequencer has a full control of building a block for roll-ups. Usually they build a block and then deliver a block to roll-up. And then even though sequencer has a full control, Radius has an encrypted mempool, so there's nothing sequencer can do, like manipulate the order of the transitions. So we can make sure that even though full control is on sequencer side. Anyway, interoperability, for example, flash loans have multiple transitions that should be executed in multiple rollups. So one thing that sequencing layer can do is that it can guarantee atomic inclusion, which means that sequencing layer can build a block, and then at that time, it can include these transitions in flash loans transitions in multiple rollups. So we can guarantee atomic inclusion as well. But the problem is that atomic inclusion is not enough to guarantee this interoperability between rollups. We need some kind of atomic executions, because even though the transitions included in a block, we cannot guarantee that it's going to be executed or reverted or something. So we need to prepare for this situation. So at that time, I think all the commitment, all the validation thing can guarantee this atomic execution thing happening between multiple rollups. But it's kind of difficult, but we are still researching for better solution for that. And then just in case this atomic execution is broken, we have to roll back to the previous state. But as long as this sequencer layer has keep tracking these all states and all flash loan transitions or cross rollup transitions in sequencer layer, we can exactly point out that where these multiple rollups should roll back. So that's another efficiency that we can get from this sequencing layer architecture. So we all know that many rollups will come, especially a tsunami of ZK rollup part, because rollup is going to provide scalability, flexibility for your project. So we'd like to make sure that this movement keep going, and to support these millions of ZK validated rollup, we think that our approach with this modular approach and sequencer layer is really needed for this space. Okay, thank you for listening. Thanks. Yeah, sure. No. Okay,
what do you think about utilizing VDFs for encrypted mempools? What do you think about utilizing VDFs for encrypted mempools?
Probably.
What do you think about utilizing VDFs, verifiable delay functions, for encrypted mempools?
Can I take the offline? Can I take off stage? I can't hear properly. So.
He takes his off stage. Any other question?
Sorry about that. Okay, thank you.
Elio, okay, there. Please, welcome to the stage.
Yeah, this is it. Yeah. So, sorry, what is this?
No.
How do I?
Put this here.
Sure.
Forward, backward.
This is forward, right?
Forward, backward.
Backward. Okay. Yep. Okay, got it. Excuse me. I'm a little short here. Hey guys, how's it going? Thanks for the thumb up. Okay, so welcome to the talk, my tech talk here. Elio, how many of you have heard of Elio? Wow, I'm very impressed. I have to talk to my event ambassador here in Istanbul. It's my first time here. My name is Joanna. I run the BD department, business development department at Elio. And I'm usually based in New York, but you will see me in various conferences. So yeah, really excited to be here. I think DevConnect is a great venue for people from both U.S. side and Asia and Europe, everybody meeting in one place. And we'd love to give you a little bit of a background on Elio today and dive deep into the technical design. Okay. So what we believe that we're solving is the third wave of the technical problem. So if you start thinking about the first wave, right, when we started the whole digital revolution with Bitcoin, right? So Bitcoin is essentially the it's the public money transfer, right? So the very first white paper we talked about, Bitcoin white paper that solves peer-to-peer transaction decentrally, without any intermediary, without anybody acting in between. But that is done in a public manner. And then when 2017 came in, Ethereum gave us this idea that we can put a computer on chain. So all of a sudden, we can do all kinds of different smart contract or different programs on the blockchain, right? So Ethereum is another way thinking about like doing things in the public way, but with programmability. And in between, actually, I missed to mention that Zcash is another protocol that really solves the money transfer issue, but in a private manner, right? So finally, the next step we're solving here is the private private programs, right? Like applications, right? So now developers can finally use our full stack to develop and execute anything onto this private network. Okay, so this kind of sums up what I was just saying. Where we stand in that top right corner is this sweet spot of programmability and privacy, right? So think about, not only privacy programmability, usually we talk about the blockchain dilemma, right? There's three things that usually people say we can only achieve 2 out of the 3, right? So those are programmability, privacy, or security, and then the last one is decentralization. So decentralization is actually the key here. I will argue that Elio is very different from many other ZK, EVM chains because of that, right? So we are a layer 1 blockchain, and we have built our own virtual machine to accomplish the computation design. And so just like some of the other roll-ups, we have scalability, but we actually have our own virtual machine to really come up with a privacy-preserving quality. Next one. Okay, so yeah, coming back to the importance of permissionless. We're the first permissionless, programmable, and privacy-preserving platform, right, for decentralized application. So as I mentioned, as some of these other roll-ups, right, ZK roll-ups are trying to accomplish decentralization in the future state, we're actually already accomplishing that today. And that's being embedded in the ecosystem where we have basically the prover side, we have the validator side, and the developer side, all of which are designed in a decentralized manner with incentive mechanism to encourage them to participate. I will dive into that in the next later state. And then I will say the other thing that is important is privacy, right? So we talked about what makes us different. The privacy aspect, right, is what we believe is currently stopping a lot of the mainstream to come into the adopting this, ZK or blockchain technology. Oh, okay. Yeah, so our founders actually wrote this ZEXE white paper. ZEXE is the name of the white paper back in 2018, so 5 years ago. 6 co-authors, out of which 4 is part of the core team at Alio. So the idea is really doing zero knowledge execution and enable the privacy preserving quality, right? And today you can actually see this on our testnet. We're about to go mainnet launch in January 2024, so in 2 months, short time. And again, if you think about using, a real world example, right? For instance, when I send my transaction to somebody in the audience, the transaction record on the transaction amount and the transaction address is completely, private to me, right? In the real world, like when we send through a bank, and that's currently not available on the blockchain, right? It's very transparent. If someone knows your wallet address, they can pretty much steal everything. Very least, right, knows everything that you own. So privacy is really what we believe is the roadblock for mainstream adoption today. And a good example here is to compare that with something that you guys probably, I don't know, I feel like the audience here is pretty young, so may not know this reference, but Netscape is actually the inventor of the secure socket layered encryption, right? So it invented the HTTPS navigator standard or the web browser standard. And it's kind of crazy to think about how it's ubiquitous today, right? And how innovative that was at the time. It was a proof of concept that really revolutionized the entire internet. And it doesn't actually, the company doesn't exist anymore, but the fruit that it bears, right, can continue to benefit the industry. So we believe that we are that company that leads the privacy programmable application layer. Okay, so I have already talked about the left-hand side, where we stand. I think here is really important to accomplish, all the private apps in a also cost-effective way, right? So the only thing I will touch on this slide is the zero gas fee and the unlimited runtime. So gas fee here in Alio is only enabled when computation is done on-chain or in a shared state. So in most cases, computation is actually done off-chain, and the verification of the zero-knowledge proof will be brought on-chain. So this really accomplished that, the zero gas fee on-chain, right? And on the runtime side is, unlimited runtime is already embedded on the protocol level. So all of this is to say that this really unlocks a new wave of possibility that wasn't available in Web3 before, such as machine learning model, right? So machine learning model, as you can imagine, is very complex and it's hard to run that on a blockchain. Just to give you an example, on the blockchain that use gas like Ethereum, a simple linear regression model will just exceed the gas limit, right? So we actually have a whole use case category that talks about ZK-ML, which combines both machine learning and ZK. So this one, I would say, I have already touched on. I mean, I think the only thing here is just, again, to give you a quick overview on how we, you know, in terms of your cost estimate, it will plateau after a certain level. It's not a dynamic, you know, gas model like most of the chains. Okay. So to go back to how we are designing our architecture, right? So actually, let me go to the next slide. It would be easier to explain with this. So what we actually designed is a purposely built tech stack that's completely from the ground up. I mean, I talked about the fact that our OG project, right? We've been around for 5 years, and you know, I'm glad that you guys all heard of us, but usually I go to a crowd and ask that question, now a whole lot of people will raise their hands. And the reason for that is we kind of stay under the radar for a reason. We've been very much focused on the research development side, and we build this, you know, Snark VM, Snark OS, everything from the ground up, right? We didn't just kind of use some existing model. So to really dive into this iceberg, right, the tip of the iceberg, right, what's underneath? So first layer, you have Leo, which is a high-level programming language. It's our own DSL, our own domestic, domain-specific language that is, again, purpose-built for privacy-preserving qualities. And Leo will compile into the intermediary language here is Aleo instructions. So that also interact with our bytecode. And then down beneath, you have the Snark VM, which is really dealing with the most sophisticated PhD degree, you know, ZK circuit kind of problems. So I mean, we really try to abstract away as a programmer, you know, to come into the ZK industry. You're afraid of, you know, not having a PhD degree in cryptography, but you know, fear not, because coming into Aleo, the level of entry is quite low. If you have Rust or JavaScript and TypeScript programming language experience, it's really easy to pick it up. And on the left side, we even made sure that some of the developer experience is done in the very like smooth way, right? So we have an SDK that is a developer toolkit. You can actually go onto our website that, you know, has an entire documentation layering out the specifics on the SDK, different user interfaces that we have designed for you. And then the OS is the operating system that's basically Snark-based, right? So, okay. This is just to give you an example, like what I mean by we are abstracting the complexity, I'm sorry, from the programming experience, right? So Leo here is really a bridge that bridging between the cryptography world, which is very much ZK circuit and elliptic curve based, right? And the world where you actually program and execute, you know, the one on the right-hand side, the evaluation environment, execution environment. So, you know, Leo sits in between and it interacts through, here is missing that middle layer, but it was on the last slide, the Aleo instructions, right? And then they, like if you actually ever type like a code into our interface, you will see that it just like auto-translate your code in Leo into a Aleo instruction, and it's quite magical, actually. I'm not a programmer myself, but I've done it before just to learn, and yeah, it's a very smooth user experience. Okay, so this really dives into the difference between us and a Ethereum model, right? We are not a VM chain, as mentioned. We've done that as a trade-off, right, to not specifically attracting the Ethereum ecosystem, but we are building the entire model based on privacy and based on security, right? So the reason why we chose to do that is because we first actually, our founder Howard was part of the Ethereum Foundation research group, and he was looking at potentially using the Ethereum model to build this for private use cases, and realized the record model just doesn't really work for privacy. So what it means is like, in the record model, which is in the middle, right, the Ethereum model, it only allows you to, it has the ownership information, everything, in a shared state, right? So unlike the record model, we have this UTXO-based model that we call like account model, right? So in the account model, you have, instead of two keys, usually public key and private key, you have another key called view key. And that gives you the ability to choose who you want to share that account information with and what you want to share, right? So in this account model, it truly has that, as I mentioned, the default privacy mode. But also, the other thing I want to mention is, very importantly, it's not always private. You can choose to be public or private. So if you think about, like, Ethereum is a white box, right? I call it the white box. Everything is very, very transparent. You cannot hide anything for any circumstances. And then maybe like a Zcash, right, is a complete black box, or one of those Monero, right, private payment companies. You can't see anything inside. We are actually trying to be this middle ground, right, the gray box that allows you to fluently translate between the transparency and privacy world. So here is what we call like kind of the three pillars, right, within the ecosystem. So I kind of touched on this earlier. We have the prover side, which starts with generating or running that zero-knowledge proof using the mining GPUs or FPGA or other kind of ASICs hardware. And then you have validators who are in the middle that's actually coming to a consensus using our POS. So we are POS and POW chain, right? So very much very innovative approach to combine both proof of work and proof of stake into one. And then on the developer side, right, finally get to work on the programs itself. I'm going to skip a few slides here. So I think I wanted to just re-emphasize, right, what we're proposing or what we're actually using today is a different model from the existing world, right? So because we have our own VM and the scalability is already embedded in the protocol, so we can still have that scalability, right, that's usually seen in a roll-up. And then we also have the miners or the validators involvement. So everything is designed in a way to incentivize those participation. And then finally, I think for a lot of you, we want to talk to you, the developers, about how to actually put all these tech stack into a use case, right, that's usable in the real world. So last two things I want to touch on is the current ecosystem state. Okay, so these are new slides. You guys are the first one to see it. But essentially, what we've been seeing is this dramatic explosion, I would call it, on the developer adoption. It's really been very heartwarming and encouraging to see that throughout the development phases, we have 3 testnet phases running in the last 3 years or so. Every year, we have a new testnet incentive program that we're running where we give out the rewards to developers, right, to incentivize them to come onto Alio. And each time we see drastic changes and people stay, right? They not only just come for the rewards, but they stay on the network because they realize it's something that they haven't seen before. So currently we have a monthly active developer number of 120, and the total program deployed is 14,000. And just to give you a perspective, right? So to compare that, the growth rate with some of the other leading ZK protocols, we're by far, the highest growth rate on 80% of the growth rate on the monthly active users or developers. And also just to give you a sense of who are actually building on the ecosystem currently. So we have about, this is 7, right? 1, 2, 3, 4, 5, 6, 7. Yeah, 7 use cases out there. A lot of the folks decided to do tooling and infrastructure play. And some of them decided to go into we call it ZFi, right? Our code word for DeFi with zero knowledge proof. And actually, very interestingly, a lot of folks decided to also build these social fi and gaming use cases. One thing I think really interests me is the gaming aspect, right? So now you can actually build fully on-chain game with zero knowledge embedded that allows you to bluff, for instance, right? To actually do a poker game on the zero knowledge proof chain or on blockchain anywhere. And then lastly, you have identity and governance and voting use cases and ZKML, as I mentioned earlier. So I wanted to really end on the last use case. Sorry, I know I'm running out of time here. We just launched this product called ZPass. It's a first-party dApp that we developed in-house to dogfood our own tech stack. Right? So this is an identity solution that is, and you can go to our website and try it out right now. It's already live. It's really used to do an attestation or decentralized identity solution for specifically this partnership that we just closed with Common Sense Media is to prove age of the school kids to some internet providers, right? So for instance, if your kids is, not over the age of 18, they cannot access certain content on Netflix or on Disney, for instance, right? So this is really solving a real world use case. And we're really proud to be the one that's enabling that new use case. So any questions, please, please, please do get in touch and come to our ZK house. We're actually organizing a whole week-long, 4-day event starting from today. So please do check it out. Go to this QR code, and it will allow you to go to all the various events. I'll leave it down there so you guys can take a look. Thank you.
Well, thank you all for being here this morning. Lunch is being served already. There's no need for a rush. We'll have 1 hour. And we'll be back at 1:30 for a panel about new frontiers in CK research. So we have an hour here just to have lunch and some rest. Okay, thank you all.
Hey everybody, how's it going? Awesome, everybody having a good ZK Accelerate? Yeah, okay, cool. I'm Lance Davis. I'm a software engineer at Giza, where we do verifiable machine learning in Cairo. I am here with Memi Ratsimbazevi, Misha Komarov, and Diego Kingston. We'll be talking about future frontiers in ZK research. So if you're curious about future proving systems, just in general, the future of the ZK industry, you're at the right panel. I wanted to start by asking you all just the classic ZK question about snarks versus starks. What is your preference? What does your team use? And is there anything that you would say is a clear, definitive winner?
Okay, I'll start then. My experience was I started being a snark guy, then I switched to starks. The thing is, I think that to make the distinction right now doesn't make really any sense. It's more like, perhaps, as we were talking here, a Twitter fight. But I think that, at least for beginners, starks is easier to learn because you have less things. You only have finite fields, hashing, and you don't have to get into some gory details related to elliptic curves, pairings, extensions. So really, that's why I like perhaps a little bit more starks, but just personal preference.
For sure.
Okay, well, here we go. It's like what I'm saying is that there's no difference between them, in fact, because both of those are just different combinations of the same components. I mean, let's say it this way. For example, on our side, we have, I don't know, Blanky share monetization over hash-based commitment scheme. What is it? What is it? A stark, a snark, what the hell is this? So that's the first thing. Second thing, let's say this way. I mean, it's like stark's naming was made up just to highlight that there's just a switch in the commitment scheme and that's it. So that's, like a pure marketing effort. It worked out great. I mean, people actually use it as a term, but in fact, it's pure marketing effort. So no difference. I mean, it's just a combination of different techniques. So there are weird mixers. There are weird mixes of that, and we use one of such mixes. So it's like, what's the difference?
For sure, for sure. So it's like, it depends on the types of tools that you want to use to prove computation.
Yeah, it depends on what you want to do. It depends on the answer to the question, why.
Yeah, got you. Maybe?
So for me, obviously, snarks win, because if you want to prove on the EVM, you have to use snarks, because there is no other alternatives. You have growth 16 and proof composition if you use starks anyway. Well, joking. Actually, at Tyco, we have a multi-proof approach. So we invested for 2 years into the Hello 2 KZG by the PSC team at the Ethereum Foundation. And more recently, we also are exploring ZKVM. So from Zero Powder Neil Foundation, also because writing circuits for snarks is very painful.
For sure. So in terms of the development of ZK, would you all say that most of it takes place in academia or in industry?
Well, I think it takes place in both places.
For sure.
Of course, you have different perhaps incentives or goals in academia and in industry. Ideally, what you would have is a joint effort between academia and industry. Yeah. Sometimes in academia, you have more freedom to explore certain paths that perhaps when you are in a company, you don't have that much freedom, but then, of course, you can get those cool ideas, and if you see they work, try them. So really, we've seen many people also, Starks, Eli comes from university, so it's just it goes both ways, I think.
I mean, the academia, if you want to fuck around, then of course the academia is your choice.
For sure.
It's like, and find out something, right?
Yeah.
So if you want to do the actual product, just do the actual product. Why do you need academia? That's the thing. So all the actual product used use cases, all the actual product used combinations of whatever, proof system, whatever it is, all right, were done, just for particular use case, for particular thing. It's that's, that's just what it is.
Makes sense.
So people always ask, what's the killer application of blockchain? And I'd say it's zero-knowledge cryptography research. Now, VC funds like Geometry, who are not with us today, they even have a cryptographer in residence, and that's also the same for Andreessen Horowitz, Paradigm, and other funds. But like Misha said, I think academia looks into the theoretical, but there are many, many engineering challenges that come up, and everything that we talked about at ZK Accelerate that relates to GPU, FPGA parallelization, it's not, it's computer science, it's not cryptography research that's done in academia.
For sure. So as a follow-up to that, since we're all industry here, what is you all's approach, or at least I would say engineering approach, to developing new systems in ZK? I know that each one of you have had experience with this. What is more so the design approach and execution phase?
Well, I think that in industry, what you try is to fail fast.
Yes.
You want to see which ways can work, which ones don't. And then I think we also have something that, well, we implement and then we start iterating a lot. We also try to learn from other teams. Really, what I like, especially of this field, is that there are lots of open source developments. And so sometimes some project thinks of some cool idea, we have another, and maybe we can combine all those approaches. So really, that way we can build really nice solutions, and that's it.
For sure.
The approach always depends on the use case. It's like over the years we had, a bunch of different use cases, starting from, I don't know, inventing ZK bridges, or like, I don't know, going to whatever, all the, proof market stuff, ZK Oracle stuff, and different things. So in the end of the day, with placeholder, we resulted into, trying to make it as flexible as possible. It's like being possible to adjust it to a particular use case, which is like, right here on the table. So, I mean, just make it adjustable, I guess. I mean, that's what it is. Make it flexible enough.
Yeah.
I guess on our side, we have a researcher, and for the more prospective stuff, for example, recently it would be optimizing lookups, but compatible with KZG commitment. We send that to that researcher, then we have a team that will implement either proof of concept or something that has been researched, for example, by the Ethereum Foundation, and that we work closely with. The issue is that we have a go-to-market, we have a mainnet, and we cannot focus that much time on research, and it's very important, like as open source communities, Telegram channels, like Zero Knowledge Podcast, that we use to share ideas is very important. And if you've seen the rise of AI, it was also the same 7 to 8 years ago. You had many frameworks, Fiano, TensorFlow, PyTorch, Chainer, MLIR, and everyone was talking to each other, and it went up very fast. And I see a similarity in ZK, is that competing companies are still talking, because I like that they think we need to grow the pie and not just grab everything and just keep in a small corner.
I like that answer.
Yeah, no, we like a lot your repo with all of the optimizations, fine fields. It's awesome because you know all the tricks. So thanks for the effort.
For sure. So what I'm getting here is that you need to fail fast, but then also the open source community is a really important aspect of it. In terms of somebody who is new to the space, doesn't really know much about the resources that are out there, for example, the podcast, the open source repositories, what advice would you give them for starting a new research and development project in ZK?
Oh. I guess there are a couple of very good communities that aggregate a lot of info. So, for example, 0xPark has a lot of tutorials from zero to hero. You have the Moon Math manual by Leaf Authority. you have a course that was given at MIT by Zero Spark called ZK IAP, which goes from the ground up. Risk Zero have those study club. At Tyco, we have the ZK roller coaster to keep up with every updates every 2 weeks. We're agnostic. We talk about everyone. And Lambda class has also, well, there's Zero to Hero and an excellent community about ZK. So I think you need to get into one, and then you follow the breadcrumbs.
Yeah. It's like on our side, we hosted and we still host like a series of, like workshop, explainers, everything. But I would say they are more related to, not, how to reinvent the wheel, but on how to, like expand the field. That's like, a little bit of an effort we do from our side to, help with this.
For sure. Well, in my case, I didn't come from cryptography. I come from chemical engineering, so I had to learn all this stuff from the beginning. And really, I found that there were like very good resources like the CK MOOC. It was a little bit more academic, but at least from my studies and all that, maybe it was more familiar to me. You also have to find the resource that's right for you. Some people are more math-minded. They need to understand the math first. Some other people like coding and like reading code bases. So maybe you have to find which one is the right approach for you. Of course, the best idea would be to follow the different projects, because there you have different resources and also code. Because there is one thing that when you read a protocol, in the paper, it's one thing. When you implement it, it looks completely different. So going to the code base lets you figure out all those details, or at least the choices some people made to solve those problems.
For sure, great answers. So then when we go the opposite direction of companies or research institutions creating content, Tycho, Neil, and Lambda class all have wonderful content out. What is the typical production life cycle for great content, especially when it's very technical?
Well, right now we are doing several boot camps. So I am in charge of the Sparkling Water Bootcamp, and I am super happy to have many of our interns here. And the idea is we try, as always, to iterate fast. We have like open discussions, try to be as clear as possible. Maybe we try to find also places where there is not so much information, because really, if we see a very good resource by somebody else, we just put it in our learning path and say, go read this, read that. And yeah, we try to play a lot. We are also teaching a course about cryptography at university. So really what we want is also to get feedback, because we realize there are different profiles. There are people who like code, and there are people who like more math. And so you have to address both and try to generate resources that are adequate to each group, and try to also make them understand the math, because really in CK, you need to understand at least the basic concepts.
Yeah.
Well, on our side, we don't see any point in spreading effort to, just educate for nothing. So once an educational content and something coming up from our side, or like, just happening from us, some workshop or like whatever, it's usually about something, some problem on the market we see which can be currently solved. So this could make absolute sense for the folks coming in with something like, okay, this is the actual thing which can actually be used, and we can even, if you come to us with, as after workshop or something, we can tell you exactly whom to come to and what to do to get this used by somebody, like the actual product thing. So it takes a lot of fighting internally. Like, for example, with a proof system thing, with a proof system like on London workshop we did some time ago, Alisa did it. We basically targeted it to that point when we realized that people have considerations about, how performing the tool chain is, or like, can it handle something or not? So we're like, okay, well, this is how it works. this it can handle, this it cannot handle. That's the thing. Or like there was an Oracle workshop. It's like we hosted a ZK Oracle workshop exactly when we saw that there was a market opportunity for those who come to this workshop to get such oracles built up for different products, for different protocols, and solve the actual problem with it.
Yeah.
So it's all about we kind of try to target when we see it makes sense for something.
Yeah, for sure.
So for content management, I think companies need to realize that it's a full-time job, and the skills to get into all of mathy detail and get those into a comprehensible wall are very rare. And usually the research takes a long while, so they have multiple streams at the same time, and they just take notes as news come from companies, from research, etc., and then they ask engineers, what do you think of that? Is there a future? And at one point, you have something good enough to create a content. If it's not enough, you just go to the researcher and you pick their brain, you organize a Twitter space or a video, and then you do a summary, and you add everything all together.
Got you. Great answers. Just want to ask, in the perfect world of ZK, do we still use trusted setups?
Well, that's another dimension. But of course, really using trusted setups gives you some advantages because really you get smaller proof sizes. So maybe it's something that still you don't have like super powerful quantum computers, so maybe you can deal with it. And really, it offers like some advantages also in terms of the cost of the verification cost. So maybe for the time being, we'll have to settle with trusted setups, even though we wouldn't like, at least in my case, to have a special setup and have to trust that it was done correctly. So that's a problem.
I'd say, do we use it depends on the use case again. It's like for some cases, the security assumptions are critical, and you cannot rely on trusted setup of whatever size. So you just cannot fuck around with some use cases. Okay, so it's like, for example, like with the placeholder securing like Lido thing, it's like you cannot just do anything with it. You get like as secure as possible. That's the thing. But in the same time, verification cost, let's be honest, is all that matters. Everything else is bullshit. So, I mean, you will not get proper verification cost on EVM until EVM changes for the absence of trusted setups. So once EVM changes good enough, I mean, we'll get a better cost, and, it makes no sense to use KCGY.
Yeah.
So on the EVM side, one of the most costly thing is the state. And the issue with stocks and everything that do not have trusted setup is that the state grow with the size of what you want to prove. So for blockchain use cases, I think trusted setup will still be needed. But then in the future, maybe if we reach a perfect world of ZK, it will be when you have quantum computers and you won't be able to use pairings on elliptic curve at least, and you'll be forced to use Starks. Now, if we get pairings on lattices, that might be solving some of the problems that we have regarding quantum computers, for example.
For sure. So just wanted to ask some individual questions. For Memi, I wanted to ask you about trustless bridging on Tycho using ZK. What do you all do now?
So at the moment for bridging, we don't do anything specific cross-chain, but we have a partner, Polyhedra. They just received a grant last week, and the product is ZK Bridge and ZK Lite client, and they do that with a fast finality. And so for now we rely on partners. We need to pick our fights.
For sure. And then Misha, what about placeholder and the ZK LLVM?
So, I mean, it's like, what about it?
Yeah,
I mean,
just
okay, whatever. So basically, it's so basically what it is, it's a proof system designed for procedural generation of circuits. it's like, you know, tightly coupled with the circuit compiler. I mean, and the circuit compiler has been used like for, you know, different use cases, like, I know, starting with ZK VMs, like for ZK sharding we spoke about like recently, or like, I don't know, for cases like, I don't know, some ZK oracles, some cases for ZK bridging, some ZK ML use cases. So, I mean, it's a Blankish arithmetization proof system with IVC coming on. Default commitment scheme in there is like, you know, LPC, list polynomial commitment, modification of Fry, okay? So there's a way to switch the commitment scheme. So that's like the thing.
Really cool. And Diego, want to ask you about recursive Starks, particularly those that use multiple proving systems, like using Groth16 to verify a recursive Stark.
Yeah, the idea is that in Starks you can use recursive proving, like to batch several proofs and then distribute the cost of the final verification among all the different programs that you proved. So the thing is, Starks have a logarithmic proof size, which is sometimes not convenient, and besides in the EVM, well, you have to verify it using pairings, so you have to change the proof system. Of course, in that case, since Starks has a different native field, you are forced to emulate the field, which adds some overhead. Of course, then the cost is in the prover, not in the verification. And really, that way you can get like a very succinct proof. So it is interesting. It is being used by several companies. For example, the CK EVM by Polygon has one final step where they use Groth16. Of course, by doing that, you also lose the post-quantum security, but nevertheless, Ethereum relies on elliptic curves, so we would have to change Ethereum first.
Interesting. Thank you all. Wanted to ask if there are any questions in the crowd. All right. I have an application question if there are none. Want to ask you all about zero-knowledge multi-party computation. What do you where?
Hello.
Yes.
I just wanted to know, like, what do you guys think about folding schemes and all of the research that is being done on folding schemes?
So one of the paper of 2023 was revisiting NOVA on the cycle of curves. And that highlighted an issue in the, not in the research of folding, but just that when Microsoft did NOVA, they created security proof on normal curves, and then for efficiency, they implemented this on the pasta curves. And then, it was broken. The fix was quite easy, but it means even though there are a lot of interest in nova, supernova, hypernova, protostar, protogalaxy, I don't know what else, we need to move slowly, but also fast, because we need to fail fast to prove if it works or not. Otherwise, everyone will go to Starks, I'd say. But there is interest, at least at Tycho, and Misha said that he has interest in IVC, and he will release soon. So.
Yeah, and also the people at Starks were trying to see whether we can use some of the cool ideas from folding schemes. Of course, perhaps what we lack is comprehensive benchmark. We still have to discuss that and try to get to more realistic numbers. But again, as Misha said, it also depends on the use case. So we have to see which one is the best option for your case. And luckily, I think we are all moving into a multi-prover. For example, we at LambdaWorks have both a Plonk prover, a Stark prover. So we want to give the user the option to choose which one is best for him.
I would say regarding interest in Nova-like IVC constructions from our side, it's like, well, funny thing is that the paper you mentioned, folks are doing this over pasta curves. We did this a little bit earlier in terms of just, never published. But anyway, it's like, and we faced the same issue you mentioned. So it's like, yeah, I mean, it's like, it's the thing. But anyway, it's like, doesn't matter. It's like, well, Alyssa will give a talk about some of our efforts in this field, I guess, like, I don't know, 10 minutes or something. So yeah, just that's going to be the answer.
For sure. Awesome. Any more questions from the audience? Oh, we have one more back there.
Okay, so I kind of wonder what's your guys' opinion on Lasso and Jote, and which is a like newly proposed ZKVM architecture.
Yeah.
It's not really a ZKVM architecture. It's more like the approach of proving the lookup table structure instead of proving the actual execution. So it's like, you know, just one more level of indirection. So that's basically like what it is. And I mean, looking into it, haven't done it yet. Just, you know, taking a look at it.
So that's all the time that we have, unfortunately. But thank you all so much for coming to the panel. Thank you to our panelists, and hope you all have a great rest of the conference.
Thank you. Could I start? Yes? Start? Okay. Hi, everyone. Mm-hmm. 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 Hi everyone, I'm Alisa Chernyeva. I'm head of research team at NIL Foundation. We're mainly focused on the development of our proof system placeholder, but for a few last month, we tried to combine it with ZK-EVM type 1. And for today, I want to talk about, firstly, I want to give you some definition of type 1 ZK-EVM, just remind. Second, I wanted to talk about modularity inside our proof system placeholder. And after these things, I just give you some conclusion. Okay, first of all, I want to remind you what exactly mean type 1. So it would be like full compatibility with Ethereum side, and it would be like the same structure, the same hash function, the same state, all of these things. Also, we keep original gas cost and have full bytecode compatibility. It's pretty obvious. If we have ZK-EVM type 1, we would have type 2, type 2.5, type 3, type 4. But with each version, we have a little bit downgrade, and sometimes we cannot use all functionality inside EVM. So does it mean like, they give me some simple example. It's like if we can change for another type ZK VM, change hash function, and build another Merkle tree, but we cannot link it inside the smart contract to another hash function because, yeah, it's pretty obvious. We build it on the top on another hash function. So we try to keep full compatibility with layer 1 application. So also we have a problem inside this thing. So let's try describe it in some not simple words, but it's short representation. It's like we try to prove unlimited instruction in the worlds of finite circuits. So we would have some program, like here written. We have some unknown length. It can be unlimited. But what is the matter? We have finite set of instruction. So we know where is what exactly is this instruction, but we don't know how would be length, what exactly instruction was be used. We don't know it in advance. So what we should do? It would be not so complicated algorithm, but firstly we need to split our programs in some several blocks. You can think about it like in the simplest way, it would be one opcode, one circuit. For example, we have exponentiation instruction, we have expectation circuit. But at the simplest way, sometimes it's better combine it into some high-level circuits with a similar operation. How we can show it? It would be like memory circuit. It can be arithmetic circuit, which contains inside, for example, some multiplication, addition, and we can have hashes circuits and other things too. So, and the last thing, when we get all intermediate circuits, we need to aggregate it into one proof. We have a pretty obvious technique for this. It's a lookup argument. We have as a result of one circuit its lookup table, and we use it in another circuits. So what's the really problem here? It's a problem what we don't know how to split it into programs, and we don't know how it's better to aggregate it. For now, it's a complicated task. And another one questions, if we have some changes inside the VM, or we have a new cryptographic primitive for proof system, what we can do? We need to, I don't know, write by hand new circuits. What we should do? It's an obvious question, but I tried to answer for them. So I wanted to go to second block of my talk. It's about placeholder. What's it exactly? Placeholder, it's a modular type of zero-knowledge proof system based on Planck-style arithmetization with custom gates. And I know what you know all these words, except one. It's about modularity. And it means that for now, we have different proof system. And all of them have some kind of constant design. It has one commitment scheme, one field, one of these things. What I try to do, we try to combine all sub-blocks inside the proof system in one proof system. So what we can change? We can change trust assumption. We can change field, lookup techniques, different approach to gate generation, how we can build a recursion. We have a full compatibility with EVM verifier. And also we have different approaches for public input. So how it will be look like? Like you use our nil tool chain, and you just write your desired properties and get a result. And if you want to another properties, you can just rebuild it. So let's look in the details, what exactly I mean between these parameters. So firstly, it's a trust assumption. Basically, it's just a choice of commitment scheme. For now, we have two options. It's LPC and batch version FKZG. Yeah. For KZG, it's always chip verification, but it has universal trusted setup. For LPC, we don't have any trusted setup, but it's not so cheap, really. But we can achieve some trade-off between proof generation time and verification cost. And when I say verification cost, Obviously, I mean cost in gas. Second option, it's a fields, and it's almost based on your previous choice about commitment scheme. So if you choose LPC, you should take some field, and one of factor would be big power of tool. So for this case, we use Palace field, but you can switch it into another fields with property. And for KZG, we can use any field of pairing-friendly curves. So also, we have different lookup techniques. For this slide, I write all of them, but we don't have all of them inside the placeholder. It just maybe you know something about it, but you don't know another one, and it just shows how I try to split it into cases. So, first of all, we have one approach which depends on main assignment table size. Main table size, it's a circuit table, usual circuit table. And when I say it about here, it's lookup table size depend of main assignment table size. Second one doesn't depend. So it looks like what second approach always would be better, but it's required to use field of pairing-friendly curves, and sometimes you cannot do it if you don't want to use non-native arithmetics. So what we have in the placeholder, we have our own generalization on lookup, and for second, we have a lasso. Also, we have different gate generation technique. First of all, it's a usual Plonkish custom gates like Turbo-Plonk, just polynomial constraint, copy constraint, all of these things. And the second one, we use IVC Plonkish. It's maybe you hear about like Nova, Protostar, all of these things. And sometimes it's better to use IVC Plonkish, but not always. For example, we say it's about the KVM, so I try to give you example with opcodes. So it wouldn't be better if we use some addition, just simple arithmetic, yes, it would be better to use IVC Plonkish because it's a very small block. But if we think about Kichak, it's pretty big, and if we have a pretty big total amount of repetition of Kichak hash function, you should better to use IVC Plonkish. So, and last two things inside placeholder, we have general recursion support. For independable circuits, I mean when output on one circuit it isn't input for another circuit and we do not execute it in parallel, so it's like usual prover. But if we have some intermediate variables, it becomes more complicated, and we need to get a new structure. We call it like shared public input. So you need to use another Merkle tree for additional columns. It's not so easy, but we have dependable circuit support. And last thing, it's about public input processing. Sometimes we have a big public input, and we can know to send it in the Ethereum directly because it would be cost not so cheap for us. And we use, in this case, hash input. So in the public input, it would be just hash. And we need to prove inside the circuits all Merkle tree from this public input what it exactly has with Merkle root. It's not cheap in the circuit side, and in this case, we need to use recursion support, but it's work. And you would have cheap verification. It was all about exactly proof system parameters, but it's not all about it. Also, we have flexible circuit technique. It's work with the KLVN compiler, and how it's look. We have some trace constraints. It's like usual circuits constraints. Maybe you hear about like gates. They express it like polynomial form, permutation when you have just two cells, lookup when you have some set of cells and you prove what exists in some lookup table. It doesn't matter what exactly, but it's usual our trace constraints. Let we have some metric function, which would be take some set of primitives and would be returns with set of constraints. When I say sets of primitives, it's like you can think about like predefined circuits, something like that. Okay, in the like all algorithm would be looks like this. Firstly, we use the KLVM. We get some source of C++ code, maybe Rust code, it doesn't matter, and we get a set of primitives like output. After this, we use our metric function, which try to get better. For example, it's try to get better gate degree. It try to get better which cells we need to use, how many columns we would be use. It try to optimize state size, all of these things. So in the second step, we get all these trace constraints and all parameters. After this, we take each primitive. For primitive, it can be like hash circuit, for example. We take hash circuits, we take all these parameters from metric function, and we get some mini circuits. And after this, we get mini circuits from each primitives, combine it together, and we get a result for proof system. We get full instruction in the better way, and it would be created like automatically. We don't need any handwritten circuits. So let's get me like some results. I tried to say it in some words when I discuss it, but I want to get it you more clear. So look like this. Sometimes Ethereum virtual machine can be updated. We can, for example, get new opcode, new something, and for now we should to create by some circuit designer a new circuit, and it can influence on all architecture of the KVM, and it's not so good. And with our flexible circuit technique, which looks like this, we can load it in the KLVM without any handwritten circuits and get a result. Secondly, if we have some new cryptographic primitives, for example, like new lookup argument or something else, when we add it in the placeholder, you should just rebuild it. So what I want to say, if we have any changes for proof system, for EVM side, we just need to rebuild it. We don't need to create a new ZKVM. We don't need it with nil toolchain. And the last thing, it's more minor thing, but I just wanted to say about it, because for now, when we try to build ZK EVM, we use different proof system, and how it's our placeholder is more modular proof system. We just take another parameters, and it gets us usability. So as a result, in one sentence, my final words, with nil toolchain, we can achieve automatic upgradable ZK VM. Thank you. Maybe you have any questions?
I'm just curious, you mentioned so many techniques, but everything relies on Zippel lemma. And there's got to be something else. For example, if I change one bit in my computer, it crashes. So is there any research that is just outside of this Zippel lemma, relying that two polynomials will differ, etc.? Is there like anything completely different from this, or is all ZK based on that?
Could you please repeat about what you definitely talking? I don't hear you.
Oh, you didn't hear?
About exactly gate generation?
No. Just, you mentioned a lot of proofs.
Yeah.
They're all relying on Zippel lemma. It's basically how two polynomials of low order will differ if I just change one value and the whole thing crashes. But in my computer, if I change one bit, it will crash too. So there's got to be some other technique outside of polynomial Zippel lemma, relying on Zippel lemma. Is there any other research? I'm just asking you because you mentioned so many techniques. Have you stumbled upon any?
Yeah. If I understand you correctly, you mean what if we try to create a new thing inside, add new feature? Yes. Add new feature, it would be crash everything. Yes.
No. Are there any other
Or if
ZK-proof systems that don't rely on polynomials? Like everything we hear so far is Zippel lemma, polynomial, everything. Is there anything else, any other? Yeah.
Pretty hard to hear from this side.
Should I repeat again?
You can go to me after this call and we discuss it.
I'll come. Yeah.
Yeah. Yeah, we can talk here, yes.
Can we have there? Okay. I'll introduce you to Francisco Algaba from Giza, please.
Hello, everyone. I'm actually going to talk about Orion, and you will know very soon what it is, what is the vision for what we are doing with Orion, the benchmarks, and the future outlook for it. Basically, Orion is an open source framework for doing CKML, or validity ML, and we open source this framework for the community so they can create their own verifiable models, so they can create a new set of new applications for the blockchain, like new primitives for DeFi, like yield, enhancement strategies, risk assessment, etc. We have a whole ecosystem around Orion. We have the framework itself, that is the open source tooling. We have the hub, that is the collections of tutorials and things that the community makes. The academy, that is how you can start learning. Orion, the tutorials, how to build your own neural network, how to start integrating it into your protocol, etc. Then we have the toolbox, that is, okay, given this framework, how can I easily integrate it into my other tooling? So we have there some tools that can help you out. And this framework is built in Cairo, that is this verifiable programming language that is made by Starware. And we build all the primitives so people can build the right functionalities, like if you know something about ML and PyTorch, we have a very similar API where you can have the same developer experience for building these primitives. For example, we provide tensors built in, so anyone can build tensors the same way they can do it in Rust and with PyTorch. We also have all the primitives already built for neural networks. So you can have all these linear layers, convolutional layers, ReLU activation, softmax, all these operations that are very well used in the ML community to create these models. You can also have it, you can build it, and create your own model. But it's not all about neural networks and tensors. We also support machine learning algorithms, like we support XGBoost, decision trees, random forest, and you can just bring your model that is trained and convert it into Orion, and basically you can have the same functionality, but in a verifiable way, so you can use it whenever you want. Aside of Orion, that is basically focused on the inference side of the pipeline for machine learning, we also have the right tooling for building these solutions. So you don't need to build in Cairo if you don't want to. So instead of that, you can just code your Python code, use PyTorch, TensorFlow, your Firebird framework. You can build your model. You can train it on your data. You can build your solution. And once you have your model saved, you can use the CLI that we built to convert this model directly into the Cairo representation. And once you have this Cairo representation, you can execute your verifiable model, you can generate the synchronous proofs, and you can verify them on chain, and you do whatever you want to do. Aside of that, we also manage all the end-to-end lifecycle of models, so it's not just about generating proofs and verifications and transpiling models, but it's also about solution and scaling, so you can very soon will be able to deploy these models as well as a service to create inferences. And very recently, we started working on what we called cost of Orion. That is, okay, what is the actual results and benchmarks for executing these models and the proof generation time, what is the cost, and what is the gas usage. And for these benchmarks, we use the Lambda class prover that is called Platinum prover. We use it as the baseline for generating these results and these benchmarks. And what with these benchmarks we try to make is we create a depth benchmark where we basically assess with different depths for simple neural network what is the cost of generating these proofs and verifying them using Cairo. But there is like some disclaimers to take from all this benchmarking. The first one is that the prover is not optimized for performance yet. It's like the initial version that they released. There is no enhancement, so it's more focused on stability at the moment. It's only used in CPU. There is no GPU acceleration or anything like that. As well, the programs that we generate, the Cairo programs, are not parallel executions, at least for now. So it's everything single-threaded and single-core, and just to take in mind. So you can see, like, we can, in this benchmark that we did, till 50 layers of neural networks, that is the same size of a typical computer vision model, that, like ResNet 50. We can execute and prove the inference in like 20 minutes and verify in 10 using this initial Platinum prover implementation, but it's getting better day by day. So what are we working on in order to improve all this performance? We have two sides. One is the prover side, and the other one is more focused on the execution itself and the framework. And we have basically 4 main things that we're implementing in terms to improve the performance. One is MLIR. We are working also together with Lambda class in this framework that is Cairo to MLIR. So we can execute the Cairo inference directly in MLIR. So there is like no performance downgrade. It's like you can use CPU, you can use CPU, you can use whatever you want. It's highly parallel, and asynchronously, we can generate the synchronous proof associated with that. So it's not like synchronous, not anymore, and you can have the best of both worlds. Also, there are like prover improvements, like Lambda class is creating an amazing prover, and by the end of the year, it's expected that the performance is like a 10x improvement. So like very good prospect in that side. Also, we are looking into pipeline parallelization, and it's like how, without changing anything in the prover, we can optimize the execution so it's faster. And in this way, we are like applying different techniques like pruning and piping, that is how to parallelize the execution of the multiple layers of the neural network with just setting different workloads for activations during the inference. So basically, we are splitting by layers the execution, and you can execute these layers in parallel, so the execution itself is faster. So it's like some kind of recursion-like for the execution of the inferences. And then is the Cairo compiler, where, as you probably know, there is the Cairo VN that is like more focused for the blockchain, but we are working in the compiler to integrate also new built-ins, so are not like blockchain focused and are like more for ML, so we don't need to execute in a naive way the executions depending on these blockchain-based operations, so we can have these built-ins specifically built for ML. As you saw on all these previous slides, Orion is very related to Cairo, but we don't want this to continue the same. So we want to expand how people build verifiable machine learning. And right now, like, you have all these Python libraries like scikit-learn, like PyTorch, Hugging Face, and on the other side you have all the CK DSLs like Cairo, Circom, Halo 2, etc. But there is no way to mix them together like in an easy way. So that's why we are building Orion, so we can bring all these different libraries into multiple CK backends, so people can use the solution as they want and use the backend that they want for the solution. So for that, like very soon, like by the end of the year, we're going to expand the Orion ecosystem into more CK frameworks to not only Cairo, but also Noir, RISC-0, and Ezekiel. And you can interact with all these multiple backends for the Orion ecosystem using the CLI if you don't want to write any kind of model in these frameworks, and you can just build your model in Python and that's it. You can convert it into any of these multiple backends, or you can build your own model using our Python SDK that is going to be released soon. So you can build the models instead of using the CK DSLs. You can use Python, and you can create your whole workflow for creating these actions on chain for models. And that's everything. Thank you very much. Any question? Good. Good. Thank you.
Okay, I leave you now with Diego Kingston from Lambda class.
Okay. Thank you, Leandro. So I will be talking a little bit about improving current Stark provers and some of the strategies we have, since, well, we are here to discuss SQL acceleration, and that can help us a lot. Of course, as we will see, that will depend in the use case we have and in identifying correctly the bottlenecks we have in Stark provers. So this is an outline of my talk. First, I will be giving a brief introduction to Starks in case you don't know, so that you know exactly which parts compose the protocol, and then we can discuss how to improve them. Then a little bit about Stark Platinum, which is our prover. In the previous talk, Francisco mentioned he's using it, so we are super happy it's gaining acceptance in the community. Then we will discuss some areas where we can improve performance regarding field arithmetic, hash functions, proof size, and lookup arguments, and then finish with some conclusions. Okay. So what Starks? Starks are simply scalable, transparent arguments of knowledge. This means that these arguments of knowledge do not need a trusted setup and are conjectured to be post-quantum secure, and that the proof can be verified much faster than naive re-execution. So what are the ingredients or the steps for Starks? First, what we need is an execution trace of the program, which is a table containing the evolution of the registers at each clock cycle when we execute the program. Then, for those transitions to be valid, we have a set of polynomial constraints that are defined over the trace, and these are called the algebraic intermediate representation of the program. Then what we have to do is show that the trace satisfies these constraints, and to do so, what we are going to do to be able to prove it in a succinct way is interpolate the trace. So what we are doing is encoding each column of the trace as a univariate polynomial. And to do that, we have to do it efficiently. We are going to use the FFT. Of course, that forces us to use what we call FFT-friendly fields, which are fields containing a large subgroup whose order is a power of 2, a large power of 2. Okay? Then, to commit to those polynomials, we'll have to build Merkle trees from the evaluations of that polynomial over a larger domain. And again, there we will use, to build the evaluations, the FFT, and then Merkle trees, for which we need hash functions. And once we have these polynomials, in order to prove that the constraints are satisfied, what we need to do is, first, compose the trace polynomials with the constraints, so as to enforce the constraints over the trace, and then divide the constraints by the vanishing polynomial over which those constraints are satisfied. And once we have that, in Starks, what we have to prove is that that quotient is in fact a polynomial. And to do that, we are going to use Fry, which is simply a fast-read Solomon interactive oracle proof of proximity. Okay? So, Stark Platinum is our implementation of a general Stark prover. You can see the repo over there and follow all the developments in LambdaWorks in our channel. It's written in Rust with focus on security and performance. You can use it to prove code written in Cairo. There is a special folder which contains the Cairo error, but you can then also use it to generate your own error, and we are currently trying to build a drop-in replacement for Winterfell. And we are working towards full compatibility with Starkware Stone Prover, so that then you can verify your proofs with the L1 verifier. So we saw that one of the things we have to do is FFTs, quotienting, and all that. All that is related to field arithmetic. So the original Stark prover works over a 252-bit field, and the best arithmetic we have is Montgomery arithmetic. And, well, we are constrained to use FFT-friendly fields to compute efficiently. So, of course, this does not give us enough freedom to choose maybe other types of fields. But right now, the idea is using smaller fields, such as mini Goldilocks or Mersenne primes, which have special reduction formulae. And that way, we can compute everything faster and also use less memory, especially when we try to represent things in the VM with a field element. Here we can use, if we use mini Goldilocks, we can use 64-bit registers. Of course, one drawback of using smaller fields is that then to get to the desired security, we have to extend it. And so we have to work with extension fields, which adds a little bit more complexity, but nothing else, okay? And to use these smaller fields, of course, we have to make some small changes to the VM. As regards to hashing, especially when we want to do recursion, we have to prove a lot of hashes. So one thing we would like is to use arithmetization-friendly hashes, such as Poseidon or TIP5, but the problem is that these hashes are much slower than traditional hashes such as SHA-3 or Blake. Of course, maybe with some help from hardware acceleration or specialized instructions, we can get much better with these hashes that especially contribute to a significant overhead in the Frey protocol. Of course, what we can do in the Frey protocol to avoid all these commitments is try to skip layers, which means committing to every second or third layer, for example, reducing the amount of hashes the prover has to do. Finally, regarding proof size, well, there are some optimizations that avoid sending elements that can be directly computed by the verifier from information the prover has already to send. Another thing we saw is that in the case of the stone prover, we have to send 2 evaluations per query from every layer. And if we group both evaluations in the same branch, then we reduce the amount of authentication paths that we have to send. Of course, another advantage is using page inclusion proofs, which reduces also the number of hashes that have to be calculated. And of course, in the case of the Fry protocol, it can be interesting to skip layers. And originally in Fry, one had to wait until one reached degree 0. Of course, we can make some optimization by finishing before it reaches degree 0. So those are some of the tricks you can use to reduce proof size. Another one has to do with, of course, the serialization format, and we are working towards that. And, well, another important thing is when one tries to prove things with the VM, there are some operations that cannot be expressed efficiently as VM instructions, and so maybe we need like a specialized coprocessors, for example, having, in the case of StarkNet, you have built-ins for the operations of elliptic curves and signatures and hashes. So, of course, right now the problem with these built-ins is that we have static layouts, meaning that we have just one layout, and meaning, for example, we have this box, and if we want to send something this small or something this large, we are paying always the same cost. So maybe by switching to dynamic layouts, we can get much better for users not wanting to do specifically blockchain operations or blockchain-related applications. And also we could use maybe something like chiplets. For example, that is something that the Maiden VM has. Of course, one of the main costs here when we want to check either the built-ins or the memory consistency is related to the grand product check. So we have to do a lot of sorting of large vectors, maybe computing some inverses. So in general, this is like quite expensive. We can get, of course, much better by using new techniques. For example, the logarithmic derivative lookup offers some advantages for some commonly used operations. For example, one operation one has to do a lot of time is rain check. And in the case of the Maiden VM, when they switched to the logarithmic derivative, they reduce the amount of columns the prover has to commit to, and that reduces also the calculation time. And right now, or a few months ago, we had like an improvement with LogUp by adding the GKR protocol to prove the lookup. So we expect that this will mean a significant boost to the provers. And well, finally, a word on security. The security in the case of Starks depends on 4 parameters. The first one is the field size. So as long as the field is much larger than the evaluation domain, we are on the safe side. Of course, if we use smaller fields, we are forced to work in general with degree 3 extension fields. Another thing is the hash function, but in general, what we have to do is just use the correct digest size. If quantum computers were to appear, then we would have to increase the digest size to the double, and that would double the proof size, but that is something that at least we can live with. And then there are like 2 things that determine the final security. One is proof of work, which just increases the cost for the prover to generate favorable queries, and the other has to do with the number of queries. So each query more or less achieves bits of security, but well, that depends also on the margin and the assumptions you want to take. If you want to use provable security, then you need to do lots of queries, but you are always on the safe side. But most of the projects have been working with conjectural security because we still don't have like a better bound. and so far they've been working really, really well. Okay. So thank you very much for your attention, and if you have any questions, happy to answer.
Thank you, great presentation. I wanted to quickly ask about the benefits of using chiplets versus built-ins.
Well, the problem right now with built-ins, as you have them in StarkNet, is that you have like fixed layouts. They were optimized for the operations StarkNet has to do, but really if you want to do something else, maybe those layouts make you pay a significant overhead. With chiplets, you have a different ordering, and if you see, for example, in the case of the Maidan VM, first they put all the information from the hash chiplet, then the elliptic curve, and so maybe that gives you like a nicer trace to prove, but we hope that we can, after we achieve compatibility with the StarkNet prover, we can then move on to implement some other layouts so that you get specialized provers to prove your application and not just StarkNets.
Thanks.
Hi, Christian here from Dateo. You mentioned on your hashing slide things like Poseidon being arithmetization friendly, good for recursion, but much slower than SHA-3, for example. Now there's a new hash function just a few months forward called Monolith that gets the best of both, right? Similarly nice as Poseidon, but the same speed as SHA-3. Isn't this a bit of a game changer for you also?
Yeah. In fact, we are implementing it in LambdaWorks. One of our interns said, I want to add that, so now we are going to try and play a little bit with it. Luckily, we get the best of both worlds.
Great to hear, thanks.
Well then, thank you very much.
Okay, thanks, Diego. Well, coming up next, Roshan from Marlin.
Hi. So I'm Roshan from Marlin. I'm a researcher there, and I'm here to talk about like proof markets in general and like a little bit more about like Calypso that we're building. So Calypso basically is a circuit agnostic confidential proof market. It lets you like outsource ZK proof computation that today you might do on your own servers or on like your own like users' devices to us. We can do it like much faster, much cheaper, much more efficient since it's like aggregated across all protocols and stuff like that, right? But this is not quite what I'm here to talk about. I'm here to talk more about why you should care about like proof markets in general, right? So let's dive right into it. Show of hands if you guys think like ZK is magical. Yeah, cool. So ZK basically lets you like cryptographically prove any arbitrary computation that you might have, right? And as it turns out, this is like an incredibly like powerful primitive, especially in the blockchain space where you have like thousands of nodes verifying what you're actually doing and probably just one guy who's doing the actual computation, right? So it gives you this sort of leverage where you can sort of offload computation onto one prover who might do like orders of magnitude more computation, but that basically leads to like the verifiers having to do like much less work, right? And like this applies to all sorts of applications that you might see in the blockchain space, like rollups, bridges, oracles, like payment apps like ZK Money and stuff. And like slowly we are seeing the rise of like AI, ZKML, and all this stuff as well, right? But in my opinion, ZK today doesn't really have a good UX, right? And it's mainly because of this, which is like proof generation takes way too long. That's because like ZK involves heavy compute operations, like primarily are like MSMs and FFTs. And it turns out to be like computationally intensive for even like relatively small circuits. Like it's usually like orders of magnitude slower than doing the actual compute itself, right? And given that time is money, more compute time invariably means that proof generation is like incredibly expensive today, right? So here's a few numbers. It's a little old, but on the left side you have like SHA-384 That's usually used in like TLS certificates and stuff like that. On like the zero VM, it took like around 64 seconds on my laptop. On the right side, you have like payment transactions, something that you would see in, let's say, in like ZK Money or ZK Bob or like stablecoin apps like that, right? On my laptop, it takes like around 60 seconds, single-threaded. And if I do it like multi-threaded, it goes down to about like 15 seconds, which doesn't seem that bad, right? I mean, it's not great, but it's possible, right? But it gets worse. It's like significantly worse in browsers. And it's especially important because this is sort of like the most popular like dApp platform today, right? People use it through websites. And the problem there ends up being like you need to execute your ZK provers inside like a JS or a Wasm sandbox. And that means you don't really get to optimize it a lot. Like you don't get access to like intrinsics that let you do like SIMD and stuff like that, right? But it gets even worse. So some numbers for the browsers. You have like 15 seconds that it used to take on my laptop. It now takes like around half a minute to a minute in a browser, right? It's even worse on like mobile devices, which is like arguably the most like important application platform today. And like the market share is only going up every year, right? The main problem here ends up being like the hardware is pretty limited. And you also have like limited battery capacity. It doesn't matter how optimized your provers are. Engineers at Apple and Google make sure your provers aren't going to run that fast because they don't want that to happen, right? And so what was like half a minute to a minute on my laptop ends up being something closer to like 1 to 4 minutes to make a payment transaction, which is kind of ridiculous, right? So, okay, I know what you might all be thinking. Just optimize. You're a dev. You know, why come complain to us? Just optimize, right? Not that simple. For one, software optimization takes a lot of resources. It's very different from the usual software dev job that you have, which means it's like a very different skill set, hard to find people and all that. And like, in my opinion, not every project should even try to do all that. They shouldn't really need to have a CK team, right? Okay, fine, let's say you do get a CK team. It turns out that it's really hard to optimize on common hardware regardless of what you do, right? You usually end up needing like something like GPUs or FPGAs to have good performance. And like developing specialized hardware, for example, ASICs and stuff, are like incredibly risky and expensive, right? So even if you do end up doing all that, at the end of the day, you can't rely on your users having any of that, right? You can just rely on users having like normal laptops and CPUs and all that stuff. So let's come into the real world a bit and look at like how optimization actually works in the real world, right? It usually starts slow. You have some users that are like using your applications, and that basically gives you some demand for like getting faster proofs and a better user experience, right? Given the demand, you hopefully have a bigger target market that your ecosystem can serve with like higher revenues and profits. And that means your ecosystem can basically now justify investing resources into like software optimizations and maybe even like specialized hardware and all that stuff. So hopefully all these investments pay off. You get faster proof generation, and this faster proof generation now gives you like even better UX that makes more users use your applications, more demand, better improvements in hardware, all that, yada, yada, yada. So this is basically like an important flywheel to get spinning in the real world if you actually want to like optimize for your use cases, right? And this is not just theoretical. It worked for Bitcoin, so why can't it work for us, right? Like Bitcoin started with CPU mining, which is extremely slow. It slowly moved on to GPU mining. And we had a brief period in between FPGAs, and like ASICs rule the mining space today, right? And that's because like ASICs are orders of magnitude like cheaper and more efficient today than like CPUs that you would get, right? But this sort of stuff didn't happen in a vacuum. It had to be gradual, and like basically it took time and like intermediate steps to get to ASICs. So, okay, it's fine. Users don't have like powerful hardware. Why not just make projects run their own hardware, right? Maybe projects run servers and stuff like that. That's not as easy either, because I mean, you need precious capital to invest into your servers. You have to sort of like over provision in case like you get a burst of users and all that stuff. You have to manage utilization of your hardware, scaling up and down. You can't really use it 100%, which means you sort of have to like pay for idle resources. And you have to like monitor your hardware, maintain uptime for your users and all that stuff, right? If this sounds familiar, this is basically the reason why nobody pretty much runs their own servers today for like backends and stuff, right? Like cloud services are popular for a good reason, which is that nobody really wants to do any of this, right? So, which brings me to why you should care about like outsourcing proofs, right? And it's basically just these main 4 takeaways that I want you to have. It's that you get much faster and cheaper proof generation because of like better hardware, more powerful hardware, as well as the fact that it's basically aggregated across all applications. So you get like much better utilization and efficiency and all of that. And it gets your optimization flywheel spinning for your specific project as well as like for the ecosystem in general, right? It's much more efficient since like the same compute resources can sort of multiplex between different applications and serve them. And it like puts you on a path towards like decentralization like right from the beginning, right? So, which brings us to what we are building with Calypso. It's a confidential proof market. On one side, you basically have applications that like require ZK proofs to be generated, like payment apps, games, rollups, oracles, all those guys. On the other side, you have like hardware operators who are ready to like provide the compute resources, so like GPUs, FPGAs, even like powerful servers and stuff like that. So you basically get like a lot better resource efficiency. The network is like secured by stake, so if you don't get proofs back, you can sort of slash them and all that. And like usually much faster and cheaper than like trying to do it yourself. So something that's a little unique to what we are building and like what our partners are demanding is privacy, right? That's a really important component of like zero knowledge proof generation. So we basically use like secure enclaves to provide confidentiality and like isolation. So like it's hardware level isolation, and it ensures that even like the host can't really read what you're brewing and all that stuff. It's like pretty popularly available, like built into most CPUs, and like most cloud providers offer it under the confidential computing thing as well. Like NVIDIA recently launched the H100 GPU that has confidential compute as well, so excited to expand there. And yeah, you can sort of like encrypt all of your storage and network as well, so people don't get to see like what inputs are coming in and going out and all that stuff. And it's circuit agnostic, which means like the protocol itself like operates on independent abstractions. It can like support any sort of ZK circuit and ZK VM, and like it's really easy to add like new stuff that's coming on as well. Something that we're really excited about is like common developer tooling that it's somewhat unified across all the ZK circuits and VMs and stuff that you see. Like especially if it like lets you compare across the ZK circuits and VMs and sort of select the ZK tech that best match your use case, right? So this is the main takeaway that you want you to have. It's that if you're currently generating ZK proofs yourself in your servers or like even worse your users' devices, like think about outsourcing it to a proof market. You'll get like better user experience and all of that. And if you're building something cool, Calypso is currently in beta. I'd be happy to like give you access and credits and stuff to get you guys started. So yeah, that's about it from me. You can find us on our socials or like feel free to hit me up at the event outside. So yeah, thank you. Yeah, happy to take any questions if you guys might have. Nothing. Cool. All right. Thank you.
Okay, thanks. We're having a delayed speaker, so we're checking if I can find the speaker. Yeah. You're Jason. We were looking for you. If you can start. Okay, thank you. Thank you. But we have to switch. He's the one that we need to switch because you sent the new one, right? Okay. No, there we are. Thank you for the early start. You can see everything there.
Yeah, do I have a clicker?
And forward, backwards, and a pointer, if you want.
Okay.
Okay. Thank
Yeah,
you.
great. Thank you.
Welcome, Jason.
No mic?
Yeah, here. You need to walk.
Oh, I like to walk. Okay, this is fine. Hello, everybody. I'm Jason from Ezekiel. which is a framework for machine learning with ZK. Before I start, I want to kind of take a moment to think about, with you, about, what are we doing this for? So like, what's the point, right? So imagine that a friendly grandma asks you, what is the problem that you're solving, right? People ask us a lot about our business model and kind of legitimacy of what we're doing. I think we're solving important problems. I'm not sure if the friendly grandma does. And I'd say that the problem that we're solving is basically that people lie on the internet, right? So that is fine and entertaining, but it's also a problem when it comes to financial transactions. And in some sense, the only thing that blockchain is good for is to create a shared collective truth that we can all reference, right? The historical solution has been trusted third parties, right? So if you go back to the 1997 Szabo paper, he was already pointing this out, right? So the thing we start with is we have a mutually trusted third party. We want to do a financial transaction, we trust the bank, right? We want to do an identity transaction, we trust, Mark Zuckerberg. And we've been able to, he envisioned replacing that with a mutually trusted virtual computer. This was almost 30 years ago. We've been building that computer ever since. This is the main working version of that computer, right? This is a trusted virtual thing that we can all share and that prevents us from lying on the internet at the cost of consensus. But, it is still a bit slow and it doesn't do everything we want it to do. And so, the role of ZKML, which I'm telling you about ZK in general, is just to expand the space of things that the EVM can do, from this relatively restricted thing to broader types of computation, much more complex functions. Of course, I'm telling you things that you can do with Ezekiel, which is a particular framework for writing in ZK, and you don't really care about what the EVM can do, right? You care about what you can do, because if you can't get it to work, then it's infinitely slow. So what is Ezekiel? It is, in our opinion, the easiest, fastest development loop in ZK. Having a tight development loop is critical to advancing the space and to exploring all of the ways we can expand that little bit of consensus, the little crystal of consensus that we've built with Ethereum. It's a compiler that turns ML and AI models into zero-knowledge proofs. It compiles from Python with 15 million developers, so we're trying to onboard a lot more people into kind of Ethereum and its orbit. And it verifies on-chain with EVM or in other low-resource environments. We have JavaScript SDK, and we have, like many other folks here, a cloud service that lets you delegate your proofs to us if you prefer. And one of the cool things we can do is you can do everything in a IPython notebook. So you can open it up on Google Colab, you can define your circuit, you can compile your circuit, you can deploy it to the back end, and you can do something else cool, which we'll see in a minute. So yeah, you're specifying your logic, your AI logic or your app logic in general in Python. We're using Rust and kind of our variant of Halo 2, maybe we should call it Halo 5 if we were better at marketing, to turn it into a zero-knowledge proof. And then you can deploy Solidity verifiers. You can use TypeScript and JavaScript on the front end and back end. And if you like, we can help you with proving and serving, but it's all open source. So if you don't like, you're very welcome to run it yourself, and please do. And now we have GPU acceleration, thanks to Inganyama. Okay, but why Python? This is the percent of developers that know Python. This is the percent that know Solidity. This is about 15 million. This is not that large. And then if you go to sort of ZK circuit languages, you'd see the same relationship again, right? So Python is a way for us to access a much broader universe of developers and get a lot of work done quickly. So we make it possible, as I said, to do everything from a Google Colab notebook. You can automate the calibration, the fiddly parts of the ZK to choose your circuit parameters. You can set up the circuit from Python. You can prove, create EVM verifiers, deploy the EVM verifiers, and check that they work. The model definition language is nothing special. It's just you can use PyTorch. You can use TensorFlow. This is PyTorch. You just write normal PyTorch, and then you compile it. You can use sklearn, so you can do traditional data science stuff with it. This is a gradient-boosted tree. And increasingly, you can use more general computation. So this is an example of proving and verifying on the mobile browser with our JavaScript SDK. So these are local proofs and verifies. And one of the fun things you can do is if you don't mind paying a 10x cost, you can verify with the EVM contract in the browser, which is also kind of fun and kind of makes you wonder why not use EVM everywhere. I hope in the future all web apps will be written in Solidity, but we're a ways from there. And if you've been over to the DevConnect venue, you probably used the ZooPass. We also let you program ZooPass itself using Ezekiel. If you want to deploy a new logic to ZooPass, whether it's just a simple set membership proof, which we can support, or more complex things that use machine learning models, you can do that as well. And there's a talk by our team member Casey on Friday about that at Prague Crypto. People often ask us which models work. So lots of things work. It's a bug if it doesn't work. If you can express it in PyTorch or TensorFlow and it doesn't work, please tell us. So neural nets, vision, decision trees, as I mentioned, random forests, and those kind of things, which are very widely deployed in industry and which win Kaggle competitions. We can do transformers and small large language models, which is a bit of an oxymoron. Those are getting bigger and bigger. Nano GPT, when we first launched, it took about half an hour, and now it should take less than 2 minutes. It might be 1 minute at the latest. Self-attention, all sorts of things like that. Classic statistics and data science, descriptive statistics, regression, all that kind of thing. The world runs on regression. And we're doing increasingly general purpose logic like set membership, proof of solvency, whatever you like. We like the AI model, ML model, so we're still sort of thinking through with you kind of how best to extend the logic other than just handing you a virtual machine, which we think is too general to be helpful right now. How fast is it? Okay, so everyone asks how fast and how big. So there is actually no limit on how big anymore because we figured out a way to split proofs up into chunks. So that's not something I can meaningfully answer. But I would say that really what matters is the rate of improvement, right? So GPUs themselves that run neural network models, they double every 2.5 to 3 years in terms of performance or flops per dollar. So as long as we're faster than that, eventually we'll catch the state of the art. And right now we're going much faster. So we're about 18,000 times faster than we were a year ago, and this is actually a little bit out of date because last week we shipped some things that dropped proof time by about 30 or 40%, just algorithmic changes. And that's before GPU acceleration, which we're here to talk about. And in some ways, more importantly, is not how fast is the computer, but how fast is it for you, right? So how long does it take you to build a new app with this? And our goal for that is minutes. Right now it's still realistically hours, kind of hackathon scale, but it used to be a lot longer. So we'd like that to be as push button as possible. And so, kind of our philosophy in summary is, as I think many folks have said, that ZK app development today feels like a lot of math, a lot of custom languages, clever circuit writing. I'm a former mathematics professor, so I love that. If you love that too, please write awesome circuits. If you love it slightly less, this is fun too. This is open source, so you can actually, even if you don't like the compilation we've created, you can dig in and change it however you like. And there's limited targets for proving and verifying. And managing cryptographic artifacts in production tends to explode in your face when you're not careful. So our goal is to make it so you could, in theory, do everything on a mobile phone. Create the model, deploy it from the notebook. We can manage the proof version artifacts for you if you like, and you can prove and verify on mobile or check that it was verified on mobile. Okay, so now finally I just want to talk a little bit about GPU acceleration and our kind of experience with it. I think for everybody looking at this field, right, GPU acceleration is really exciting. It's got sort of great potential for improving the performance of proofs. But CUDA, right? So it's really a pain to integrate, it's a pain to install, and it's pretty annoying. So we're very thankful to the team from Inganyama for helping us build this out for Ezekiel. GPU proving on the good side is super fast, but on the bad side, oftentimes it's closed source, right? So lots of GPU proving is happening behind the scenes. There's a sequencer, it computes proofs. You can tell the proofs are correct, but you don't get access to the GPU bindings. So the GPU bindings are restrictively licensed, or they're hidden behind a cloud in order to protect the business model or revenue. So we kind of say, screw that. Inganamna and Ezekiel. Ezekiel is open source, Icicle is open source, and you can do now GPU accelerated proofs, Ezekiel proofs on your device today, on your laptop, or even in your browser. And what you're going to need to do is normally you would do pip install Ezekiel, and now you're going to have to do pip install Ezekiel-GPU and have a GPU, and everything should work. And I think, yeah, so if you want to check that out, this is a link to a Google Colab notebook in which GPU proving is enabled. So when you go to the GPU, we go to the runtime of the Google Colab notebook, you can select runtime, pick a GPU, like a V100, I think are in the free tier, and you can run through the notebook, and the proof will be computed by the GPU. That's all. Thank you. Yeah, any questions? Yeah. All the way in the back there. Oh, I see. Oh, well, that too.
So you said the GPU acceleration is already available right now? It's already a feature, not testing?
Yeah, it's a feature. If you follow this link, you can run GPU in your browser on a Google Colab notebook. Right
Okay,
now.
I will try. Actually, we just did a hackathon project with your product, but we just
Nice.
ran it on the CPU. It's, it takes time, so we really want to try the GPU acceleration.
Cool. I mean, it varies a lot by circuit right now.
Okay.
And I think hopefully it will continue to improve. You're going to see probably about 50% faster, or like 2x, speed improvement. Hopefully that should start to become 10x, depending on the circuit. But we need to tune it more. And the way we tune is people tell us, I want to run this circuit. It wasn't as fast as I liked, and so we'll figure out, what went wrong. Yeah, so please tell us. Yeah, if it's not good.
Thank you.
Yeah, I have a question. Actually, two questions.
Yeah.
So the first one is, I wonder how you guys constrain the Python scripts in the sense that, like, I wonder if you guys have come up with a way to somehow statically parse the Python scripts and then compile down to Halo script. Yeah.
That's a good question. So to be more precise, what we're actually compiling is Onyx. So, which is a way to record a neural network or other computational graph. What an Onyx is basically you take the abstract syntax tree of the computation and you dump it into a protobuf in sort of the most straightforward way you can imagine, but it is a standard. So PyTorch, TensorFlow output that. When you do a scikit-learn can be transformed into that. Other things can be transformed into that. So that's kind of our intermediate representation, which is a static.
Thanks. Second question. In which part do you try to use CUDA? Is it on the arithmetization part or polynomial commitment part? Where do you use
Mainly
the
on
GPU?
the commitments, the MSM, and TT stuff, yeah.
I see. Yeah.
All right, thank you.
Well, thanks, Jason. We're going to have a 20-minute break if anyone wants to rest and have a coffee. We'll be back in 20 minutes with Lagrange, okay? Thank you. Hello, hello. Okay. Are we live? You have here the clicker, forward, backwards, and a pointer. Okay. I'll introduce you to Ismail from Lagrange.
Good afternoon, everyone. My name is Ismail, and I am the founder of Lagrange Labs. So what is Lagrange Labs? So Lagrange focuses on building proving systems and proving infrastructure that make it efficient to verify large-scale computation over on-chain state. And why is this useful? Well, it allows you to build applications that are far more expressive and far more data-rich than what you can today. So let's take a step back to start with and talk a little bit about verifiable computation, VC, broadly. So verifiable computation, or zero knowledge, as a lot of people like to call it, allows you to shift the safety of a computation away from a lower trust proving environment onto a higher trust verification environment. In the blockchain context, we typically see this embodied in shifting where computation is verified away from an off-chain actor who executes that computation and onto an on-chain verification contract where that computation is verified as part of some application function. So what are the applications of zero knowledge that we're seeing in the blockchain context? And this should really not be new information for everyone at the Zero Knowledge Day. But the early question that we saw people tackling with ZK applications are really, how do we increase the abundance and the privacy of block space? But over the last year, or maybe 18 months, we've seen a new shift away from that question onto a new question, which is, how do we increase the safety and expressivity of computation, the safety of the data we can access for that computation, and the expressivity of the functions that we can run? And this is where we've seen these new generation of ZK applications, the co-processors, the VM extensions, the non-EVM ZK execution environments, ZK interop, and more. And so let's break down both of these new trends that we're seeing. So what do we mean by safety of data access? Well, is the data that an application has predicated its core functions on derived from a source with the same safety as the underlying execution environment? So is my application that derives its safety from Ethereum consensus relying on data supplied by some off-chain oracle? Is a interop protocol core to the function of my application deriving its safety from a proof that's verified on Ethereum consensus or from elsewhere? What do we mean by expressivity of transactions? Well, if we look at the current embodiment of transactions that we see on-chain, they typically are simple exchanges of value or simple state transitions in a contract. When we look at the future state that these new ZK coprocessors or VM extensions are unlocking, these are large asynchronous computations that can be executed elsewhere and verified back in the execution environment. So think of inference of an ML model. Think of query over a large subset of on-chain state. Think of maybe a big data scale computation over historical on-chain transaction, receipt, or storage data. These are the type of things that can run asynchronous and then verified back in the core execution environment. And so this gets to what Lagrange Labs does. So Lagrange's ZK MapReduce stack is optimized for very large-scale verifiable computation over historical storage, receipt, or transaction state. So to put this in the lingua franca of now, think big data co-processing. And so what does this leave us with, and why is this useful? Look at on-chain state today. Fundamentally, what you see is a fragmented data lake. There are disparate application states over rollups, L2s, different L1s, modular context as well. And what you see is that modern applications are unable to query across a meaningful amount of that state. So you can't derive your pricing for your lending app by an analysis of on-chain state. You have to rely on an off-chain feed to synthesize that for you. You can't have a meaningful search over the owners of balances in ERC20 contracts because you can't have sufficient depth on your query. You'd have to iterate through all the owners. And so this is where ZK MapReduce and our team's work comes in. This is a proprietary proof construction developed by our team that is optimized for concurrently proving large-scale batch proofs and dynamic data parallel computation. Things like MapReduce, Spark, RDD, and SQL, the types of things you'd run over your Web 2 data lake, now applicable to on-chain state. And so what this lets you do is to structure proofs that have a very rich relationship with the underlying data of a chain, that have a high depth of historical data and a high breadth of cross-application or cross-chain data that can be recursed or folded together and merged to one composite proof. And so what is required to generate a proof? Really 4 principal components: a block header, or more than one block header, of a source or series of source chains, a specific range of storage slots and block headers you want this computation to run across, and then some computation that's data parallel. SQL, MapReduce, Spark, RDD, something along those lines. And then finally, a verification contract on the destination where you want that proof to inherit its safety from. So how do we do this, and what is kind of the secret sauce behind our proof constructions? So the core of this is a vector commitment scheme our team developed called REC proofs. So we presented REC proofs for the first time at Stanford Blockchain Conference in the summer. And what this enables us to do is to construct batch proofs over very, very large subsets of a commitment, and to have dynamic computation over that data concurrently with the proving of that inclusion. And what REC proofs have, as compared to other vector commitment schemes, is this new property of updatability. And this might seem trivial of why would you want to update your proofs, but we'll very quickly see why this matters a lot when structuring proofs over blockchain data. So think about wanting to derive the standard deviation of an asset between a range of blocks. Let's say block B to B minus K. And you want this standard deviation, so that you can do your Black-Scholes and compute your volatility, to be derived from on-chain dexes rather than some off-chain trust me style source. And so you want to structure your proof such that it proves the inclusion of the prices and then calculates a standard deviation across that range of K blocks. But we're on a blockchain, so new blocks come in. And so 12 seconds or maybe less in a modular context or an L2 context, you would have to recompute this proof from scratch. So you would, in essence, have to remove the oldest piece of data in that buffer and add the new piece of data for the new block, which forces an entire recomputation that's linear in complexity and time with respect to the size of the data you're computing over. That is intuitively not a very effective paradigm for data structures that continually update. So this is where REC proofs come in. You can structure a REC proof over a very large commitment of data, and then you can update the underlying proof when the data that you're computing over changes. So for things with low entropy, like this proof we just talked about over a range of K, you would only have to make a logarithmic time update by removing the oldest data and inserting the new data, and you can change the computation along the path without necessitating an entire recomputation. So proving time is an order of magnitude faster. And so this is very, very good for blockchains because they are in principle low entropy when you look at storage state. The majority of storage slots don't change across successive blocks. And when you're structuring proofs across large ranges of blocks, the majority of that data and that buffer is going to be consistent across the marginal run of a proof. So you don't have to actually recompute duplicate work every time you want to prove something. And so this new principle of updatability in proofs allows you to scale proof computation not through recomputation, but through composition of previously computed proofs. So this gives you an incredibly low overhead on supporting new chains and supporting new computation frameworks without requiring you to have the traditional proving time complexity that naive approaches have. And so we have benchmarks from the paper in SBC, and the first version is 135 times faster on recomputing than naive approaches, but we expect this to be in the order of thousands when we talk about MPT trees, when we talk about production data. And because this is data parallel, and we can go fundamentally, embarrassingly parallel on all of the computation that we do, we can increase our speed by up to 10x by distributed proving. And the verification time, since these are very small proofs that are composed together, is substantially lower too, as is proof size. And so we're going to discuss very briefly a few applications that I think are very relevant when we kind of think about the future state of coprocessors and ZK compute with respect to on-chain data. So the first is something that we like to call on our team digest transformation. So what is digest transformation? Think of this like ETL, extract, transform, load for on-chain data. The majority of data in the blockchain context is encoded in formats that is not friendly for booster rollups or ephemeral rollups or coprocessors to compute over. So what this leaves you with is downstream complexity that gets pushed onto any ZK application that wants to compute something meaningful over on-chain state. What you can do with a digest translation is you can prove that the unfriendly Ethereum structure is equivalent to some new structure that is faster to compute over. So imagine you have a booster rollup that wants to compute over some subset of the MPT tree. Instead of having to continually compute over the catch-ax and the RLP encodings with high proving time, you can simply put a rec proof on top of that entire portion of the tree and iteratively prove that that's equivalent to some, let's say, Poseidon-Merkle tree. All of a sudden, your booster rollup just has to verify the proof from the rec proof and then only has to compute over that new structure. Meaning that you can take the output of our coprocessing and you can use that as an input, in fact, for another coprocessor, booster rollup, or ephemeral rollup. And you can make the second application substantially faster by being able to leverage the updatability of the proofs of the underlying data. So to get to something a little bit more fun, think about verifiable rewards. This is another one we're very excited about. Things like contract secured revenue, where you want to issue sequencer fees or some financial reward based on-chain activity. And you want to do so iteratively without having to push the regulatory issues and the agency issues onto some party who becomes the arbiter of reward issuance. So in these situations, you can structure this computation over large subsets of the commitment, and then you can prove that when relevant. So the next one is another somewhat in the weeds primitive, but it's very applicable to things that use BLS key aggregation and have to prove APK aggregation on chain. So if anyone here is familiar with BLS aggregation, the complexity typically in proving time comes from the aggregation of public keys rather than the verification of the aggregate signature, which is a linear time, which is a constant time operation. And so with rec proofs, you can prove the inclusion of some subset of signers in a commitment, and then you can update the proof of that aggregation as the signer subset or the signer set overall changes. And so what this allows you to do is to iteratively change the BLS aggregation as you change the signer set or signer subset without having to recompute all of that. And that's great for applications where the entropy between successive signer sets or signer subsets is very low. Now, another primitive that we like to talk about is something called full storage queries. Most data in smart contracts today, as mostly the developers know, is encoded in mappings. So you have some index and then a bunch of values, and a bunch of secondary index or tertiary index. So it makes it very difficult to query over anything that isn't the primary index. So if I want to figure out, for example, all NFTs that are blue in some collection, because I have some second-order GameFi application that needs that, you can't really compose with that initial contract very well because the data that you require can't actually be searched. You have your index, and then you have your owner, then you have associated metadata properties, and you can't actually figure out what those associated metadata properties are without just looping and iterating through the entire collection. And this is the same principle with the ERC20s if you want to check how many users have a balance greater than n or how many users' balance has changed between some ratio over the last 2 weeks, 2 months, etc. And so what you can do with this is you can just structure a proof over that entire subset of memory corresponding to the mapping, and then you can just update that proof and compute over it. Finally, you can build some very cool exotic DeFi primitives. I'm not a DeFi developer, or a very good one, but there are a lot of very good ones. And when you can start actually accessing the on-chain data that you use to start deriving things like volatility, standard deviation directly from on-chain state rather than from off-chain sources, it decreases the risk profile substantially of anyone composing with or building with a DeFi application. So if anyone wants to learn more about some of the technical underpinnings behind the talk today, I would recommend you look at rec proofs. the paper that we discussed briefly earlier, as well as some recent work our team put out involving the application of folding to rec proofs in our ZKMR stack, where we turn IVC Nova into PCD-based Nova. So thank you, everybody. And now I think it's time for questions. Questions?
Hi. Do you like the rec proof actually like use the Nova like for underlying to generate the proof?
Yeah, that's a good question. So RecProof supports any proving system that has recursion or an abstraction of recursion like folding. And so as long as you can have the same arity in your proof composition that you have with your underlying data structure you're proving over, then you can use RecProofs with what you're using. So you can use it with Plonky 2, you can use it with Nova, you can use it with Supernova, you can use it with Starkey, you can use it with anything, really.
So I might have one more question.
Yeah.
Okay, for Halo 2, especially for the Halo 2 or PSE4,
yeah.
So it's not friendly with the recursion. So yeah, so I think like it will be a big problem for your project, or you have any solution for this?
For PSE, I mean, I think PSE, so I think Halo 2 doesn't have good recursion time, it has aggregation time. So I don't think that something that requires iterative updates to a proof with this format would be well suited for Halo 2 as a proving system. Mm-hmm. But I think there's other things that Halo 2 can do well.
Okay, thank you.
Of course. Good questions, thank you. No one else?
Well, thank you. We are rescheduling a little bit because we have some panelists stuck into traffic. So thanks to Ola that will be saving our agenda. Thank you, Philip. I'll be spoiling a little bit here. Here, okay. This is you. Thanks, Philip.
Yeah, so hi everybody, my name is Philip and I am the COO of Ola, and I'm here today to give you a brief introduction to what we're building in case you have not heard of us before. We are basically a CKVM team or a CKCKVM team. We're looking to do both privacy and scaling. Oh, we had two screensavers here. So right, a brief background on scaling for Ethereum. There's been many different suggestions to how to do scaling, both horizontal and vertical. We've had different stacks with the OP stack and different CK stacks. And basically how we're different is that we're looking to do both scaling and privacy. If you wanted to, you could even use the Ola ecosystem as a standalone environment and run your own single dApp as a solo chain. One thing that we also, which is kind of out of context for this this talk now, but we did look into the BitVM paper, which was kind of interesting, and we think, so BitVM, by the way, is a paper that was released 1 month ago in October of 2023, and it's about doing peer-to-peer in a two-party setting scaling for Bitcoin, which was kind of interesting, and we did look into applying our VM for that as well. So if you're interested, come to our booth and happy to discuss about scaling Bitcoin as well. So everything we've done so far is about making this as efficient as possible. There's many things, talking about Ethereum specifically, that aren't very CK friendly. And that ranges from different hash algorithms to how we can go about getting the trace, which is what's being proven at the end of the day, as small as possible. So we're running a RISC ISA. Our VM is fully Turing complete, so you can deploy any arbitrary logic on top of it, and gas would be the limitation in terms of what programs you can run. We also, as you can see here, have some CK-friendly hashes in Poseidon 2 and using Blake. So that's a little bit about the VM itself. this might be small here on screen, but basically the bread and butter of our solution is about achieving compliant privacy. And I'll talk more about that, but here is the technical overview. So how a full end-to-end transaction lifetime flow works in our system is that everything in the red here refers to client-side operations. So that would be the end user device. And then we have our nodes here represented in blue. And at the end of the day, the L1 here could be Ethereum, it could be Celestia, it could be any chain. So whatever layer we deploy on, we just need a smart contract where we can send the proofs of the state changes happening in the Ola ecosystem. So just highlighting that this could be any layer. But we're looking to do this for Ethereum first. So in Ola, very similar to other privacy-oriented solutions, you would execute private functions at client side, so at your end user device, meaning you send a partial proof relating to what transactions you've done together with a signature. That's going to be verified on the node side, and the node would then continue with the rest of the public functions to be executed. And then we have some neat tips and tricks here using parallelization. There was some discussions earlier today about Starks versus Snarks. So our CK backend is based on Plonky 2, actually a modified Plonky 2 for recursion. And then we're using Starkey as our block builder. So fully Stark-based at the moment. We're using some parallelization here. It's kind of like a conquer and divide approach where you have specific operations, you divide them, and then using recursion, you prove them all the way up to the top. We also looked into using snarks. So you could use fflonk if you wanted to make the byte size smaller when you submit that to the layer 1. But then, as was mentioned previous in discussions today, you have some trade-offs. You're losing the quantum resistance, and you also have a trusted setup. But there's different ways to go about this. We have not launched our testnet yet. We're going to do that next month. So we'll see what we end up doing. Another thing is that we're using account abstraction. So if you're familiar with the Ethereum ecosystem, this is ERC 4337, if I'm not mistaken. So we're not looking to reinvent the wheel here, but we're not supporting EOAs in Ola. We think that smart contract accounts offer more flexibility to the end user, such as paying gas in whatever token you'd like. So we're looking to utilize the existing tech to make the platform as good as possible. Right. So privacy, this is actually the problem we're mainly looking to solve. And here we are kind of different to other actors in this space. So I'm sure most of you in the room are familiar with the protocol Tornado Cash, which has been a mixer on top of the Ethereum network. And the problem we've seen here is that when you have a complete black box, meaning you have no input whatsoever to what's happening and where the funds go, government and regulatory bodies have an issue with this. So what we've done in Ola is that we're looking to counter this with what we're calling partial native traceability. And I have a slide here showcasing some Merkle trees where we're going to go through how this works. So basically to the far left here, we have the public tree. So Ola, if I didn't mention it before, it's a hybrid rollup. We're looking to support public and private smart contracts, and we leave this at the hands of the developer. So the developer can choose whether or not they want to build a private or public dApp, and the users can choose whether or not to interact with a public or private dApp. So in the system, we have two different Merkle trees. We have a public Merkle tree, and we also have a private updatable Merkle tree. And this is different to some other teams using nullifier sets and decoupling the spending of private inputs and outputs. So in an example here, if you interact in the Ola ecosystem, we use UTXOs under the hood, by the way, just as many other privacy teams. If you imagine that Alice wants to pay Bob, then to the far left here, it's very small, but it says Ola. Then if you would want to pay Bob, and Bob would be what says CM0 here, that stands for commitment, which is basically plain text encrypted data. In that transaction, the only thing that would be visible would be the sender, so that would be Alice. Now, if Bob wishes to make a payment to whomever, now everything's fully private. The one thing that we've made an addition here is the traceability. So the UTXOs, or rather the encrypted plain text data, the commitments, they are linked to each other. Now, this is really a spectrum of trade-offs. So you're lowering your privacy compared to some other solutions where everything's hidden because you can trace the UTXOs, or the encrypted data, but you're also increasing the compliancy of the system. You no longer have this complete black box where you have no clue to what's happening, and if you go into the system and out of the system, you could basically just wash money. So should we realize down the line here, let's say 1,000 transactions later, that the originator Alice wasn't actually Alice, that was a criminal, then we can help and pinpoint to where the funds have gone and maybe when they exited. You could also further, in theory, improve this by having some kind of DAO mechanisms where you can, if you provide enough proof or evidence that somebody might be a bad actor, you could freeze their funds and so on. So we're looking to build this solution where we can bridge the gap between the Web2 world and the Web3 world, where it's acceptable by governments to have these kind of solutions, but we're not compromising that vital end user privacy. So we want to preserve that privacy for the end user. Right, so where are we right now? We launched our POC earlier this year, and we're looking to launch our dev testnet. So at the moment, what you can do on the machine is basically you can run the virtual machine locally on your computer. You can run a simple smart contract, and you can generate a proof for that. What we're looking to do now is to launch our dev testnet coming next month, and then we'll have our nodes operating, meaning the node will take care of the proving and also the verification for you. And you can request that verification back to your local machine. And then a final step would be to have a public testnet where the verifier would sit on top of some kind of test network, like on Ethereum on Sepolia, as an example given. So by the way, if you're interested to come and work with us, we are actively right now on our socials. We have a link. I think I have a QR code for this that you can scan if you want to get allow listed to either deploy some kind of dApp and try the system out, or if you want to try and run a node with us. Right, so everything that we do is open source. So you'll find all the code in our GitHub. One thing that I forgot to mention in the beginning is some of the levels of abstraction that we're doing. So I never mentioned what language we're using. We have our own language called Ola-lang or Olang, and it's basically a Rust fork. So if you are familiar with Rust, you're going to be good to go. It's Rust with the Solidity types. So if you're familiar with Solidity and Rust, you're going to be having an easy time. We're also looking to add kind of high levels of abstraction here. We know that coming in and writing CK dApps isn't easy, so there's no CK DSL components in our language. It's just basically Rust. So there's no need to deal with any circuit writing at all. We have constraints on the VM itself, so the VM will generate any circuit for whatever arbitrary code you want to deploy on it. And yeah, that was it. So I'll leave this up for a second here, and you can scan the QR code, and happy to take any questions. Yeah, don't be shy. One at a time. No? Over here?
Polygon ZK EVM is using Starks just because it's fast, but there's no privacy. And then they're taking the Stark proof and making a Snark proof out of it for sickness. And that's how they work. If you are not using Starks, if you're not using anything that fast, isn't this going to be computationally kind of slower and maybe not competitive on the market?
So in terms of CK efficiency, we've done a lot of research on this, and we've actually pivoted many times. In the beginning, we weren't looking at Starks at all, and then new research came out. We're continuously looking at the best CK option. We looked into incrementally verifiable, well, that's a mouthful, verifiable computation as well, and we can add that as well if we want to. I think all products that are on the market today use some kind of snark at the end of the chain. Even if they're Stark-based, they use a snark. And I think that might be the route or the path we're going down as well, unless we see some breakthrough. But yes, you're altering the security premises then. And I think even Diego from Lambda class said this before, that, I mean, okay, you're losing the quantum resistance, but sure, I mean, the EVM and Ethereum itself is based on elliptic curves, so you need to change out Ethereum in that example as well then. Yeah. Any other questions?
How does Ola compare to like other ZK friendly like EVM, like VMs, for example, the Cairo VM itself in terms of throughput, like as an execution, from an executional perspective, like, so have you like done some benchmarks and compared it with Cairo VM or other ZK friendly VMs?
Mm-hmm. Yeah, sure. So there are some benchmarks on the GitHub repository that you'll find. We have some benchmarks for a Fibonacci sequence. I think we ran that like 1,000 times to, I don't remember to exactly what number in the sequence, but you'll find that on the GitHub. We also actually, mentioning Starkware and Cairo, we also run algebraic risk. We're a risk-based solution, which has taken inspiration from Starkware specifically. We also have some other tips and tricks I didn't mention because in the mean of time here, but we're using, if you're familiar with Starkware and hints, we have a similar concept. It's called the profit in our solution, and that's basically just about taking, instead of proving something natively in the VM itself that's going to be included in the trace, an example given could be the calculation of a square root. Now, doing that natively requires quite a lot of opcodes. So what you could do is you could run like a Python script outside of the VM. It's actually handled by the VM as well. So when I say outside, don't think outside, but the VM could run a Python script, get the result for that calculation of a square root, and then we can just assert it with 2 or 3 opcodes that the result we're getting back is correct. So there's many like tips and tricks and tweaks we're making to make this as CK efficient as possible. Yeah. Well, one last question. I think we have 10 seconds, but maybe the panelists aren't ready anyways.
Yeah. Since you mentioned your UTXO with privacy enable, which we have a competitor which I heard of is Alio, so I would just like to hear from your perspective of your differences compared to Alio and what are your advantages too.
Yeah, so first of all, I think the Alio team they're doing great work, and we're actually good friends with the Alio team. One difference, language level. So for developers, they have a CK DSL, so you need to learn about. So basically, the problem, right? The problem is we have developers here, and they aren't familiar with writing CK dApps. Okay, so how can we lower this threshold? Well, how they went about it is they're taking the circuit components, and they're shoving that into the language as templates for the devs to use, basically, in Leo. So that's a difference in Ola. So instead of taking these circuit components and shoving them into the language, we're taking them and shoving them under the hood into the Ola VM itself. So we put constraints on the VM, and you basically just have your high-level language, and that will compile into whatever circuit you need. So you don't need to deal with any circuit writing into the language itself. So that is one difference. Then another difference is in terms of the Merkle tree structure we were talking about. So we have less overhead in managing fewer trees. And then we have the trade-off, privacy levels. So if you can link encrypted data, that shrinks your privacy by a little, but it increases the compliance quite a lot. So in a fully decentralized world, we think in our team that this is the best way to go. In a hybrid world where you maybe interact with Sexes and other centralized solutions, you could maybe put requirements to, well, you must show your viewing key to ever deposit into this central exchange. A viewing key, by the way, for those who don't know, is a non-enforceable key that relates to your private inputs, but I can't force anybody to reveal their key. They must do that themselves. So there are some complications by doing or going down that route. So these are, yes, some of the few differences between the Aleo team and ours. On a CK stack viewpoint, they're running sexy as their protocol, right? So that's different to us. So there are differences here and there in terms of, the two systems. Yep. Should we, any last? Do we have time? One more question, one final question, or are we good? Everybody's going to build an Ola and go onto GitHub and pull the repo? Yeah. Yeah, so thank you so much. Please try it out. It's super simple. And if you are a developer looking to try something new, happily working with other dev teams, so we'd love to see more traction. So reach out to me. I'll be around here. Just come and say hi. And thanks to Ingo Nyama and also Geometry and Lambda class for helping out with the organization. Yeah, thanks.
Okay, thank you. Well, I need to check where we are. We're having a panel. This one, okay, Seeker Hardware. Please welcome Hamid, Evan, and Rahul. Please.
Where should we sit?
It's 25 plus 5. If you want, you sit yourself or for the people. Okay, thank you for waiting.
All right. So how should we sit?
You should sit here, I think.
Yeah, like under our hand. Okay.
Thanks. Oh. Thanks.
All right. We good to go? All right. So how is everybody doing? All right, great. I know coming toward the end of the day, so hopefully you had some good talks, learned quite a bit. I'm going to act as the moderator, dual duty. I was not supposed to be the moderator, but since we couldn't find the right moderator, so I'm going to kind of be a panelist and also moderate as well. Hopefully it's going to be okay. My name is Hamid Salehi. I'm the Director of Product at Adaptive and Embedded Computing Group at AMD. We have been involved with providing hardware for ZK-proof generation for the past few years and really supporting the community. Last year, we were a technology sponsor for Z-Prize, and this year as well, 2023, we are a technology sponsor as well. So that was a little bit background about me. And before we get started, I want Evan and also Rahul talk a little bit about maybe introduce yourself and then your involvement with on the hardware side, especially with ZK-proof generation, and kind of give the audience a little bit background. That would be great. Maybe I start with Evan and then go to Rahul.
Yeah. Hi, everyone. My name is Evan Marshall. I'm the CTO of DMOX Labs. Our goal is to make programmable privacy as practical as possible. So we're really focused on client-side proof generation. In that vein, we are one of the architects for Z-Prize Track 2, which is browser-based proof generation, optimizing it over BLS 12, 381. And we're probably best known for our wallet, which is the Leo wallet on the Aleo blockchain with little more than 100K users.
Very good. Rahul?
Cool. Hey, everybody. I'm Rahul. I'm currently at Wormhole, which is a cross-chain messaging protocol. Currently, there's a lot of talk about bridges in the ecosystem, but this is something that we've been working on for a while and kind of moving to a ZK solution as well, and that's really where we're trying to take production ZK into the market. My background, I was involved in Z-Prize last year as a participant. I worked on a FPGA MSM implementation that's out there. You can check it out, called Cyclone MSM. I'm also part of the Z-Prize steering committee this year, and really excited to see kind of the implementations that come out this year. It's more focused on the application side as opposed to the low-level ZK primitives.
All right, very good. So I'm thinking maybe first question we go to Evan, and both me and Rahul are kind of more familiar with the server side as far as hardware acceleration goes. On the browser side, maybe obviously dealing with programming GPUs to accelerate ZK proof generation, how is that different, comparing it to what we do on the server side and, in terms of developer ecosystem, programming GPUs, type of devices, obviously, what can you share with the audience?
Yeah, so a bit of background. A new standard was released as part of Chrome 1.13 in May of this year called WebGPU. And WebGPU is trying to solve the problem of enabling browser applications to access the GPUs and provide a single universal interface. The language, like Wixel, is most probably closest related to Metal. And it's getting, crypto wasn't the original inspiration for it. It was probably either gaming or machine learning, but it's getting more stable over time as the spec continues to get implemented. I'd say the biggest difference is that you can't really assume details about the chip that you're working on. So a lot of the optimizations that we see in other contexts don't necessarily carry over, but you can still get massive improvements by leveraging GPUs for things like MSMs. So I'd say right now the standard is not fully implemented, but it is part of Chrome Stable. So it is something good to try out, but it's not a lot of the safety features you don't necessarily get. Like right now, you don't know how much memory is currently being used. You basically have to try to allocate buffers and see what happens. So it's still in somewhat of a new stage, but it's a really kind of exciting technology for web applications.
That's awesome. So kind of going back to Raul, kind of same thing, but on the server side, for somebody who wants to start thinking about doing hardware accelerations on FPGAs versus GPUs, both different primitives, or creating a more complete proof generation. Maybe share a little bit of your experience. Obviously, you participated in Z-Prize last year. Maybe walk us through that process a little bit.
Sure. So the hardware platform that we were at least focused on was the FPGA, like Xilinx FPGAs. So we used, at least for the MSM implementation, the AWS F1 instance, but for the sort of NTT, which is a core part of other proof systems, including Starks, the C1100 was the provided FPGA. There were a few challenges, obviously, with trying to take some of these proof systems or these primitives onto something like the C1100. Namely, really was the main issue was really the data bandwidth issue. Not that the FPGA couldn't compute fast enough, which it can. It's sort of that when you try to move data from your host to the FPGA, if the data bandwidth isn't high enough, it doesn't really matter. If you can do your NTTs quickly, you just won't be able to get the results back in time. So that's something that this year's Z-Prize, and I think lots of folks in the ecosystem realize, and kind of trying to expand the data bandwidth and use better versions of PCIe, which was quite difficult to use previously.
All right, great. And then there was a question I'm supposed to ask myself, basically. And the question is, I presented this morning about different type of hardware, FPGAs, GPUs. And the question is for people who are actually creating proof systems, what do we see as AMD? Obviously, we support quite a broad set of partners, startups that are trying to generate hardware to do zero-knowledge proof acceleration. And what we see currently for people who are actually thinking about creating systems that are going to go in production is, and I mentioned this morning, really the mindset have to be, how do I create a complete system where you can accelerate the entirety of the system. Focusing on one single primitive necessarily is not going to help you much, no matter how much you accelerate it. And typically, creating this more complete system that accelerates the entire proof system, first of all, it could involve more than one FPGAs. It could involve a combination of FPGAs and GPUs. There might be primitives that it's much easier to accelerate them on GPUs, and certain primitives might be easier to accelerate them on FPGAs. And also, not all FPGAs are equal as well. So you have different types of resources, obviously, in addition to what you get in terms of fabric logic cells in an FPGA, you have access to different math engines, DSP engines, AI engines. As a matter of fact, there was a very interesting work by Ngonyama that was just released that showed that some of our newer FPGAs that give you access to our AI engines could potentially have significantly better performance compared to previous generation. So really, if you are thinking about a more serious project, creating something to accelerate the proof generation, you have to think broadly as far as how you can accelerate the overall application. We say whole application acceleration, and then what type of resources you need and match that to the available GPUs, FPGAs, and also look at the roadmap, what's going to come out in the next 12 months, and pick the right hardware, because that's extremely crucial to make sure you have really viable hardware acceleration. So now that we kind of got that out of the way, so going back to Evan, so there is a question in terms of, I guess it's a two-pronged question. One is for people who want to get started, especially on the client side. What are the pitfalls? How should they get started? What should they think about as far as developing an application?
Yeah, so we open sourced a repository that was kind of joint work between Aleo and Aztec in terms of like it's called WebGPU Crypto. You can Google it, or maybe I can get a QR code somewhere later. But I think that's a good place to start. You can kind of see that, get some idea of the benchmarks and what it's going to be like. I'd say in terms of optimizing your proof system for web-based clients, it's a really difficult problem in the sense that you don't control the execution environment. So you're always going to need some sort of like WebAssembly backup for if things go wrong in the GPU. I wouldn't rely entirely on the GPU. And there are things that aren't faster in the GPU. So that's another thing to consider. And you also have to consider like the relative power on someone's machine, where if you're dealing with a powerful CPU and there are only GPUs, like an integrated chip, it may not be worth it. So building in the engineering is a really big challenge. It's not just the algorithms, it's, as you were saying, the entire system. And then in privacy applications, things get a lot tougher, but that's kind of I think the motivation for client-side proving until we get some of these fancy MPC networks built for private proof delegation.
All right, no, that's a very good point. A lot of people ask me, about hardware acceleration, and my first answer is, first you have to establish you actually need it. Because a lot of time, especially with CPUs coming out with 96 cores, you might not even need an accelerator. So you establish that, whether it's throughput or latency, or make it cheaper, and establish that, and then figure out how you're going to harness some of the power of GPUs and all the rest of it. It's a great point, Evan. So going back to Rahul, so obviously last year you participated in Z-Prize and to accelerate some primitives and FPGAs. Now this year being part of Wormhole and now thinking about hardware acceleration in a different context as far as for an actual application in production, maybe talk to the audience a little bit about that thought process, that how would you decide whether hardware acceleration is needed, or how would you go about it?
Yeah, so I think first of all, like you guys are both right, which is first you have to decide whether or not you want hardware acceleration, and we didn't start in mind with, okay, we're going to take whatever primitives we're building and we're going to hardware accelerate them. I think that's definitely the wrong approach. We built our system, and then we benchmarked it. We said, here's the constraints of our system if we run it on this machine versus this other machine, all CPU based. And we decided, okay, at this point, because our application is extremely latency sensitive, users who want to use this cross-chain messaging protocol aren't going to wait an hour or 2 hours for either for their messages or their assets to move cross-chain. So it's extremely important that in this competitive market where there's lots of different cross-chain messaging protocols and bridges, that if you're going to offer a trustless solution, that it'd be competitive with any other validation mechanism or verification mechanism that's out there. And so if we want to make it as competitive as, let's say, like a multi-sig approach or as an optimistic approach, we really need to be as close as possible to the actual consensus of the relative source chain. And so hardware, I think, does provide a lot of benefits, but it's still unclear, which parts of the proof system, add the most benefit. I mean, you still run into, Amdahl's law, which is, I think, the core crux of trying to accelerate anything, and deciding which components to accelerate is still still remains a challenge. Deciding even which platforms to use, FPGA versus GPU, deciding which components I want to put on the FPGA, which components I want to put on the GPU, that's still also an open question for many applications. And so that's part of navigating whether or not we want to use hardware acceleration for this component, or maybe for signature verification, or maybe we want to use hardware acceleration for hashing. And so there are a lot of trade-offs that have to be kind of defined before you can move forward.
All right, great. Thank you, Rahul. So going back to Ivan, there are questions about standards, right? Libraries, standard libraries, APIs, and obviously the ecosystem right now is quite fragmented in terms of what's available. And for somebody who wants to get started developing higher-level applications, it's a little bit of a confusing environment. I'm curious, what's your view of when is the right time to create the standards, and how far are we from it?
Yeah. Given the rapid evolution of proof systems, I actually think the fragmentation is somewhat necessary because we don't know what's going to happen. We started with snarks, and everyone likes the constant size proofs. And then for some reason, even though the asymptotic complexity is worse, snarks seem to be faster in actual practice. But the proofs are too large, and now we have folding. And so we may be, kind of going back to MSMs. So no one really, I think, has a good idea of what is going to be the gold standard of a proof system that we can stop innovating on in 3 years, even 2 years. So I think in terms of standards, it's important to have something like Z-Prize, which is kind of always pushing the limit of what's possible. And hopefully we'll reach a point where things are so fast that we won't be, like, if a proof takes 30 seconds to generate, obviously we need it to be faster if you're trying to do like a transaction. But if you're going from like 0.1 seconds to like 0.001 seconds, optimization might not be as necessary. So I think standards should emerge once we have more confidence about the direction the technology is headed in.
All right, very good. I'm kind of putting that question to Rahul a little bit differently. Like at Wormhole, when you were thinking about the proof system, what proof system makes sense, how did you go about that process of picking a system?
Yeah, that's a difficult question. Anytime you're building an application that's based sort of on a moving target, right? There's a lot of research that's coming out, every few months or even every couple of weeks on a new proof system that's based on, maybe new ideas that just maybe haven't been implemented yet. And so you might start with a proof system that has a great implementation, and then a few months later, there's someone else suddenly breaks through some glass ceiling, and there's something that's 10x faster, that purports to be 10x faster. Now, if you're dealing with this changing landscape, you have to be very careful about which direction that you choose. Otherwise, your project might not exist in 6 months, especially if you're in this competitive market. So how do you navigate that landscape? I think one, you make directional bets on a few different things, right? You don't decide, okay, I'm only going to use this proof system, but you pick a class of maybe proof systems that you think are going to be valuable, and you sort of have to have like an investor mindset when you're thinking about this, which is you're not trying to predict the price of a specific stock maybe, but you're trying to assess where the trends of the market are going. And you can make bets in both directions. And so at Wormhole, I think one of the things that we've really done is make sure that we both have implementations in these sort of Stark-based systems, but also very much exploring folding schemes and the IVC approach to make sure that this actually may be the right system, whether or not we choose to go one way or the other. So we have our feet in two different places, and we'll see which one ultimately wins, and it might be both of them.
Okay, great. And kind of as last question, I'm going to put this to both of you. For somebody who wants to get started in this space, what's your advice? What should they think about, right? For a new project, for example. Now, obviously, both of you can answer on your on the browser side, client side, but also on the server side as well. Maybe start with Evan.
Yeah, I'm really excited about the power. So we build a wallet. We work with a lot of teams that are building dApps, and I'm really excited about kind of the new wave of applications that ZKPs are enabling for consumers. applications like on-chain credit, things that aren't using off-chain data that aren't really feasible to do right now. I would say the space is so deep and it's such a rabbit hole that you kind of have to determine where you want to go. So if you want to learn the math, I would recommend a textbook called Moon Math. It's a repository online. You can download it, free PDF. It's a great way to get involved in the math. If you're interested in building like an application that uses ZKPs, I think something like Alio, which has a Leo language, or something like Aztec, which has Noir, is a great place to get started where you can use some of the benefits without understanding the math. So I would figure out like what level you want to go in at it and not try to think about all of it at once because it's too much.
Great. Same thing for your role.
Yeah, I would definitely agree with that. I think ZK touches almost every area of computer science. Like all the way from like complexity theory to hardware. It kind of goes down the full stack. So it's hard to be an expert at everything. And I think picking one specific or two specific things within that framework is a good idea. There's a lot of good courses out there. I think if you want to go down the theoretical route, there's a great course by like Alessandro Chiesa at Berkeley from his fall 2020 and 2021 classes, which really go through some of the complexity theory associated with ZK. But really, I think if you want to build with ZK, you really just have to get your hands dirty and start writing circuits in whatever sort of language or proof system that you feel comfortable with. I think CirCom is a great starting place. Another great option is to kind of use something like Plonky2, which I've been using recently, and I think is a great starting point, especially if you want to abstract some of the sort of circuit components away. But yeah, I think from an application standpoint, like ZK is, I think there's a lot of possibilities, but at Wormhole, for example, like ZK really is part of the underlying infrastructure, and so developers and users don't really touch any of that infrastructure. The goal is to make sure that this is as, if we're trying to build something like a trustless sort of cross-chain messaging protocol, that it's there and that users don't really have to interact with it. So I think you can work at any level of abstraction. In some cases, even if you're using applications that are built on ZK, you may not even have to touch the ZK components. You can just sort of use and develop on top of that protocol as you wish.
All right, great. So we have a few minutes left in our session. I'm going to open it up to the audience, see if anybody has any questions about. Okay, I see a couple of hands.
Which high-level programming languages or ZK domain-specific languages you recommend for programming language enthusiasts or functional programmers to get interested in?
So Raul, you kind of touched based on it a little bit, maybe expand on it a little bit.
Sure. So I think everybody's sort of familiar with CirCom, which is a great, one of the earliest ZK DSLs that's gained a lot of traction. I think that's a good one to start if you want to understand the sort of how a circuit is, or the programming model for a circuit is very different from maybe other programming models. There's also some newer ones out there that are quite interesting. There's Noir, there's a bunch of these other sort of DSLs, like Alio has written one as well called Leo. Personally, I think there's another one that I think is quite interesting, which is Lurk, which is more functional based. It's a Lisp. I think that definitely has a lot of promise. It compiles to or interprets to Nova, which is one of the newer folding schemes. So that there's a variety of them out there, but pick your poison and get started, I guess.
Yeah. One other thing I recommend in terms of just learning material. So Berkeley has a very interesting MOOC, massive open source course that's available on YouTube. So definitely worth a read for sure. Okay, I see one more hand, two more hands. All right, 3. Okay, that's good. We have.
Yeah, Hello. Yeah. So I have a twofold question. One is targeting you, Hamid, for AMD. I know AMD has done a very good job in designing or coming out with latest Zinc FPGAs targeting applications, signal processing applications. I have designed millimeter wave radios using your Zinc processor. So now having this looking into the ZK market, if Xilinx or AMD is thinking about coming out FPGA devices specifically targeted for that segment, And second question for all three of you is for people like I design is mostly in system Verilog. So what is your advice into getting hands dirty into this segment?
All right, all right. So on the AMD piece of the question, I guess, overall, there is a little bit of rush to having a specific devices, whether it's ASICs or whether kind of a specific FPGAs targeting a certain applications. Typically, we are very cautious when we think about, a domain-specific piece of hardware. As a matter of fact, we did launch a domain-specific piece of hardware last week and a couple of weeks ago in New York and London, targeting specifically the electronic trading market. But typically, those type of decisions require really massive business cases. The matter of fact is AMD has a very robust roadmap of GPUs and FPGAs that have different combination of resources. And I think within that broad product portfolio, you should be able to design your system, get it to 99% of where you really need to get. So do not focus on a specific hardware, right? It's easy to think about it. It's kind of fun, for raising money, that sort of thing. But it's a very dangerous space to be in unless you absolutely know what the target is and there is product market fit. So I would caution people against that. And the second part of the question.
Could you repeat the second part?
I design FPGAs and ASICs and stuff, system Verilog, and I'm very interested into this ZK proof market. So what would be your advice to get hands dirty for FPGA and ASIC designers?
So maybe I should take
writing system Verilog code.
Okay. I thought you were asking about how to use high-level programming languages. So being an FPGA designer, it makes it a little bit easier because if you can work with the circuits, you don't need to go to higher-level programming languages. But frankly, I would say that partner up with somebody who understands the broader system, right? Do not go all the way. You really need a team to develop a lot of these systems. I think the level of complexity is not something that an FPGA developer can sit at home and develop the whole system. So that's my advice. Have somebody that understands the cryptography behind it, the higher level, primitives, and then you can do the hard work of turning that into hardware, Verilog VHDL type of language, right? Any other questions?
I have one question regarding to the security of zero knowledge proof. Actually, upgrade the hardware to minimize the impact of the attack or migrate the vulnerability of the hardware is very expensive. So what do you think about that?
Okay, the security question. Evan, that's a good question maybe for you. He's asking about the security of ZK systems and
Yeah. So generally, people target about 120 bits of security, and it's based on the discrete logarithm problem. You'll figure out how big your field needs to be. Most people try to fit their field within 256 bits. Like BLS 12377 is a 253-bit scalar field where the MSM, the twisted Edwards field where you actually do the MSM. So that's kind of what people target now if we have to use bigger fields because new attacks, new algorithms to calculate the discrete log become more viable. You can use larger fields. I think there's a big question about quantum security, right, where we're sure that discrete log is broken in a post-quantum world, but none of the internet is post-quantum right now. So it's kind of, I think, a big question of what, cryptography is always designed in such a way that you don't want to overbuild things because then it becomes inefficient, right? So you target specific levels of bit security in such a way that you can still do things efficiently. So if new attacks come up or computers get really, really fast or FPGAs get really, really fast, we'll use bigger fields.
All right, okay.
My question is to FPGA designers. What are problems, and is it possible to build a FPGA not for a proving system, but only for primitive operations such as multiplications and hashing only, and let the developers use them in some effective way? Why such a generic devices doesn't exist now?
Yeah, maybe Raul, that would be a good question for you. Yeah.
Yeah, I think so. I think previously a lot of people focused on like taking primitives like multiscalar multiplication as an example, or like NTT, which are two sort of core primitives, both for different proof systems. But if you really want to accelerate your whole system, which is what I think what Hamid was talking about earlier, it's important that you take the whole take the whole proof system and put it on there if you want to sort of get the maximal benefit of that. If MSMs are 80% of the computation of a proof system and the remaining 20% aren't MSMs, there's something else, and you accelerate MSMs as fast as you want, you'll still run into Amdahl's law. At some point, you won't be able to accelerate your system further. And so if you can put more components of your proof system on hardware, the better chance you have of actually getting better performance. So that's why there's really a push to get all these different components like LDEs, NDTs, other things on FPGAs.
Yeah, thank you.
All right, maybe one last question. We have 1 minute. All right, there you go. I see one in the back.
Hey. Since you've all worked with the hardware, I was wondering what, for you, the ideal hardware would look like, both in terms of programmability and in terms of parallelism or performance.
Yes, obviously, that question, depending on you're on the client side, it's very different versus the back end, right? Maybe for you, how would that look like on the front?
I would like to see the web GPU standard fully implemented on browsers, and not just the subset that currently is supported. In terms of actual, it's really a question of a bunch of things, right? So what sorts of proofs are people making on phones versus laptops, right? And honestly, I feel like machine learning, the hardware requirements that AI is pushing, are actually really making cryptography, like more complex cryptography, possible on client devices. So I'm more like just thankful we can ride that wave than asking what more I can have. There's like specific features though, like I'd like to know how much memory is currently allocated on someone's GPU and not just like try stuff. Because if you allocate too much and crash someone's GPU card, it takes down the whole machine. Yeah.
All right, great. So with that, we are out of time. Thank you both, Raul and Evan, for 5 more questions. Okay, we have more time. So maybe Raul, then maybe you answer that same question on the server side as well. That would be.
Yeah, I think there's a ton of things that you could potentially want, but one of the things that I think could be exciting is to essentially have infrastructure or abstractions to help you access accelerators like in the cloud. And I think Enganyama released something a few months back as well, which was quite interesting. But having access to these accelerators in the cloud really makes it easy for people who want to use EK to really just plug into some accelerator in the same way that developers maybe spin up an EC2 instance right now. If you have the same sort of approach, it becomes easier to just embed accelerators into your project.
Yeah. And I'm going to answer kind of a tangential, I guess, answer to that. Specifically in terms of FPGAs, until a few years ago, it was very difficult to actually access FPGAs, especially for a startup still in the community. Back in the day when Ethereum mining was all the rage, people would know, obviously, GPUs you could go buy off the shelf, and FPGAs you could not access unless you knew somebody who knows somebody type of situation. And we did a lot of work trying to change that, starting with Z-Price, for example, giving people access to FPGAs, and now continuing that through 2023. Our goal is for anybody who wants to access FPGAs, even smaller startups, to develop, any type of applications. There is a path for them, a path that's affordable. Also, we do a lot of community support. So we do provide hardware to a lot of startups that we think has potential to produce something valuable. So we have done, I guess, a lot actually as AMD to really foster the ecosystem. Okay, so more questions? We got a little bit extra time, so. All right, I think.
Yeah, the timer here just keeps resetting.
Yeah.
So we're like watching it go down,
Yeah.
and then it adds 5 more minutes.
All right. So I guess with that, we are going to give everybody a few minutes. All right. Thank you, Ben. Thank you, Raul.
Yeah, thank you. Thanks.
This one. This one, that one, okay. Okay. Okay, let's get it started. So, okay, please.
Right. All right. Hello, everyone. This is Gökhan from iOS Ventures. I'm an investor with the firm since 2020. I will briefly talk about iOS Ventures, but first of all, today's panel is about ZK killer apps and the survival of ZK in the future. Most of the talks today were very technical. We just wanted to touch upon what are the use cases of ZK, and maybe retouch on what is the value proposal from the ZK in general in the space. So this is what we're going to talk. It's going to be a very light talk, very high-level talk on the ZK applications. Before we start, maybe it's best if you can start with the round of introductions. Manasi, why don't you go first?
Yeah. Thanks, everyone, for joining. My name's Mansi Vora.
I work at a company called Receido, where we build a general-purpose ZK virtual machine. What that means is essentially you can take any arbitrary piece of code and run it in a ZK environment. The interesting thing about our approach, we've targeted the RISC-V instruction set architecture, and that essentially enables developers to write their ZK code in common programming languages like Rust, C++, Go. So I think there was a question at the previous panel, what languages should we be thinking about when we are programming ZK? And I think traditionally, you've had to learn a domain-specific language. The approach that we've taken, we are really enabling ZK in common programming languages. So that's the project.
Hi, my name is Joanna Zhen. I am the head of BD at Alio, L1 blockchain championing ZK technology and privacy-preserving qualities. Prior to Alio, I was at Optimism as a BD lead, and prior to that, I was at Coinbase building 2 products, including institutional sales tool and an NFT marketplace.
Hi, this is Garvit. I'm the founder and CEO at Electron Labs. So at Electron, we are essentially building what I like to call as a computation compression engine. And we're essentially using zero-knowledge proofs to compress down consensus algorithms to single Groth16 proofs. The idea behind this is that it's extremely difficult to actually run consensus nodes, and especially if you try to run these consensus nodes as a smart contract on any chain. So imagine running a Ethereum consensus node on a Solana smart contract. So we essentially compress down these computations down to validity proofs, which are then extremely cheap to verify across different chains. So basically, if you don't have to run a full node anymore in order to verify consensus completely. So yeah, we work with the large L1s, as well as people who kind of need very high security bridging. Yeah.
Cool. I'm Carter. I am the founder and CEO of QED. So QED is a horizontally scalable L2, and that just means we can support applications with millions of concurrent users. And we do all this without any security trade-offs, so everything is proved end-to-end. And we submit all of our block proofs off to Ethereum, so we can take advantage of Ethereum's wonderful consensus as well.
Perfect, yeah. Thanks a lot for the intros. Maybe to give you guys an idea, there has been around $1.5 billion that has been invested in the ZK space for the tech development in the last couple of years. And all for that is obviously for people to come and build on top of these ZK platforms. And finding a use case, finding a product market fit is definitely challenging, but I think we could argue that scaling, privacy, some of the product market fits we've found already. But I just wanted to revisit and see what you guys think about, and maybe this question you guys can all touch upon. What do you think are the main value proposals from ZK? And to build on that, what are some of the applications that are possible with ZK that wouldn't be possible otherwise? Let's start with...
Yeah, sure. Right. Yeah, so as you mentioned, right, ZK has been a really hot topic these days. But a lot of research has been going into the ZK industry, for the past few years, right? Alio, as example, we have been around since 2017, with the ZXC white paper that talked about privacy, zero-knowledge execution with a privacy use case. So I think specifically to answer your question, right, so ZK really enables, really 2 things, scalability and privacy. And then at Alio, we very much focus on the privacy aspect. And from a builder perspective, what you will see is an environment that allows you to build really privacy focused. You can make it not the only option, right? It's supposed to be giving you, optionality, right, to choose to do private transfer, private transfer, public transfer, in all range of options for you to build on top of. So it's really a programmable privacy application that is previously not available to build on a transparent public blockchain. So I think from that perspective, I can go into the use cases, but I know we have other questions in the future that will touch on that. But basically, I think just to leave you guys with like doing both decentralized and programmable private applications. That's now available using ZK.
Great.
Do you mind if I jump in here?
Yeah. Go
Yeah.
ahead.
So I don't know. I think we may disagree a little bit, but for me, it seems like the big value proposition is that previously Web 2 couldn't, or Web 3 couldn't use Web 2 scaling strategies because it would decrease the number of nodes that verify each transaction, just because, like, you know, the more you distribute the load, the fewer nodes are actually checking and running each transaction. But with zero-knowledge proofs, I guess this isn't the ZK part of zero knowledge, and this is a very famous pun within the community, but specifically the succinctness that we have. And with recursive ZKP, it allows us to use those same Web 2 scaling strategies that have brought the internet to, you know, scale so that, you know, what is it, tens of billions of people around the world? I don't know, what is the world population, but everyone can use the internet because of these strategies. And like ZK, well, specifically the succinct part, allows us to bring these strategies pretty much directly copy and pasting with the added requirement to prove and verify to the Web3 world. And this is without any security trade-offs at all, so long as our underlying proof system is as secure as, you know, whichever blockchain, in the case of us, L2s, that we're submitting off to. So really, like, at least at QED, we're very focused on bringing those world-changing applications that actually impact normal people to the blockchain. And you know, just to go into, I guess, a little bit of a sort of like, you mentioned $1.5 billion has been invested into ZK. There's a lot of money going into blockchain. A lot of capital has gone into our industry. And what do we have to show for it for the normal people, right? We must take this capital, this enormous amount of capital that humanity has given us, and give them something back. And with ZK, we have the first opportunity to really do that for, yeah, I guess, the non-crypto folks.
Cool.
I can double click on that. So definitely there are two buckets when, you know, like Joanna mentioned, privacy and scalability. The reason scalability is possible is because of this computational integrity component that ZK enables, which is essentially you now don't have to trust. You can offload computation to a, you know, untrusted party. You don't have to trust that the outcome or the output is correct. In the Web 2 sense, you essentially either have to trust the third party or you rerun the computation just to make sure that the output is correct. In the ZK context, you let them run the computation, and it also generates a ZK proof that the computation was done in a very, in the right manner. And so with that, what enables, ZK enables in terms of use cases is this concept we are thinking about called ZK coprocessor. So there's, of course, scalability, and we've all heard of layer 2s, scaling, you know, scaling our blockchains with ZK L2s. But there's also scaling at the L1 level that happens with ZK. And with ZK coprocessors, you can essentially offload really heavy computation onto the ZK coprocessor and just have the proof be submitted back on chain and verify that chain. So a really tangible use case is, say, you want to build a on-chain order matching engine. That's really not possible with like the current smart contract limitations and gas limitations that exist today. In the ZK context, you can offload all of that heavy computation and have the matching engine run off-chain with the ZK proof generated that then you can leverage on-chain and have the settlement happen. So that wasn't really possible at the L1 level before.
Cool.
Yeah, I just want to like add one aspect to this. Like, I mean, privacy and scalability are two obvious, you know, most talked about applications, but like ZK actually quite interesting as an execution, or rather a consensus layer, so to speak. Like if you compare that with proof of stake, for example, in proof of stake we essentially have this economic security model where if you have X dollars stake, that's the kind of security model you have. But if you're actually proving something with ZK, there's no economic security backing that. You actually get mathematical certainty that this thing is actually indeed correct according to these mathematical rules, which actually allows you to create these sort of novel execution environments which have no trust assumptions at all, except the mathematics for it, of course. So that's one use case I believe that we'll see for ZK.
Amazing, yeah. So like all of these I think ZK platforms that are building now, what they're building actually is ahead of their time. If you ask anyone in the space 2-3 years ago, how long would it take to see the first launch of the ZK VM, let's say, they would tell you 5 to 10 years. We already started seeing some of the mainnets in the space. So I understand that it is a very nascent space, but then if you want to get some mainstream adoption from the developers, it has to reach to the same level of ease of deployment as the ETH L1 or maybe even like Web2 platforms, right? So what is the state of the current developer tooling for some of the ZK platforms in the space, and what it takes to actually make it much more easier for developers to interact with?
Yeah, maybe I can touch upon our approach here. So really the motivation behind the founders starting Receiver was to make ZK accessible. Right. And again, the state of the art prior to Receiver was you have to learn the underlying cryptography, you have to understand how to write circuits, which definitely you can do, but it takes you at least it's a steep learning curve, 6+ months, and that's not really scalable across millions of developers. And so the approach that we've taken, again, like I mentioned at the start, was we are abstracting all of that away, where you don't have to think about the underlying cryptography or writing circuits, and now you can write your ZK programs in common programming languages. So, not having to think about the math and cryptography, not having to learn a new language, and you can access the other benefit of accessing or using an existing language or existing programming language is that you can leverage libraries or cargoes that people have built and written over the years, where with new DSLs, you have to build a lot of it from ground up. And so that's our approach in terms of making ZK accessible. There's definitely still a lot of work to do from a developer experience standpoint, where we still need to educate people about how to use ZK, what are the design primitives, how to think about security in a ZK context. Our approach to solving some of that is just trying, as builders of this technology, building as many examples and demos and showcases as possible to just show the world what's possible with this technology and inspire developers to then build similar applications.
Cool. Joanna?
Yeah, I don't know how many of you were at my talk earlier. I was talking about this in terms of the design, the architecture design of Aleo. Essentially, if you look at the top, kind of the tip of the iceberg, you see the Aleo SDK, right? That's the developer toolkit. But really, everything underneath is purposely designed to abstract the complexity away. So, similar to what Manasseh was talking about, we start from, compiling the language, high-level language Leo to Aleo instructions to that's the intermediary representation, and then to the bytecode level, and all the way down to the VM, the virtual machine that we have, Snark-based VM, that deals with the ZK circuit and stuff like that. So I think the point is just to get started, get onboarded into the ecosystem. It's not a huge lift for you if you already have a Rust or JavaScript or TypeScript programming language experience. And I think on top of that, I just wanted to also bring up the fact that I know you were asking about tooling specifically, but I think what we do, especially WoW, is we have been relying on the community, right? So I see people, in the developer ambassador program are in the audience. We have Evan, who's one of our grantees, in the audience. We really kind of outsource the gaps of, we call it RFP, or blueprint grant, out to the community for the public to solve. So we see, an issue for instance, we need an Oracle that's ZK specific. We publish that RFP into the public, into the web for people to solve, and then we're currently kind of contracting this specific team to be a grantee to work on that problem. So I think that has been working really well for us. We have about 300 grantees in the ecosystem, and I think every single one of them is working on something really valuable for the overall ecosystem.
Cool. And developer tooling is definitely one of the bottlenecks, but there are other bottlenecks in the ecosystem as well. Like maybe you guys can talk about like what do you see beyond the developer tooling? Are the bottlenecks for developers who wants to build on top of these platforms?
I mean, I have to jump in though and say that QED supports normal ES6 JavaScript, the world's most popular programming language. Not like JavaScript, not like TypeScript, not like Python. We support the vanilla type. Now, major credit to RISC-0 for supporting Rust. I'm not sure that there are millions of Rust developers, perhaps hundreds of thousands based on GitHub data, but still a lot, right? And if no one is building on what, like, you know, developer tooling, you ask if this is the bottleneck. If no one is building, it doesn't matter how well we could scale, right? So it is the bottleneck right now? Right. What do you think?
Yeah, I think for a lot of applications, like developer tooling is definitely a challenge in terms of getting developers onboarded. But for a lot of applications, like the one you mentioned regarding succinctness property, right? I think in these applications, you will not have a large number of developers developing multiple applications, but a small number of companies building these applications, which then get used widely. And I think in these applications, performance will matter a lot more as opposed to developer experience. And I think if you talk about, for example, you know, the performance of ZK Infra right now, like proving time is usually measured in several minutes, while we eventually need to get this down to, in my opinion, into microseconds, right? That eventually we should be able to generate very large proofs of very large amounts of computation in microseconds, because the user experience will demand that. Like, you know, if you talk about a transaction, for example, today, let's say you were to use a ZK Light Client Bish to send a cross-chain transaction, you probably have to wait a couple of minutes for this transaction to happen. However, like we know that some of the faster chains have like this 1 second block time, and if you want to offer a very high quality user experience, you have to offer proving time in the same order, right? So I believe that if you have a 1 second block time, then you probably spend a couple of milliseconds or microseconds to generate a proof, but then you have to send it across. If you're waiting for more than that, then you're waiting too much and you're basically affecting the user experience. So yeah, like basically performance of these systems is I believe is a major bottleneck. Yeah.
So we agree that like the UX for both, because essentially from what I understand, and tell me if I'm wrong, but what you're saying is like the bottlenecks that we have are the developer user experience, which is based on tooling and languages and so on, and then we have the end user experience, which is based on like waiting for finality and these kinds of problems, right?
I'm basically, the bottleneck for ZK perspective is the performance, but I'm like the reason I said performance because I'm working backwards from the user experience here, because that's what matters in the end. Yeah. So
agree.
Yeah.
Agree. Just to push back a little bit on the minutes part there with the proofs. I mean, like there are lots of proving systems that can generate proofs fairly quickly, like QED, proving one transaction on the client side, something like a few hundred milliseconds, doing a 4-to-1 recursion. Now we have fast recursive ZKP because of our wonderful new Fry-based proving systems. We don't have to worry about these issues, right? We have block times, 100, let's say 1 million transactions in a block. We have block times of around 6 seconds. So we're not waiting minutes anymore, right?
Yeah, you can definitely, prove specific items, for specific use cases quite fast.
Smart contracts.
Yeah, but if you start, let's say, proving generalized computation, right? I'll give you a number, right? So that if you were, let's say, measure it in terms of CPU cycles, which I think RISC-0 does, then you are, compared to a normal computation that is running natively on a CPU, you are slower by a factor of at least 100, and in certain cases, you're slower by a factor of 100,000. So that's what I'm talking about. That in terms of comparing native performance, you're significantly slower. And that definitely...
Distributed compute, right?
Sorry?
Distributed compute and recursive ZKP.
Yeah, but your hardware cost goes up, right? I mean,
Not that much.
No, quite significantly, right? I mean,
4-to-1 in less than 500 milliseconds.
You're missing the bigger picture, right? See.
What's the bigger picture?
You can get the proving time, let's say, down by a factor of 100. But you have to add 100 machines after that, and your cost goes up by a factor of 100.
Well, my users are proving their own transactions. Why can't they participate in the block production? I only need, well, if we're doing a 4-to-1, then we all know from our math classes that we're going to need n over 3 to participate if we have a 4-part, if we have a quad tree, right? So I just need a third of people that are already proving their own transactions to donate another, let's hear it, 500 milliseconds of their compute time, 1/3, for a massive discount in gas fee. Right. I think this is rather reasonable.
For a use case that just relies on client-side proving, that's probably fine.
Right.
But for a lot of use cases, like the one you mentioned around succinctness, you need to deal with much larger amounts of, and it's a single machine that...
No, it is quite succinct. We're talking about like everyone receives 4 100 kilobyte proofs of, what is that, less than 10 packets? TCP packets? Right?
I want to move the conversation more to the... So one thing that's important, I think, when it comes to ZK discussions, like a lot of people are excited about what are the use cases for ZK within the Web3 space, right? And scalability, privacy are some of the things that we've mentioned. But then a lot of people are also interested in, like, is ZK going to provide some value add to some of the Web2 applications or Web2 world, right? So maybe let's move the conversation up to the app side again. Do you guys think it's going to be helpful for some of the enterprises, some of the Web2 companies or users, what we're building at the ZK side? Manasi, you wanna start?
Yeah, I'll definitely take this. I think as a company, we believe ZK technology definitely goes beyond blockchain Web3 applications and use cases, definitely. That's the first place, and there's a lot of demand there. So we are very focused on, scaling blockchains, scaling DeFi applications, bringing privacy on chain. But there's so much more that ZK can enable, and it doesn't even have to touch crypto or blockchain. And to make it concrete, there's one level which is bridging the Web2 and Web3 world, which we are exploring currently, which essentially is taking off-chain data, which already exists in the Web2 world, for example, identity, and bridging that and bringing that in a trustless manner on-chain, so you can leverage, traditional identity on your smart contract. An example of that, we just launched Bonsai Pay, which enables you to send crypto assets to a Gmail account. You don't even need to know the person's wallet address, or the person doesn't even need to have a wallet to be able to send them crypto now. And this is enabled because we are bridging, taking Google's OIDC, JOT tokens, proving them in a ZK manner, and associating that with a wallet. So that's one use case which bridges Web2, Web3. Pure Web2, I would say there are so many, when we talk about privacy, so many use cases in the healthcare space, in the identity space. Another concrete example, the National Renewable Labs in the US, which works under DARPA, controls or monitors and does research and development for the energy grid, they've actually written a paper on ZK to use ZK in control grids. So, again, going back to the computational integrity part, where you don't have to trust the different nodes in the electric grid and still can take those inputs as valid inputs, and that reduces the, just the vulnerability factor and increases security. So there's so much. I think that the Web2 world is really unexplored when it comes to ZK use cases.
Right.
Yeah, I would like to just add to that. Definitely think that it is the reason why we believe that ZK is the what's the right word? The trigger for the next mainstream adoption, right? I think specifically at Aleo, as I mentioned earlier, we focus on privacy use cases, and privacy is the most underrated or most misunderstood concept out there. When people talk about privacy, they think about maybe just money laundering, right? Using like dark web or ISK technology. But what we were talking about is we're actually talking to the many enterprise users about building these compliant and private solutions that enables them to programmably build these configurations to add this compliance layer on top of something like a fraud detection on top of the like a stablecoin, for instance, stablecoin transfer. So we very much want to bring these Web2 players into the Web3 world. One example is we recently just launched this product called ZPass, which is something that we internally dog-fooded our own tech stack. ZPass basically is a self-sovereign identity solution that can be used for a range of scenarios. One particular scenario that I'm very excited about is we work with this company called Common Sense Media. So they look at these school kids' age verification and they provide that to the internet providers like Netflix and other like Disney content providers in the world. So we are the technology provider in between these two, the content providers and basically the school age children, right? So we provide the attestation layer on top of this existing KYC infrastructure. And that's something that we see having a real world use case, right? Not just, we don't even, like when we pitch to these companies, we don't even talk about us as a blockchain company.
Right.
As a matter of fact, we just say that we are a technology solution provider, with zero knowledge proof at the core.
All right. Given the limitation, maybe I have one more question for Garvid and Carter, but let me open it up to the audience. All right, yeah. So then maybe one more question from my side, and then I will open up to the audience. So where do you guys see the space going like 3 to 5 years from here now, right? What do you think is the worst and best case for ZK technology? Where do you see the adoption?
Sure. So I think like rather than just like 3 to 5 years, I would like, if you talk about very long term and probably
Right.
talk about end game. So like, I would say like there are 3 areas which kind of, we'll see. So obviously developer experience is one which we've discussed. Performance is definitely another one, that we've seen happen here. But I think what will happen over the long run is that the cost of proof generation will essentially, turn down to 0.
Right.
Like as we saw with payments that, in certain areas that the cost of payments is 0, we will see the same with zero knowledge proofs. And what's going to happen as a result is that people will generate zero knowledge proofs for pretty much everything, right? So right now we do it only when we absolutely need it because like it requires a significant amount of capital actually to be invested before we can start generating these proofs. I think what we'll eventually see is that, so for example, if you talk about a developer today, when they compile down their code, once they build the code, they basically deploy it. I think one of the things they'll also do in pretty much all use cases is they'll also generate a proof of that and share that. And they'll do that because there's some added benefit of that. And even if it's a good to have use case, they'll do it anyways because it will be essentially free to generate these proofs. So we'll have pretty much zero knowledge proofs for pretty much all programs being executed everywhere. And given the fact that generally things are moving towards trustless computing anyways, it will make sense to have these proofs come as a receipt for pretty much everything. So yeah, I believe that's kind of the long term for zero knowledge proofs.
Right. Have we all forgotten Web3, why it's called Web3? Like, if zero knowledge proofs can enable us to scale the trustless compute technologies, called blockchain or whatever you want, to Web 2 scale, then shouldn't that mean that zero knowledge proofs are what make Web 3 become Web 3? Right? Shouldn't we want, like, we spend all of our time on our devices. I spend most of my time on my devices. That's why I've got a little, but, maybe I should spend less time. But most of my life is on the internet. And right now, that life is controlled by one of a few large platforms. And as a species, we're moving towards our whole lives being on the internet. Now, do we want to live in these little, technological dictatorships ruled by, some people like Elon Musk, some people don't, but there's multiple of them. I don't want to say anything, we love Amazon though, of course. But we do, we love Amazon. But, we need, as a species, if we are going to live in the digital world, we need a fair way to do it. And currently, the compute model does not give us that. But ZK can. So where is ZK going to be in 5 years, 10 years down the future? Hopefully, for the interest, I think, of everyone in the room, moving towards that. Not just financial applications, although financial applications work great. Hopefully, we see more and more and more new applications that didn't work with existing blockchains start to work with trustless compute. I don't know if that's something that is shared by my fellow panelists. I hope we're kind of all on the same page about that. But yeah, the ZK is the future internet, right?
Perfect. Thanks a lot. So let me open it up to the audience. Please raise your hand if you have any questions, and we're going to bring the microphone. I'm sorry. First, we will have to take behind. We'll come next.
So my question is, as Joanna touched upon the application, they have for kids using certain applications. So my question is, do you see applications, I'm not talking about the blockchain space here, but outside, I don't know whether you call it Web 2, like the network security, where you have the DDoS kind of attacks, And also, like malware kind of stuff, getting into one's computer and doing damages. So do you see ZK applications, and are people looking into that? I'm just curious to hear you guys' views on that.
I come from a security background. I was previously in a hacking gang as a child and was arrested, but did not get a felony because I was a minor. But yeah, so I have some hacker background. Maybe I can touch on that question. But yeah, so like I think for certain applications, probably less on the the end user side, more on the server side, where like you want to make sure that one server hasn't been compromised by malware. You can do any like mission critical computation that it's doing and prove it. And then I guess some other server doesn't have to just blindly trust the result of that one server. So even if you hack into the server that's doing this critical computation, you don't have to worry about if it's been compromised or whatever. Maybe you have another air gap system that's going to be ingesting the result. But I guess that works. But I'm very bullish on ZK, but I don't see it like us running an OS on it. Although I know RISC-0 has booted Linux, and congratulations on that. But I don't know, maybe RISC-0 has a...
Yeah, I think it goes back to what I was saying earlier, the computational integrity piece that ZK enables, where now, you don't have to trust the output that comes from a random, outsourced computer. And you have a ZK proof that's generated with that output that can be verified. And you trust that the program it ran was ran correctly because you're verifying the ZK proof, and it's cryptographically secure. So that's all I have to say.
Cool. Let's take another question.
Hello there. My question is for Elio, but others can take it too if you like to. About this particular claim that decentralization, scalability, and privacy aren't mutually exclusive anymore. Could you please expand on this a little, like in terms of your performance predictions? Like realistically, how far do you think the Elio system will scale? And a second question again for Elio: why did you, in the Leo programming line, why did you prefer a low-level approach? And what do you think this brings? Thank you.
Sorry, the second question one more time.
The Leo language, why is it using a low-level description? Why did you prefer that, right?
Okay, so the scalability question, right? I think basically the way that we've been looking at scalability is just using off-chain compute model. So all the everything computation-wise is happening off-chain. That's why there's technically no gas fee or technically no transaction fee unless it's running on-chain or in a shared state. And then on the zero-knowledge verification, that's when you first finish your computation, then you bring the proof on-chain. That's the only portion that will bring to the brought on-chain, right? So that's why from a scalability standpoint, it's similar to like a roll-up, for instance, right? It's very scalable. Yeah.
Right. But how scalable? Like in terms of performance numbers,
like
transactions
a benchmark
per second for, say, an expected or average
smart
contract size?
I don't know if we have a TPS per se.
Yes, I was just wondering what kind of study you did on this, like theoretical or,
Yeah, I think depends on, let's just use a simple transfer as an example, right? It's, let's say, like an NFT private mint, it's going to take you maybe like 30 seconds to complete, right? So it just depends on the complexity and the size of the application. The actual application running time will be dependent on that.
Mm-hmm. All right. All right, that has to be all. Thanks a lot, everyone, for coming and joining us. Thank you for participating.
Thank you.
Thank you.
Let's meet.
Now we're going to have Porter from Mother Labs. Let me look at here. Well, welcome. Let's wait. We remove the chairs. Very careful. So, please, let's have some order here so we can continue with the talks. If we have some Q&A, we can go to the next room, please. Let's put here the. Okay. We're about to start. Please take a seat. Okay.
Great. Test. Thank you.
20 seconds.
No, you're good.
Okay, I think that's it.
All right, we're ready. Thank you for having me. I'm Porter. I'm here to talk about security and circuit anatomy. Very excited to see you all today. When I was preparing these slides, just a warning, I wasn't sure what the background of the audience was going to be, and so I assumed that there might be more beginners who want to learn how ZK Sync circuits work. There's actually a lot of experts in the room, including some of my teammates who wrote the circuits, and so I will try and make it interesting by talking past what's just on the slides and say some more advanced things so that everyone can learn something. Cool. So my background is I'm on the security team at Matter Labs. I help our cryptographers a lot, working with our auditors and bug bounty programs and things like that. And I like math. So ZK Sync, if you don't already know, it's leading ZK rollup on Ethereum. We are working to advance personal freedom for all. Our one company announcement is we are hyperscaling with the ZK stack. ZK stack it's actually already been in the works a little bit, but we're announcing it at the conference this week, so it's kind of not related to my presentation, but if you'd like to build with the ZK stack, reach out to our team. But also I want to say the Matter Labs team is like the most amazing team I've ever worked with. If you ever have a chance to come apply and work here, the team is really, really good. There's a lot of smart people, and I really like my job every single day. It's great working with these people. So with that, our mission statement, and then we'll get started. Our purpose is to break financial barriers and enhance the world's freedom by accelerating the mass adoption of public blockchains. It's easy to plop a mission statement on a screen, but everyone at Matter Labs really does believe in this stuff through and through. So today's agenda, very brief intro on ZK rollups. I know you guys already know what they are, but very, very brief, and then we'll dive deeper into more interesting things. And then what do we need to prove to make a ZK rollup? circuit anatomy, which is like a new buzzword that I've made up for this talk, but it's like the structure of how all of our circuits fit together. I'll talk about security and conclusion. So ZK rollups, what are they? Everybody knows ZK rollups are just rollups that ZK prove everything. And so the question though is like, what is everything? And I think this is the part where a lot of like, if you're not as technical or not as into like the ZK math itself, this is where like most people get lost, is the like, what is everything? And it can be intimidating because you think that like, there's no way I'll be able to learn beyond this level because ZK circuits must just be impossibly complicated. That's not really true. We can actually break it down, and hopefully this is going to make a ton of sense, and all of our circuits will be like very straightforward to you. So what do we need to prove in general for ZK EVM specifically? We're trying to prove everything that the Ethereum virtual machine does, which is what? Well, it's all the opcodes that are all the operations that you can call. So adding, subtracting, multiplying, dividing, shifting, jumping to another instruction, storage reads. I put that one at the bottom because that one's like a little more complicated than some of the others. So when it comes time to make the circuits, we might handle some of these a little bit differently. So we do need to prove also memory and storage. So anything that's like read or written to memory or placed in storage for later, we also need to prove that besides just like the raw computation. There's also the precompiles to worry about that aren't really opcodes, but you want to like call these sort of special syscall functions. EC recover stands for elliptic curve recover. It's how you get back from the signature to the Ethereum address. Ketchak and SHA-256 are common hash functions. We also need to check that we're executing the correct code. So I said earlier that we're going to prove every opcode, but how do I know that those opcodes that I'm proving are actually what was supposed to be there in the first place? Well, we'll need to check that and make sure we're reading or that we're executing the correct smart contract. And I think this is lastly, we'll need to prove events and L1 messages. Events are pretty much just like L2 messages. It's just little like posts of data on the chain so that maybe you can read the chain later and just look through events for something. Cool, so that's all the things that we'll need to prove. Now let's look at how zkSync described our circuits. I call them Boojum circuits. Boojum is the name for our new proof system. It's finally coming into production in the next week or two, depending on how fast we roll it out. It's been through a bunch of testing, a bunch of security, and a ton of stuff, and I'll talk about that later. The circuits are written using the Boojum library, so I've just called them the Boojum circuits here. So first of all of the opcodes need to get proven, and this happens in the main VM circuit. This makes a lot of sense. It's the sort of the meat of like proving all the execution is that the like, I don't know, it makes sense to call it the main VM because it does most of the work. So the way the main VM circuit works is it's going to have multiple cycles, and every cycle will just do exactly one opcode. So we might do one add, and we'll have to prove the add. There's some other details like proving that the registers are updated in the correct way. But if you're new to ZK, you could see like how like you might be able to prove like one add at a time, and then a divide, and then a jump, and like keep cycling through, and that's how you work your way through all the proving. Storage read is expensive, so theoretically we could just put everything in one giant circuit, but that's going to like hurt performance because some of these operations are very slow, some of them are fast. So pretty much our main VM circuit only does actually like the very quick operations such as addition, and then it will also post to another circuit more expensive things such as storage read. So we have other circuits that handle the memory is handled by the RAM permutation circuit, and storage is handled by the storage application circuit. Similarly, we have circuits for all the precompiles. EC recover, Ketchak, SHA-256, they all get their own circuits. All of these are like very commonly called functions, and so it makes sense to sort of like optimize one circuit just for these pieces of code. And also checking that the code that we're executing the right thing, this happens in the code decommitter circuit. And the events and L1 messages are actually like so similar that we can put them in the same circuit, and that one's called log sorter. And that's it. So we can put all of our circuits together. If I showed you this diagram at the beginning of the talk, that would have looked terribly complicated. It still might look a little complicated, but I've already explained everything. We start with our main VM circuit at the top. Thankfully, the screen's pretty big, so I think hopefully people can see it. Top middle is main VM circuit, and it pushes things later. So we see on the right the logs, the storage sorter, storage application. On the left-hand side, you'll see things like Ketchak and SHA and RAM permutation circuit. And so this is what all of our things look like in practice. Cool. All right, so that's like the beginner level. I do want to talk for, I guess I've already been talking a little bit, but talk for a little more detail about really how all this fits together. So it's nice to have a circuit for everything, but you also have to connect them properly. And naively, everything's like in all of computer science just connected with a queue of some kind. But we need to make sure that we can also prove that our queue is done correctly to prove that we've actually done everything that we're supposed to pass around. So the way our queue works is basically just a repeated hash of each input, and then in the same way that's when we're pushing into the queue, and then when we pop from the queue, we also repeated hash everything that we pop, and we should end up at the same spot because you're popping all the same elements you're pushing. So at the end, we just have to check that the queue is empty and that all the pushes equal all the pops, and we're good. So that's how our queues sort of hold all of the things together. There's one other caveat that I've slipped past, which is that some of these circuits can only handle a little bit of data at a time. And as we're running our big blockchain and doing tons of transactions at a time, one of these circuits might not actually be enough for an entire batch. And so in practice, we'll actually probably have 10, 20, 100, I don't know, copies of the main VM circuit running next to each other in a row. And so we'll also need to prove that basically the inputs to one VM circuit are the same as the outputs from the previous one. So just chaining everything together nicely. So you do all this, and then you recursively prove all the multiple copies of the main VM circuit down to one, and then we have a scheduler circuit which finally wraps all of these things together. And at the end, we end up with one final proof, and that is the outline of ZK Sync circuits. So we did it. All right, the second half of the talk is about security. So there's about $450 million TVL on our blockchain right now. And so the second half, I'm on the security team. I have to keep this safe. And I also want to get some sleep at night. So how do I do that? It's a tough job because sometimes if you miss one line of code, then there can be very catastrophic damage and extra things can get proved. I will give one caveat to this, which is that just breaking our proof system is not always enough to actually get an exploit in the production system because we have some defense in depth measures outside of just the ZK cryptography. But for this talk, I'm just talking about the ZK cryptography itself, and we don't want any bugs. Also, Chainlight's in the audience. They wrote an awesome write-up of this bug and how it happened and full explanation. Thank you, Chainlight. So, ZK audits. We work with individual auditors and companies like Trailbit, Spearbit, Chainlight, several others. These people are amazing, tons of domain experts who have spent a lot of time looking at this type of stuff. It's super great working with them, especially when we have one piece of the code base that we really want someone to look at. If we completely rewrite one of the circuits to, for instance, we recently rewrote Easy Recover for performance reasons because it's called so often for every single EVM transaction. So now that we have a super optimized one, we're going to want a new audit for that. Competitive audits are very fun. We recently gave away, in the process, I guess, of giving away $1.1 million USDC with Code Farina. I think it's the largest competitive audit on Code Farina ever. It was also the first ever audit on Code Farina that included the ZK circuits, so that was a big deal. If you helped to look at our code, I might have answered some of your questions. I helped write some of the documentation. Hopefully that was useful. And it's pretty fun to get to give away this much money in 3 weeks. And a lot of amazing people came together and found some cool bugs. which will be announced soon, I think. We've finished judging, and all the bugs were submitted, and we fixed all the errors already, but we're waiting for Code Farina to decide like how much money each person gets. So that's the holdup if you're waiting on your bounties. But we will probably continue to do more competitive audits in the future, so if you missed this one, there will be more chances because the results we get from this are actually really amazing, even compared to traditional audit firms. Bug bounty is always ongoing, so if anything happens, if we've missed anything, and we will reward you if you come submit a bug to us at any time. And one announcement that I can start to say is that we are working on adding, not just our circuits are in the bug bounty now, but the compiler will also be added to the bug bounty, and I think this is going to be the first compiler that's on Immunify. So we're working through some like challenges of like how do you include this type of code, and how will we like check bugs, and so it's very exciting to be able to put like so much of our code base on Immunify. It's awesome. A few more techniques for circuits is fuzzing, formal verification, and something that we are working on and like have like very solid progress is two-factor authentication using TEs. So this is something that's very cool. I think Justin Drake wrote a blog post about this on ETH Research like a year ago, but you can double check whether the ZK proof was done correctly by running all of the same code, or not the ZK code, but just normal code inside a trusted execution environment, and only when both of them agree on the output, then you move the chain forward. This way, even if there's some critical circuit bug, as long as like the TEs don't have the same bug, it won't break the chain and people won't be able to steal money. And so our TE engineers are like super talented people. I actually get to work with them a lot. Very excited for this. So cool. I think that brings it to the end. So thank you. If you want to learn more, message me on Twitter anytime. I always answer questions. And it's great to be here. We have time for questions?
Thank you for presentation. And I have questions. You mentioned why storage rate is expensive.
Yeah, why storage read is expensive. That's good. So it's because of the way like it comes down to how the proof system works, which is like, I didn't want to go too much into Boojum. We're using Plonk arithmetization with Fry prover, if that means something. And basically to do like normal arithmetic, it's easy to just make Plonk gates and constraints. To do a storage read, a lot of times you want to do like a permutation argument. And so that permutation argument can be like larger and it's kind of different and unique, so it doesn't quite make sense to fit it in with the rest of the opcodes. But that leads to a bigger point, which is that some operations like L1 gas costs are like how expensive it is to do an L1 operation, but some L2 gas costs can be different because like some things are easier to prove, some things are harder to prove. So that's kind of an ongoing challenge, is how do we like line up the costs between the two. Thanks. Okay, I'll stick around afterwards. Thank you guys.
Okay, coming up next, Andrea from Veridice.
All right, hi everyone. I'm Andrea Buterchi. I'm the Vice President of Engineering at Veridize, and in today's talk, I will present 2 security tools that we developed at Veridize for zero-knowledge proofs. All right. Perfect. Okay, so in the last few years, we witnessed the emergence of ZK solutions, and here we're talking about privacy-based contracts, rollups, and even privacy-preserving blockchains. And actually, at Veridize, we audited several of these services, and our conclusion was that sometimes manually auditing ZK products might be challenging. So we wanted to push the limits of ZK security, and we started implementing tools that can automatically detect bugs and vulnerabilities in zero-knowledge proof circuits. And a few words about Veridize. We are a company that provides the traditional auditing for all the blockchain layers, but we are also developing state-of-the-art tools for securing the blockchain ecosystem in general. And we are doing that, where we are providing access to these tools through our security as a service platform, which basically brings these security analysis tools to the fingertips of the blockchain community. And in today's talk, I will briefly discuss 2 of these ZK-related tools, which are PICAS, an automated verifier for zero-knowledge proofs circuits, and ZK Vanguard, which is a static analysis tool. All right, so before I dive into the specifics of these tools, I will briefly tell you about the workflow of a zero-knowledge circuit. All right, so we start with the source code, right, which can be written in either Circum, Hello, 2, or other domain-specific languages for zero-knowledge proofs. And this code is then transformed into a witness generator and a set of polynomial field equations. All right, and the latter is then converted into a prover and a verifier, which are collectively called a snark. All right, so one thing that I want to mention before moving forward is that unlike traditional programming, the source code contains both the computation and the constraints, and we'll have a look at that in a minute. Another mention is that for the examples in this presentation, we will use Circum. Cool, so a quick introduction to Circum. What you see here on this slide is a very simple example of a Circum template. So in the first part of this code snippet, you see the signals, input and output signals. And on the second part of this code snippet, you see the computations and also the constraints. And if you notice, like here we are using 3 operators, the assignment operator, the first one, the equality constraint operator, and the third operator, which is a combination of these 2. So the third operator also affects the computation part and the constraints part. All right, so we can distinguish these 2 entities, the computation and the constraints, in this way. And usually how this works is, the users provide the input, the computation part outputs a witness, which will then be used to produce the proofs. And after that, the set of constraints, the verifier which uses the set of constraints will say, okay, the proof looks okay to me, or no, the proof is invalid. And what we usually want is this computation part and the constraints part to be equivalent. And I will tell you why this is important. Perfect. So to formally describe this equivalence, it looks like this. This is a property that needs to hold. So basically, what this property says is that for every input-output of a program P, so this every input-output pair of P must satisfy C, the set of constraints, and for every pair that satisfies C, this pair has to be an input-output pair of P. And we realized that this property is often violated in, in zero-knowledge applications. And actually, this non-equivalence issue is the root cause of the unconstrained circuit. So basically, this is also related to non-determinism behavior. And in some cases, this non-determinism behavior produces multiple, distinct outputs for the same input, which is not desired, of course. And, in other words, this translates to the verifier could accept invalid computations. Awesome. And, these are just a few examples of the hacks in the wild that, were produced by violating that property I mentioned before, the equivalence property. All right, so let's have a look at an example. This is an intentionally buggy example. Basically, the issue is located in that for loop. What happens in here is that we don't loop up to n, we loop up to n-1, and the last, and if we instantiate like this example with n equals to 3, we realize that the last, so I didn't explain what this code does. So basically it takes like a numerical value and it will output its binary representation as an array of bits. And what is going on here when we instantiate this example with n equals to 3, we realize that the third output signal is unconstrained. And this means that the attacker can pass any value for this signal. All right, so there are some strategies that are usually used to find bugs or vulnerabilities in zero-knowledge proofs. And one of these strategies is static analysis. So how this works, it basically applies some predefined rules to reason about bug patterns in ZK circuits. And like on the left corner, you will see an example. And for instance, for this example, since z, right, is a function of x and y is a function of both x and z, the static analysis techniques could infer that y is uniquely determined by the input x. So it is unconstrained. It is constrained, basically. Another technique is SMT. And we can basically express this under constraint property as this logical formula here. And it is what this logical formula says that for every input that we provide to our witness generator, then we will always obtain the same output. So we don't have non-deterministic behavior. And for instance, if this property is satisfied, it means that our circuits are under constraint. So this is how SMTs find vulnerabilities. Of course, these strategies have pros and cons. For instance, static analysis is scalable, right? But it is not as precise as SMT is. However, even if it is more scalable, static analysis could provide false positives, and SMTs, even if they don't scale, they are the most precise in terms of security guarantees. So what we did at Veridize was to implement this tool called PyCus, which is a verifier that automatically checks whether a zero-knowledge proof circuit is under constraint. And what we did was to combine these two techniques that are, interactively communicate and share knowledge throughout the process of finding vulnerabilities in zero-knowledge proofs. So whenever the SMT gets stuck because it doesn't scale too well, static analysis could provide it with some help. So basically, here what we do is to combine the strength of both static analysis and SMTs, and the partial results from one phase to another can be used throughout this process. And at the end of this process, if PICUS will output true if it can prove that this set of circuits is properly constrained. It can also output false if it found a vulnerability in the constraint, and a question mark if it wasn't able to find anything relevant. And that's because, like PICUS also takes in a timeout. So when we reach the timeout and the tool doesn't find anything, then, it stops there. All right, so if you want to find out more about the tool, you can definitely check out our PLDA paper. We explain, we also share some results we obtained in the past, and you can check the paper by scanning this QR code. All right, so I prepared a demo of PICUS on our security as a service platform. So what you see here is the interface of our platform, and we basically upload the source code and select the circuits that we want to verify, and we submit. Basically here I selected the buggy version of this code, and we will see soon the non-buggy version of the tool analyzed to see what's the output of PICUS in that case. So here PICUS says that for input, for a specific input, we get two possible outputs, which is a warning that our circuits are non-deterministic. All right, so now we select the fixed version of it. And we will see that PICUS basically will say that it wasn't able to find anything wrong with the circuits. All right, so I would like to briefly talk about another tool, which is ZK Vanguard. So this is a static analyzer, and what you see on this slide is the general workflow of a static analyzer. So we start with the source code, which we compile and then represent it in a way that our analysis can reason about the circuits. And by taking in some detectors, we will output a report if we found, or not something in the code. And this analysis representation is actually a constrained data flow graph, and I will explain shortly what this means. And of course, like ZK Vanguard has multiple detectors, but today we will focus only on the under constraint output. All right, so this is a simple example. Basically, this template adds two binary values, and the constraint part, you see like the second part of this example is the constraint part and the computation part. So the problem here is that we don't actually, our output signals are not constrained. Basically, there is no constraint on the input signals. So this leads to us being able to input bogus proofs, and the verifier will be able to, say that, okay, your proof looks fine, even if I inputted something wrong. So what is going on here is that, for instance, if we want to add 1 and 0, the output should be like basically 1. But if we set the proof to the carry 1, the result should be 3. So we basically are able to prove that 1 plus 0 is equal to 3. And the verifier accepts that because the constraint doesn't, refer the input signals. Okay, so this is how we represent in a visual way what is going on in that circuit part. The arrow lines mean that there is a relationship between the inputs and the outputs, and the dotted line means that the constraints between the input and output. And if our code is basically properly constrained, there should be dotted lines between all the inputs and outputs nodes in this graph, which is not happening here because we only constrain there are only equality checks for the output signals. Okay, so I also prepared a ZK Vanguard demo on SAS. It works similar to our PyCast tool. Basically, we have to upload the Circum code. We select the path, the source path to the circuit. All right. Perfect. And now we select the under constraint outputs detector to see what Vanguard does, if it is able to detect something. All right, and Vanguard was able to detect that we have under constraint signals, and it mentions precisely which of the signals are under constraint. Okay, some takeaways. We all know that hidden ZK bugs could lead to severe financial consequences, and at Veridice, we try to mitigate these kind of situations by implementing automated tools that can automatically detect these vulnerabilities. And two of these tools are PyCast and Vanguard, which employ SMT reasoning and also static analysis to secure the ZK products. All right, so yeah, thank you very much for joining me. If you want to find out more about the audits that Veridice performed in the past for all of these ZK clients, you can scan the QR code and it will direct you to the page, the audits page on our website. Do you have questions? Thank you.
In practice, when you write a circuit, there are multiple constraints on the same piece of data.
Yes.
So you can only detect whether it's totally dangling. But if you're missing something crucial, when it's already slightly constrained, there's nothing you can do, right?
I don't think I follow your question.
I have a bit that is completely unconstrained, you can detect it. But if I have one constraint that touches that bit, you're already fine. But what if I need multiple, but because in the logic of the program, you need multiple constraints, there's nothing you can do, right?
Of course, we are reasoning about all the constraints that are part of the program, right? So if we find we try to reason also about the relationships between all these constraints, right? So for instance, an example is ZK Vanguard, which uses as an analysis representation this directed graph, and it tries to reason about the relationship between the input and output signals. So these kind of things could be in practice detected.
Thanks.
Okay.
Okay, thanks. We have right here. I'll look for Augusto. Thank you. Here. Okay, let's please welcome Augusto from Polygon Maiden.
Hello, everyone. I'm Augusto, and I'm here representing the Polygon Maiden team. And I'm going to be presenting the work that we have been doing for recursive verification on the rollup, on the Maiden rollup. And Maiden is a project that has both a completely new virtual machine and the rollup. And just a heads up, like most of the work that I'm going to be presenting here, it's actually a result of the teamwork, and I have done a little bit of this that I'm going to touch on it, but it's also like a lot of work of my colleagues. This is the outline of the talk. I'm going to talk a little bit about the approaches of recursive verification that we have considered, and then we're going to talk a little bit about the pros and cons of like the approaches that we have looked at, and then we're going to have a look at the requirements that we have settled for our rollup, and what are the goals that we have for our rollup in terms of performance. And then we're going to look for the verifier costs and identify if we can actually match the goals that we have in terms of performance with verifier costs. Later on, we're going to look at some optimizations that we're implementing into the rollup, and I have like some results at the end. So the first approach that we have considered for the rollup and for like the recursive verification was to use a specialized circuit, right? So we would have the virtual machine in the bottom. And it's a general purpose virtual machine Turing complete. You can input to it any kind of program that you want, and as an output of the execution, you have your proof. And you can do the verification of that proof with a specialized circuit. And if you do that multiple times, you can aggregate multiple proofs, and then you have like a aggregation of multiple proofs. The second approach that we have considered is just to use the virtual machine itself to do the verification. And we can exploit the fact that our virtual machine is Turing complete. So we can just write a program that does proof verification and run that inside the virtual machine. We get a proof of execution from the virtual machine, and we basically achieve the same thing. So like these are the two approaches that we considered. And the question is like, what are the pros and what are the cons between these two implementations? So we have the question of like, we have the dimension of flexibility for the two approaches. And in this case, the virtual machine implementation is much better. And the reason why it's better is because we can actually run the verification procedure inside the virtual machine, and because it's a virtual machine, we can actually just run extra code alongside it, which means that we can basically do anything that we like after the verification or before the verification. Another dimension that it's actually important for us is the complexity. We usually try to maintain complexity at a minimum for everything that we do in the project, and that's a trade-off that we try to make things as simple as possible. In this case, the virtual machine approach would be more complicated because we have to have multiple implementations of the verification of like the circuit. There is a question of auditing, and in this case, we believe that having a single circuit, it's easier to audit instead of having multiple circuits, which would be the first approach, where we would have one circuit for the virtual machine and another circuit for the recursive proof verification. And the last dimension is performance. In this case, the specialized circuit would be definitely the best version for performance. And the recursive verification inside the virtual machine depends, and that's basically what the talk's going to be a little bit about. So those are the approaches that we considered. Let's talk a little bit about the requirements that we have for the rollup and the goals that we have set for ourselves. So we decided to go with the single virtual machine approach, basically because we get the extra flexibility, and we are using that extra flexibility to build the rollup. In our case, we allow the users to generate local proofs before they send the transaction to the network. And when we receive a valid proof into the sequencer, that does not necessarily mean that a valid proof implies into a valid transaction. So we need to run extra code to make sure that the data that it corresponds is packaged together with the transaction is actually valid. For example, to make sure that the account state that's being transitioned is the correct account state. So that's the reason why we decided to go with a virtual machine instead of a specialized circuit. We also have like some other requirements like security guarantees, and we're targeting 100 bits of security. And besides that, we also have like some expectations on the side of the programs that the users are going to be running. Because we have local proving, so the users are generating proofs locally. We expect these programs to be from very small to medium-sized. And that's captured on the number of cycles that I have represented in the slides. This is something from a few microseconds to generate a proof to like 1 or 2 minutes on a Mac Air Pro. But like there is still like relatively small programs. And the question is, can we do proof aggregation, like recursive verification with these programs. We are targeting for ourselves 2 seconds recursive proofs aggregations, and the goal is to have 2 seconds in commodity hardware, so like laptops like this, and also into server, and like if we go with a beefy server with like tons of CPU cores, GPUs, and lots of memory, then we can actually increase the ratio of transactions or like proofs that we're verifying on the same batch. But in general, we are targeting 2 seconds for recursive proof verification. And the question is, what can we do in 2 seconds? Because that's what determines how much work we can actually put inside the program that's going to be doing the verification. And here I have like some reference points. These is the current numbers that we have for our virtual machine. And as a reference, I put it like Blake tree. But keep in mind that Blake tree is actually not part of our constraint system, so we actually cannot use that for recursive proving. It would be amazing because in 1 second, we can actually do a lot with Blake tree. We currently use a version of Rescue Prime. We call it Rescue Prime Optimized that takes 6 seconds to run that many cycles. And you guys probably know it, but you can think of cycles as like numbers of rows in a trace. So this is clearly not 2 seconds that I mentioned before in the previous slide. The thing that we're trying to do is to reduce the gap between the RPO hash function in respect to the Blake tree hash function. We believe there is a lot of performance to be gained in there. And what we're trying to do is implement a new hash function that's going to be more optimized. We are not going for Poseidon, which is the one that has the best performance right now, at least one of them, because there are some questions about the security of the hash function, and like there's some, it's just a conjecture, but it may not be sufficiently secure for the next 3-4 years. So we are sticking around with a different hash function that we are implementing and optimizing, and we believe, and we have prototypes for this already, but we believe that we're going to be able to do this many rows in the trace in 2 seconds, which fits our target for the aggregation of proofs for the recursive proof verification. We're also doing some other things, like we're removing traces from, removing columns from the trace, which also improves performance and makes sure that we can actually reach our target. So this is the first thing, like this optimization gives us 2 to the power 17 cycles. And we want to do a 2-to-1 on commodity hardware, like a proof of aggregation on when we do recursive proving. So the question is, can we do 2 proofs in that many cycles? Or can we do 1 proof and half of those cycles? The rest of the presentation is basically the performance changes that we have done into the virtual machine and into the rollup to achieve this. So the important thing is actually to know where is the cost coming from on the recursive verification. And most of it comes from the SARC verifier. We do have some extra logic on rollup, but it's not the majority of the cost. And I believe, like, you all know these, but that's just like an overview of like the main points of the SARC verifier that we have to take in consideration when doing the performance analysis. And for our virtual machine, the design of the virtual machine is as such that we can actually analyze things independently in terms of hash and general computation. So just to understand why, I have like a tiny little diagram of the virtual machine, and these are the 2 important things of the architecture of the virtual machine that allows us to have like this independent analysis. And the main thing to notice here is that we have a chiplet, which allows us to do hashing operations concurrently. And we have another main processor that does general purpose operations. So we can run these 2 things in parallel inside the virtual machine, and because of that, we are going to analyze the 2 things independently. And if you guys remember, I had like some goals for the sizes of the input programs from the users. These are all the sizes, and we can clearly fit all the hashing operations that we need to do recursive proof verification on the number of cycles that we have targeted. So that's not our bottleneck. Our bottleneck is actually on the general computation, and that's where we have spent time trying to optimize things. And the next slides are just going to be about the optimization of these things. So again, this SARC verifier like steps on a bird's eye view. I'm not going to be able to go over everything because I don't have enough time, but we're going to focus over these 3 sections of the SARC verifier. And we have to do these in 2 to the power of 16 cycles or rows in the trace. Starting with the fry layers, there are 2 operations that we care about, the folding and then doing the evaluation, proving the degree of the remainder polynomial. We have a general approach that we could do for the remainder polynomial, like a degree verification, which would be to run a entity inside the virtual machine, which would be extremely slow. So that's not what we do. What we actually do is that we do the entity and provide non-deterministically the inputs to the virtual machine. And we do all the computation using the barycentric form. So we can actually do the remainder, like we can prove the degree of the remainder polynomial up to 8 in 3,000 cycles. So that is a little bit of the budget. The next thing that we have to take care of is about the folding. And here we have a trade-off, because if we do a folding of 2 to 1, we decrease the number of operations that we have to do in the virtual machine, but we increase the number of hashes because we increase the number of Merkle trees that we have to commit into. And there is a trade-off here. We decided to go for a fold factor of 4, and we have implemented native instructions in the virtual machine to support this. That way, we can actually do 1 layer with 3,000 cycles. The number of layers is going to depend on the input program size, and that depends on what the user is doing. So yeah, like relatively quickly, but like we have to analyze later on if that fits for the size of programs that we care about. Besides the folding, we also have to take care of the deep composition. And here the biggest thing is like the random number generation and like the arithmetic operations that we have to do. We basically did the same strategy. We implemented 2 new instructions to do linear combinations, and we also optimized the formulas that we use inside the prover to remove any redundancy and checks that we didn't need. The last thing that we have to take care of is like making sure that we can evaluate all the error constraints in a sufficient number of cycles. And here we are doing something very interesting. We are trying to target 2 problems at once. We are doing this by implementing a new programming language, at a high-level programming language that allows us to define traces for Stark-proof systems and the constraints between the columns. And that's a general programming language that can be used to implement any Stark-proven system. And we use it to do 2 things. We can have a centralized definition of the constraints of the virtual machine, and then we use the compiler to generate both the program that's going to run in the virtual machine itself and the prover that's actually going to be run by the user. So we only need to audit, in theory, the specification of the constraints in AirScript, which is much easier than doing that in Rust or any programming language. And we also have the benefit that we can actually run a compiler here and do some optimizations to make sure that we actually hit the 2 seconds target. So here's a summary of all the measurements that we have done so far. If you look at the bottom of the first column, we are in 36K rows for the Stark verification, and the only thing that's missing is the error constraint. That's the question mark, but that leaves us basically a budget of how many instructions we can spend doing the evaluation of the error constraints on the out-of-domain point. This is currently the open question. Can we actually feed the evaluations on 30K cycles? Because that's what is left in the budget. And we are pretty sure that we can do this. I hope you guys enjoy this, but it's like super exciting work that we have been doing. I think it's going to be super awesome to be able to have like 2 seconds to do the recursive proof verification, because that's going to allow us to have like a very quick block production on the rollup later on. And that's all that I have for you guys. Thank you for watching. I think one question?
Yeah. Hi, thank you very much for the presentation. Super interesting. I'm curious about the state of development of the recursive proving.
Yeah, okay, so we currently have a implementation of the backend that generates the MIDA assembly code for the constraints, the error constraints. the Winterfell prover exists, and we can actually run prototypes in the virtual machine. The biggest piece that we're missing is that we don't have the whole virtual machine defined in AirScript yet. And the reason for this is because we're thinking about implementing GKR. So we are first going to finish the GKR, and then we're going to finish AirScript. So like there's some limitations there, like there's some bottleneck. Once we have GKR implemented, then we're going to finish the recursive proving.
Great. Last question. And it's potentially a bias that I have, but I have the idea in my head that it's pretty novel to be able to make like client-side proving. And so potentially what were the bottlenecks that were there like 1 year ago? Or what happened that enabled us to make client-side proving a thing now? That wasn't possible?
Okay, there's quite a few things, right? Like the size of the field that we are using, some optimizations, barycentric representation, GPU acceleration. There's just like a lot of work that has been done by dozens of people that has been going into this and making sure that we can do everything fast. So it's just like a lot of engineering work that goes into it, and there's many small pieces that helped us. Okay, thank you very much.
Okay, thank you everyone. Well, to conclude this journey, we will have a special fireside chat in a few minutes, so please stay, and we will ask the people from outside to come in. Juan Bennett, CEO of Protocol Labs, will be here with Omer Shlomovitz, that will be remote, CEO from Ingonyama. So please, in a few minutes, we will be starting, okay? Thank you. Just 2, 3, 5 minutes. Here.
Not yet. He might not realize that he's being live streamed. Okay, perfect. Are you ready to go? Perfect. All right, great. So let's start here. Welcome, everybody. We have a very special fireside today with Omer, a founder of Ingonyama. I'm very excited to chat with him about a set of things today. After the whole day talking about ZK in the depths of all the tech, I want to take a bit of a step back and talk about something very important to a lot of you listening to this, which is how to build these technology startups, especially in the area of ZK, because it's an area of cryptography that is hard, that for a long time was developed, but it wasn't fully breaking through to get into the market. It requires a very special combination of factors to be able to build a great startup in this space. And I want to use Omer's story and Ingonyama's story to help you go and start your own things and build great applications and great tech on top. So the format for the conversation will be 15 minutes where I'll have a set of questions, and then 15 minutes for Q&A with the audience. We'll span a whole bunch of topics, so think through the set of things that you want to talk about. Well, without further ado, Omer, thank you so much for being part of this, and for having this fireside with me, and more broadly for hosting this entire event for everybody. It's been awesome to see all of the talks, all of the speakers have been amazing, and everybody here has had a great time. So thank you so much, and welcome.
Thank you for hosting us. It's part of Protocol Labs next week. We are very happy and proud to be contribute and take part. Very exciting week for us. Thank you.
Great. So I just kind of want to start in kind of the beginning. Can you tell us a little bit about your story on what got you into thinking about starting a company, maybe even earlier, like what got you into computer science in the first place, like, or maybe cryptography? Like, how did you get to thinking about what eventually became Ingonyama?
Right. So my roman with cryptography goes way back. I mean, I don't have a good explanation for that, but I always had a thing with cryptography. Starting from these very high-level books, but eventually I knew that I need to understand more about the theory, which led me to take PhD route to kind of like dive deeper into computer science, math, complexity, cryptography, to understand it better. And indeed, like the other part of this my equation is being an entrepreneur, right? So these are like two things that not necessarily go hand in hand, but it's another thing. It's another kind of like thing that always been there for me. I mean, I've spent quite many years in Israel in intelligence, and it might seem very different, but obviously, first thing is I always inspired to involve cryptography with whatever project I was working on. And second, I always found myself in this position of innovation and trying to find something new. I mean, so when it is back in intelligence, it's mostly about resources, like you need human resources to convince this. I mean, when you convince this kind of like what you get. In real life, you get money, right? So yeah, I mean, eventually, my last hope before I started Ingonyama was another crypto company or another startup which I founded, and where I worked on this intersection of infrastructure and cryptography engineering. And I knew that this is it for me. I knew that this is like my passion. I'm kind of like, this is it. Now, the one optimization that I could have made was that my previous company was a consumer-facing company. So there's very little you can do at some point when the company is going with actually, to keep the cryptography innovation. I mean, you want things to be of like stable as much as they can and focus on other things. So eventually realizing that I left this company, which, you know, already part after like founding it, but immediately it became clear what I need to do next, right? So with zero knowledge, just like with any other technology, when it gets to, or when you want it to go into mainstream, you need the software, you need the algorithms, you need the hardware. And for zero knowledge in general, privacy enhancing technologies, it was very clear that hardware was missing. And for me, it was a very sweet spot, right? So I'm kind of like pushing on my passion for working in this, like, you know, building infrastructure for cryptography. But now instead of focusing just on software, we start from the hardware and do the full stack of hardware plus software. So yeah, I mean, it was very, it was very clear for me that like this is what I need to do.
In that area, especially when there's something so that others haven't done, and that seems so like a strong potential for you, but because the market hasn't yet done this, and there isn't yet demand for a product, you have to take a very big leap and have to reason through the risk profile. What sort of gave you the conviction to know that this was going to develop into something very significant, or how much of a risk do you think you were taking? You know, it's always very different in every startup what you think is going to work out, or how the market is going to evolve. But like, what gave you sort of like the conviction? How do you think through the model to figure out like, oh yes, this is definitely going to be the future. There's so much here that this entire ZK field is going to grow into and explode eventually. That gave you the conviction to go get started on this.
Yeah, I mean, so first of all, we're still not out of the risk zone. I mean, I wouldn't say that we are a successful company. We're always, you know, trying to challenge ourselves and keep pushing and shipping and execute with a velocity that hopefully is just, you know, accelerating. But at least the initial conviction first came from my network, right? So, for example, Justin Drake, right, like is the, like, let's say, the godfather of Ingonyama. I mean, when you hear him talk about like the future, what's going to happen in 5 years, in 10 years, and you let yourself like be open to these kind of conversations and you know, imagine how the future is going to look like, it's very clear. I mean, in our specific case, as I mentioned already, one thing is, just like with AI and other kind of like major technologies, you have to have this kind of like important level of hardware, but also ZK fundamentally removes trust from a system, right? And I was already in a place where I worked in this space, like I've seen, like, you know, the mission that all of us take is basically about decentralization. So I knew that ZK right now it started from blockchain, from Web3, because we are lacking this assumption of trust, and we simply don't have it, right? So we are forced to work with these technologies, but anyone can use ZK and other such technologies to remove trust. It can be any kind of like Web2 corporate. So basically I see this kind of like, you know, diffusion in the next few years. So it was very clear to me that one, the answer is going to be in hardware. I mean, processors today, CPUs and other accelerators, simply not good enough and are not designed to support cryptographic applications. And the other thing is that ZK is, like, the nature of ZK is that it's going to diffuse over time and going to be, going to impact, like, basically it's very fundamental technology, it's going to impact any vertical that would want, you know, to remove what we already seen in the space, but we know it's going to be elsewhere as well. Just remove this like centralized risk from systems.
Yeah. So, and yeah, thank you. And as you got started and you started building Ingonyama, how do you think about productizing the technology? What were some of the first things that you tried? Maybe talk about any kind of early successes or failures. How did the product development go?
Yeah. So the original idea was to build a semiconductor company, and at least initially I thought it would be like the classic way to do it, which means you do some design, like for the hardware, you implement it first on FPGAs, you find some traction, you know, some early demand from customers. Once this demand increases enough, you go to an ASIC, and from that point on, you basically kind of converge into Moore's law. So as the technology matures, there are cycles, and each time you develop a better and better chip that can give better performance to customers, which we hope, again, going to be everyone, because I imagine this kind of like silicon in phones, computers, anywhere, right? Now, this is, was too ideal, right? So obviously the market is not there, which is one thing. And the other thing is that you learn about what it means to actually build an acceleration for zero knowledge, right? So originally we thought, similar to what you have today with AI, what we have with AI and matrix multiplication, we thought, okay, so we have this like big computational bottlenecks, let's remove those with acceleration and we're done, right? But it's not the case, right? You need to do much more than that. You need to think about how the memory is structured, the data movement, the bandwidth, the I/O, and all of that. You need to actually build a full-blown processor that is also going to be programmable, right? Remember that ZK is still extremely active field, right? It's like a moving target, and with hardware, like you need to add programmability to kind of like support all of these like use cases. Basically, what it got us to realize as a product, first is that we need to focus on existing hardware that we have today. I mean, the hardware is actually the boring part, right? Again, eventually it's going to converge into some Moore's law, and then once you have the design, I mean, you can always optimize it more in the next chip. The software part is harder. I mean, how do we get people to actually adopt a new processor, a new paradigm? You want it you want the developer experience to be very smooth. You want to have adoption already there. So that's what we focused on. I mean, we're just building software right now. Most of the team is actually focused on software, and not just software, also very high level. Like we can put more emphasis on the API and the high level Rust and Go language APIs than the actual performance. I mean, you really don't care if it's 10x or 11x, but you do want your developer to have a very kind of like good experience integrating with acceleration. And then we went with existing hardware devices and appliances, right? So it's GPUs using clouds, it's FPGAs and so on. And then, we just learn more about how these can be programmed and developed. On the one hand, IPs that can be used with FPGAs, IP cores, and also for GPU. This is kind of like a general purpose library that will allow developers to either port their protocols or products, parts of products dealing with ZK, or just implement. I mean, if you are from academia, right, just implement directly on GPU. I mean, why spend time writing for the wrong hardware, like CPU? So that's kind of like the trajectory too.
Yeah, and can you maybe talk through some of the use cases that you see up ahead that maybe people, that you see in the horizon that you don't yet see people doing or owning yet, but that you think are now becoming possible, whether it is using that software or others, or things that you are sort of excited about in the frontiers of ZK?
Yeah, I mean, the first thing that when you think about hardware is to enable, okay? So if we take an analogy from GPUs for gaming, right? So until GPUs were able to render at a fast enough speed, image, they were not really useful, right? So it's about enabling new use cases, and that's kind of like what hardware can give you, right? And eventually this is the scale that we are looking for now. When we are thinking about next year, first there are a few exciting chains and L2s that either launched mainnet or and going to start to incorporate provers in like decentralized way, which is very interesting, and we try to contribute to that as well, of course. Also, chains with privacy baked into them, like Alio, like as a first-class citizen, and obviously privacy here is based on ZK. So these kind of like things that are more of like the short term. It's pretty hard to predict how the prover networks are going to behave, because it's not necessarily going to evolve into a proof of work type of, like Bitcoin type of networks. So it's not really predictable. It might be something new. And then there was like more of the long term, right? Just a conversation I had earlier today is about like with AI. So what you have today, like if you're a data scientist and then you want to work with AI, is, I don't know, you have your Python and you just like build your model and you run it. You say this should run on GPU, whatever. You don't really think about it. And you want the experience to be the same, right? Like you want, or the way I see ZK here is as a feature, right? Like, so we want data scientists, and it can be others, right? It can be, I don't know, game developers, can be whatever. Anyone should be able, in their respective kind of like development environment, to be able to say, oh, now I want a proof that goes with this matrix multiplication, this like whatever math computation, this function. You just say, yeah, here add a ZK proof, and you are done. And the challenge is to kind of like match the expectation, because you want the proof not to be as a standalone, you want it to be actually part of the output that you get, and you want it to be fast enough so that the experience will be good enough. So I think that, you know, right now, somehow the entire space, I mean, almost everyone that talked today is talked about middleware and infrastructure, and I think it's for a purpose. Like something like, you know, intuitively we feel as a collective that these things should be get better and better, and enable, as I said at the beginning, and enable new use cases and applications. So I think that the really exciting use cases are still very far from where we are today, but we think in a very healthy way about how to enable them. So I just mentioned AI, which I think, I don't know, accountability for AI and verifiability of AI would be critical. And yeah, I mean, we can go over like many other examples, but the important part is that for all of them, there's like this good like infrastructure and tools that are being built today to enable them. And I think about them as features. Might be that there are different ways to think about them, depends on the context.
A lot of computing cloud-style products have gotten very successful over the last couple decades by simplifying the process of writing some code, some business logic, and wrapping it in a very easy way to schedule that computation and run it. In blockchains right now, we're exploring scalability by having lots of groups build these very large chains, and maybe we're starting to get to roll-ups and a few L2s and so on that are kind of scaling this. But we're still very far away from the fluid scalability that the cloud traditionally has had. When you get a few thousand or a few tens of thousands of machines, you put like a VM in it, and you put either different containers on it, or even better yet, you put like V8 in it, and you put a bunch of JavaScript functions and workers inside. What seems to be missing to me is like some concrete way of making that computation verifiable. So when are we going to get like ZK containers or ZK lambdas or ZK like these kinds of very easy pluggable functional units? So then sort of like scale all of the computation here much faster. Like, what do you think is missing?
No, I can just like resonate what you just said. We actually just released over the weekend a product announcement called ZK Containers, which basically thinks in kind of like similar lines. We have best practices, like we have all of this like wonderful infrastructure that works extremely well for scaling with other industries and become kind of like a standard. And I think we see now this kind of like movement to adopt and kind of like see how it works when you think about ZK. But yeah, I don't really have anything to add on top of what you just said. I mean, I have the same kind of like questions. And for us, I mean, when I have these questions, basically my team and myself, just sit down, we read, we try to come up with strategy and try to project what we think is going to happen. But for us, this is like very early in this journey. It's just something we started not long ago to conceptualize.
Yeah, awesome. Well, maybe like thinking ahead a little bit, and I'm going to ask a couple more questions, and I'm going to open it up to the room. So start thinking about what questions you want to ask. Maybe a couple questions. So one is, what do you think about other cryptography areas like FHE, like fully homomorphic encryption? Do you think it's going to follow a similar path to ZK, just kind of a little bit further out in the future, or do you think yeah, how do you reason about it?
So personally, I'm extremely excited about fully homomorphic encryption, and we've been actively working on this field. Now, what I can say is that it's different than ZK. So recall that I told you that ZK has this impact on decentralization, right? So with fully homomorphic encryption, it's basically an encryption, right? And unfortunately, the way I view it today is that it's much more IP intensive than zero knowledge. So because maybe, I don't know, I don't have a good explanation for that, but maybe because zero knowledge was developed over the last decade, mostly in the space, we don't have this, I mean, no one is going to win or going to kind of have an IP claims here about anything. It's kind of like we work on this together, and that's a beautiful thing. We don't see it quite often in cryptography, and that's very sad. Now, with fully homomorphic encryption, the way that I view it is that there is much more IP already, like patents and all of that. And this is kind of like how it's going to be, how it's going, right? So first, in terms of like the DNA of how this technology will mature, it's just a bit of a different in terms of DNA. Also, and again, because we've been pushing ZK in a very impressive way, we see amazing results almost every day. Fully homomorphic encryption main target is right now outside of Web3. I mean, of course, we talk about it in the context of Web3. We want to see how it's being used for privacy and together with ZK and all of that, but it's also going to be extremely impactful. I don't know, just imagine with today, like ChatGPT, like all these LLMs that running it on like remote server, I can just encrypt and send it, and it will be processed, like the data going to be encrypted. I'm going to get like the ciphertext and decrypt it. It's fantastic. It's going to save a million problems, right? And by the way, it's also going to be pretty much a game of hardware acceleration, which is going to be critical here. But yeah, I mean, we do want to see, or maybe we might see here that the adoption starts from more the Web 2 kind of like data centers, and then also go into what we have in Web 3. Maybe, I don't know, just my opinion, or I'd like to also hear what you think, but that's kind of like two differences I see between ZK and fully homomorphic encryption.
Yeah. And what are your thoughts on AI? When are we going to get, I mean, you mentioned it a few times already, but as you look ahead to some of the improvements that we're seeing dropping from the AI community over the last year or two, and you maybe think ahead like 2, 4, 10 years out, how do you think that's going to both open up application space or even change what you're doing directly, even what we're all doing? When are we going to get like models writing the ZK applications themselves or the foundational SDKs and whatnot? How much of this are you tracking? How much of this are you excited by or worried by?
Right. So two things I can say. One, since at least with all of these new advancements in AI, obviously us as a company, right? So from my personal experience, we've been using it extensively. Like we've done this hackathon around ChatGPT a while ago, and in general AI technologies. So to make sure that everyone, like literally everyone, including HR, including everyone, basically is using it on a daily basis, and we govern these tools and we keep them updated. So this has definitely become part of our life. Now the question is, how do we get ZK to be part of? I mean, there are it's like two directions. One is when you think about ZK and AI, how we can bring AI to ZK, and also how we can bring ZK to AI. Right? So what I mentioned before is that when you look on a big, very energy-consuming AI system, so ZK is probably going to be a feature, right? Fully homomorphic encryption as well, kind of like maybe something like a feature. The thing is that this space, like the AI space, is moving so fast, so it really requires a lot of motivation for someone to actually say, oh, I'm going to actually buy into that. And then the question is, how is it going to evolve? So regulation might be, there was this executive order recently around privacy with AI. I mean, there might be this kind of like, regulation reasons that will just force AI to start to use more ZK kind of tech. There's also might be some real damage because of deep fakes and all of that would kind of like make the best practice to, you need to watermark this and that, and ZK is becoming like a very standard way to do that. So that's kind of like might be the door, the door into incorporating that. The other way around, by the way, it works nicely already. Like we have a lot of hype, but also many companies doing already, like bringing AI on chain, which is fantastic, and it's going to be, I'm sure, going to be like even next year we're going to see actual products that are using it, actual protocols that are using AI on chain. I mean, it's going to be beautiful, and I'm looking forward for it.
Yeah, awesome. Well, any questions from the audience? Raise hands, and we'll get a mic to you. The first one is always, yeah, there we go, back there.
Yeah, congratulations on getting new funding for your ASIC project. So when is your chip coming out? What's the plan for that?
Yeah, so about ASICs. First, there's a question on how semiconductor companies are making their first steps. And I'm going to argue that it's basically about luck, okay? And it's our goal to make sure that we are positioned in such a way that luck finds us, okay? Because obviously, as you can imagine, no one, like no big VC, is just like walking around with a check size of $50 million, $100 million. Because if you want to beat like latest GPUs with at least the ASIC to imaging, which is pointed out, programmable and so on, then it's going to cost a lot. Like you need the latest technology and such. So no VC is just like wandering around and trying to think where you can invest this, I don't know, big check when there's no real market. But on the other hand, as I mentioned, ASICs are going to be enabled, right? Because if you have ASIC, it might be open. You can open up all these new use cases, so it will grow the market. So here you have this like chicken and egg situation. Therefore, it's going to start from luck. So for us right now, it's less about, or at least the way that I've built the team is to become, it's a very diverse group of generalists, and we try to stick with the market. And I mean, obviously, to educate and do our part, and at events, to bring everyone together, but also to try and help, like to do this kind of like tide where everybody can improve their products. So today we understand the needs, and we try to make sure that any company that wants ZK acceleration can have access to it. It should be open source. It should be very easy to tap in. It's just a few clicks to move from CPU to GPU. Now, once you pass this barrier, then it's a matter of, okay, I mean, we can jump in technologies according to market demand, and then and at some point, eventually, have this like ASIC that we imagined. So, I mean, it's a very long answer to say that I don't have a date for a tape out, if that's kind of like the essence of what you wanted to hear. And the way that we try to think about it is basically taking steps, not just to say, meet me in 2-3 years, I have a chip, I don't know if it will be good for you or not, but to make sure that we at any time assess both the risk and also the opportunity, and make sure that everybody around us can benefit from acceleration today. Okay, that's what we care about, and I hope that ASIC can be very soon part of this, like ASIC tape out, not just design and building IP cores and do small chips and all of that. Like actually do the full-blown ASIC is going to be part of our roadmap very soon. But yeah, if you happen to have 50 million check, let's talk afterwards.
All right, back there.
How are you thinking about the distribution of the ASICs so that you distribute it in a fair way to service providers so that you don't have centralization?
Yeah, that's a good question. So Maybe at one, there are even like few dimensions there, right? So one level here is that obviously if we want acceleration on your mobile, so it's not like Apple are gonna have another chip inside their iPhone, right? So we need to think in terms of what's the best way to integrate to kind of like build a pickle that helps them. So it might be led by some kind of like decentralized identity or something like a very specific use case that is of interest to them. We also see, I mean, there are places where we start to see this kind of like, for example, with computers, with laptops. AMD started or will start to ship laptops with AI engines, which is a very powerful technology for ZK acceleration. So right now we're still relying quite a lot on the distribution, which is already in place. iGPU is commodity hardware. So we rely mostly on the distribution that's already in place by these like giants like NVIDIA, AMD, Intel, and hopefully Apple, Samsung, and the likes. Now, the question is, what will happen once there's going to be a chip? And it's a good question because remember that these chips are dealing with security and privacy. So just the the geofence between China and the US is going to create one issue, right? But there are many other such issues. So going back to my argument about we start from software, I can first make sure that everybody adopt best practices and easy way to, and maybe there's kind of like there was a talk today, kind of like having this like standard API working with hardware. So we start by kind of like making it easy to integrate with hardware. Then obviously you want to make the price of the chip very low, you want to make it accessible. Now I don't have good answers for that yet, but it's going to be a challenge. I mean, this is something, I don't know, maybe Juan has some ideas here on decentralization for the semiconductor levels, but it's definitely a good question.
Would the focus be more on clients, so more on consumers, or like big service providers that would be crunching a bunch of these snarks?
So this is just my opinion, but I don't think like we need to focus just on one of them. I mean, I see also this like trend in academia on how you can even have privacy when you use servers, right? Like MPC plus zero knowledge. So it seems like shaping to become a reality very soon. So in theory, like data center can cover all of the use cases, both of scaling and privacy. In practice, I really hope to see client-side zero knowledge. For example, with gaming, I think it's going to be crucial because it's gonna fight like the data. Like you want to also remove some burden from the data center and to save some money. I mean, there are different reasons like why you want to do client-side. So, I mean, according to what I said before, the goal is to and maybe it's not just like my company, obviously other companies, and we have many companies focusing on that area at this point, would do client side, but also like server side.
Hello there. I would like to ask how future-proof the general methodology in ZK systems are. So let's imagine the mobile phone of the future. By 2030, if my published predictions are correct, we should have a 5 petaflop per second, 20-watt mobile phone that has a really advanced GPU inside miniaturized, and that would be equaling the current top GPUs today. And it would be able to run, advanced AI software and some other stuff. So how would the equation change in this case? That's my question.
I mean, I'm not sure to what equation you are referring to, and also we have to compare notes about where we will be in 2030. But basically, first, maybe I wasn't clear enough about that. The GPUs are extremely good when it comes to running ZK workloads. I mean, definitely there's room for improvement. And as I pointed before, there's Moore's law in a way that you can imagine how we converge into some kind of like growth, whatever, like a kind of like growth with technology. But the GPUs, and if anyone would ever want to have an ASIC, it should be better than a GPU. But GPUs are not static. I mean, they keep improving. So right now, if you try to project it to present time, you have GPU, and that's kind of like, let's say, GPU, FPGA, whatever, like state of the art. And we are growing, like the performance is going to improve on the hardware side at least with the changes and the updates to GPUs. There's one trick which we didn't really get to as an industry, which is to do hardware software co-design. I'm going to tell you the restrictions that I have for the GPU, and then we're going to come up with this algorithm and protocols for ZK that are more hardware friendly for the GPU or for the FPGA. So that's like another kind of like boost that we can have. But eventually, steady state, it's going to be a very predictable kind of like change. And at some point, it will cost some critical mass, whatever, and some applications will become possible to do. And then we might see some jumps, right? So if there's a specific use case that is critical for mobile, there's going to be an ASIC for that or some IP core for that, and you can see a jump, right? It's going to lower the power consumption, it's going to make latency or throughput like way better. I'm not sure if that's what you meant, but that's kind of like the way I see it. So bottom line, hardware is predictable, right? That's what I'm trying to say.
All right, thank you. I think we're a little bit over time, so let's stop there. Omer, thank you so much for sharing your time with us, and thank you for putting on this awesome event. Really appreciate all of the participation in this field, and it's great to see all the acceleration you're bringing. Thank you so much, and take care.
Thank you.
Okay, well, thank you, Juan. Thank you, Omer. Well, I think that's it for today. Again, thank you for being here. Thank you, Chloe, for all the hard work today. Chloe from Geometry, that it was a lot. So thank you. Thank you to all the sponsors. They're right here. The partners AMD and Lambda. And all the sponsors, Geometry, Elliot, Take, O'Neill, Electron, Star Wars, ReZero, Lumos, Sama, MATLABs, Marlin, Polygon Maiden, IOSG, QED, Ola, Lagrange, and AWS. Thank you all. Thank you to all the speakers that were not from any sponsors. We really appreciate that. The speakers and the person who were on the panel. Thank you, Juan and Omer. Thank you to the AB team. Well, let's hope to have many more of these. Thank you for coming. Bye.
We had the most incredible experience working with Copenhagen Streaming for an event that we organized during DevConnect, hosted by Protocol Labs and Inganyama. All of the team were incredibly attentive on the day, flexible, managed to work out any issues which we had from an AV perspective, and I would 100% recommend working with them again, and I will definitely be doing so in the future.
That was really nice.
One more.
We had the audio turned on in the beginning. Can we just do it again?
Yeah. Oh. Okay. Maybe I didn't do a good job.
Should I say something? Just so we know that. Anything. Just
Me? Oh, testing, testing. Testing.
I heard something. Yes. One moment.
One moment.
All right. That was better. Okay. When you're ready.
We had the, oh, my mic's not on.
Yeah, but now it's just going in
Oh,
the
right.
recording, so now it's good.
We had the most incredible experience working with Copenhagen Streaming for an event that we organized by Inganyama and Protocol Labs at DevConnect this year. The team were incredibly helpful on the day, made sure that any of our needs were met, and we would definitely recommend working with them in the future. I know I will definitely be calling them up for the next event, which I take place. Ah! Sorry. The end. Cut the end. Cut the end.
The next event.
Okay, thank you. Sorry, I'm not a natural speaker.
You were natural. That's very good. Thank you.
Hey, ses prova. Ses prova.
Hey 1, 2, 3, 4, prova. Hey hey, prova 1, 2, 3, 4. Tamam.